Welcome everyone. I will be moderating this session. We will start our day with a talk of Professor Barbara Nelli from Università dell'Aquila, Italy. The title of the lecture is The Shape of Subfilms and Bubbles. Thank you very much, Barbara, to be here. And the floor is yours.
Thank you, Fida. Let me share my talk. Okay. So first of all, I would like to thank the organizers for inviting me to give this talk. It's a great honor for me. And I have been in Lebanon, in Beirut, several times, and I had really good time there with you. And this is the image that you see. Of course, everyone knows it, the Sursock Museum, and I really liked it very much. I was there with Fida in January 2020. That was my last time in Lebanon and also my last travel before the pandemic. And I hope to see again this museum like that, because I know that after the blast of August 4th, it's not exactly the same, but I am confident that it will be the same in short time. Okay, so let me start my scientific talk. Please feel free of asking me question at any moment. Just a minute, I have to, okay. I have to, because I have the full screen, but I have something that, okay. So feel free, I'm not, as I have the full screen system, I don't see if you raise your hand and so on, but you can interrupt me at any time. So I will talk about the shape of subfilms and bubbles. How to change page? Wait a minute. Okay. So I will start with some images. Everyone knows that if you take a solution with soap and then you put inside a frame and you take it out, you will obtain some soap films like that. So the first one on the left side is a piece of catenoids. If you put two circles, you will get a piece of catenoid. If you put an helic, you will have an helicoids. And then on the bottom, in the right-hand side, you have simply a disk, the standard one. And then you have something very nice on the left side here. And this is a Costa surface, but I believe that this is very hard to really obtain if you put such a frame in the water, but it exists from the mathematical point of view. And then you have the classical soap bubble, so a sphere, and then two soap bubbles like that. And I put twice the double bubble. These and these are called the double bubble. And you know there is a difference between these two. The first one is with two different bubbles. One is bigger and the other is smaller. And this one, the third one, is two equal double bubble. Okay, so now let us give a look to the mathematics that is behind the soap bubble, and also the why soap bubble are important for mathematics. Both things. This goes in both directions. Okay, it's very easy explanation. If you have a surface and you have two pressure on the surface of the same force, then the surface will not move and stay flat like that. While if you do a pressure that is larger on one side than on the other, then you will have that the surface move and bend a little bit. So there is a number that you can define that is this h that I put there that is proportional to the difference of pressure. And if you want to see it in a more mathematical point of view, of course, h that I write here is known as the mean curvature of a surface. And if you want to see in a more mathematical point of view, everyone knows from first years of university, that if you have a surface in the space, you can measure, you fix a normal vector, and you can measure the principal curvatures that are K1 and K2, that are the curvature of the curves that curve more on the surface. And then if you sum up them and divide it by 2, you get the mean curvature of the surface. Okay, so this is exactly the number that we see before defining it as proportional to the difference of pressure. Let me give you another characterization of H of this mean curvature. That is the variational that is given by the variational approach. You will see in a moment why I want to give this approach. I will give it quickly. You take a surface, the yellow one, sigma, that is an immersion of D, that can be a disk, simply a disk, in R3. And then you take a variation of it, the red surface. That means that you have your original surface and you sum along the normal vector, the blue one, T, that is a parameter, H times the normal vector. H is any function defined on the same domain as X. Okay, and X of T, the image of X of T is this surface sigma T, that is a variation of sigma. Okay, so you can compute, at this point, you can compute the area of sigma and of sigma T. And what you get, the area, simply the area of surface. And what you get is that if sigma has mean curvature 0, that is called minimal surface, then it is a critical point of the area of sigma T. So it means that the derivative with respect to T of the area is 0. And if sigma is constant mean curvature H different from 0, then sigma is a critical point for the area, but you have to add a condition on your function H here that multiply n, and is that the integral of H is equal to 0. In fact, this means that if you look at the volume between the two surfaces, the volume of the domain of R3 that is determined between the two surfaces, it's the space where there are the blue stuff, this is kept constant, in fact. Okay? So why this is interesting for us, this variational approach? Because in fact, these surfaces are minimal surfaces, that is H is equal to 0. And you know that nature in general try to save everything, to save itself. So here, the nature tried to save the quantity of soap solution that you use to put as surface that have this boundary that to put inside. Okay, so nature save energy, in fact save area in this case, area of the surface. So H equal to 0 is a minimum for the quantity of soap solution that you use. And here sometimes, okay, and here in fact for soap bubble, you remember that I told you that you keep constant the fact that the integral of H was 0, keep constant the quantity of volume. And in fact, soap bubble are solution of the isoperimetric problem. I mean, if you take a volume, a fixed volume, and you take the surface that has the less area that include this volume, you know that is the sphere, so the soap bubble. Okay, so this is why the variational approach is very interesting for those kind of things. Okay, so now, of course, so mathematics is important for soap bubble, and soap bubble are important for mathematics. Let us see which kind of question we can ask for such a surface or such a situation. One can ask which is the geometry and the topology of a constant mean curvature surface, for example, bounded by a Jordan curve. Okay, it's a very natural question. We saw the the frame that we put in the soap film and so on. So this is a very natural question. So you take a curve, you take a CMC surface, and you want to know which is the topology and the geometry of it. Okay. When h is equal to 0 for a minimal surface, this question has a very simple answer. You have a curve, so in a plane, because it's a Jordan curve. Then the solution, the unique solution, is the disk that is contained in the plane of the boundary curve. Very, very easy answer. You can prove it. It's not very hard to prove it. But if the mean curvature is different from 0, then you are in trouble in general. It's not so easy to answer. There are two approaches for this. The first one is, okay, you have a curve gamma that can have some symmetries, for example, a circle, and you try to look if your symmetries in the boundary can be inherited by the surface in order to determine its shape. For example, look at that. If you have a circle, you can imagine that the constant mean curvature surfaces that have this circle as boundary are the two spherical caps. These are the two spherical caps, the small one and the biggest one, because the sphere has constant mean curvature. Or I wrote it like that because the answer is not known, okay? And then you have another way of studying this problem that is, okay, so assume that gamma in fact has no symmetries. And you can try to answer to some different questions, for example, to understand if M has topology or does not have topology. Is a disk, is a torus, what's M, okay? So we can try to study these two kind we will try to understand some answer to those problems, very simple problems. So let's start with the case with symmetry, the one that we would like to prove that there is the spherical cap, the small and the biggest spherical cap. Okay, there is a nice theorem in 91 that is a partial answer that goes as follows. Is due to Brito, Mix, Harper, and Rosenberg, and goes as follows. Take a convex curve in the plane. Let M be a surface with constant mean curvature h different from 0 with this boundary that is transverse to the plane containing the curve along the curve. Then you are done. M has all the symmetries of the curve, and in particular is a circle. If C is a circle, then M is a spherical cap. Exactly what we wanted. But we have with this yellow assumption that is transversality to P. This is a very important assumption. And in fact, the tools for proving this theorem are different tools, but the ingredients, the principal ingredients are really two. One is a balancing formula. I will not enter in details about that, but this allows to prove that M is contained in one of the 12 spaces determined by P. You have a plane, so these balancing formulas plus transversality push the surface on one side of the plane. And then you need Alexander reflection method to prove that the symmetries of the boundary are inherited by the surface. Let me tell you something about Alexander reflection method, because this is really something very important for this kind of theory. Okay, first thing, maximum principle. Most of you knows probably maximum principle for PDE, okay? And in fact, this that I will tell you is exactly a consequence of the maximum principle for PDE. Because constant mean curvature surfaces are solution of a partial differential equation. But it goes as follows. You take two surfaces, tangent at a point, sigma 1 and sigma 2, and you assume that they have the same mean curvature, and they are one on one side of the other. So sigma 1 above sigma 2. Then they must coincide. Okay, this is something a little bit magic, but that comes from PDE, of course, and allows us to to understand Alexandre reflection method. Let me just give you some taste of Alexandre reflection method that is also known as moving plane method. Okay. For example, I will prove not really, but I will try to show you that if you take a surface that is compact in R3 with constant mean curvature, so it satisfies the maximum principle of before, then if you choose a family of parallel planes, you will try one of them that is a plane of symmetry of your surface. How it goes? As M is compact, you will have a plane that is far away from the surface, then P0, then you approach, you go to PT, and you find a first contact point. At this point, the surface is tangent to the plane PT. And then you go a little bit farther, and so you have a small piece of the surface, this white surface here on the right-hand side, and you do reflection across the plane PT. And you get this orange surface. At the beginning, it is inside the domain bounded by M, of course. And then you keep on going till the first point where you touch the boundary of the domain bounded by M. And this point is a tangent point, and you will have that the surface, the orange one, is on one side of the blue surface. So you apply the maximum principle as before, and you can say that this orange surface coincides with this left-hand side of the surface. This means that P tau is a plane of symmetry, of course. Okay, so you find the plane of symmetry. You can imagine that some modification of this method can be used to prove symmetries also for surfaces with a boundary in a plane. And this is what Britos, Harp, Mix, and Rosenberg use for proving their theorem. Okay, but as I told you, the general question without transversality is still open. And there is a conjecture, still, it's a conjecture that has 30 years, so it's an old conjecture, and that says that, I mean, you can prove that this surface is a spherical cap in the case M is embedded or as genus 0. Okay, so it's a, I mean, it's a very nice question and something very interesting to think about. Okay. Now, okay, of course, there are some partial results, but I will skip them. Let me go to the case with no symmetries, okay? So we will say no symmetries of the boundary, the case where I told you, well, there we can try to understand the topology of the surface. So I will tell you what is known in R3, and then what we do in this nice space that is H2 cross R, where H2 is the hyperbolic plane. That is a joint work with Giuseppe Pipoli that is in progress at the moment. You can ask me why H2 cross R? Well, H2 cross R represents one of the Thurston geometries. It is a simply connected homogeneous three-manifold, as all the three manifold that I put here are 3, S3, H3, and so Sol, Nil, and so on. And such manifold has been object of study of many authors in the last decade, in particular CMC surfaces in those manifolds. I will talk a little bit more about that just later. But now, let me tell you what is known in R3 about this problem with no symmetry. It's a very nice theorem by Ross and Rosenberg in JDG 96 that states the following. You take a strictly convex curve in the plane, then there is a number depending only on the curvature of this boundary gamma, such that whenever M is a surface embedded in the half space determined by the plane of the boundary, and has constant mean curvature small, that is smaller than this h of gamma and boundary gamma, then it is a disk from the topological point of view. Okay, so if you fix the boundary and you take h small enough, then M is a topological disk. Then you have also something about the geometry, is a graph, and so on. But for this, I prefer to show you a picture. M will be exactly this kind of picture. I mean, it's a graph here on the top, on the cylinder, on this gray cylinder, and the part that is outside here is a graph with respect to lines orthogonal to this cylinder. And what is very interesting is that here on the top, in the black box, in the blue box, the surface is very, very flat. Okay, so keep it in mind. Just a couple of questions on a couple of words about the tools. You need height estimates, again, Alexander reflection method, and the blow-up theorem. Blow-up theorem, that is, you do homotheties, you do dilation, and you get very interesting information. But why this is very flat inside the box? I mean, I will not explain why, but I will give you an idea of how it works. Look at this. That is a key fact here, in fact. If you have a small slab, and you look at the spheres inside this slab, and you take spheres that have a radius, increasing radius, that is decreasing mean curvature, then in this slab, your sphere will be flatter and flatter. Okay, this is clear from the geometrical point of view. Okay, and this is very important for this proof. The fact that there you are becoming flatter and flatter for many reasons. So keeping this in mind, let us go to the generalization of Rosa-Rosenberg result in H2 cross R. As I told you before, H2 cross R is this Thurston geometry and so on, but also, in fact, in some sense, is a toy case of a general Riemannian manifold, because it is a product space, it has non-constant sectional curvature, and but still has many symmetries. So if you remember a little bit Alexander reflection method, you need to go to do symmetries, and having symmetries is very important. You cannot do it in any Riemannian manifold. So it's a toy case in this sense. Okay, so which parts of the proof that I didn't do, but that I gave you some idea about that, do not survive here with respect to the R3 case. The first one is the blow-up part, because in H2 cross R you have no homothency, you cannot do dilation. It's a quite different space. And the second part is that when you remember that I told you that the K fact was that the sphere is very flat in a neighborhood of the North Pole when you take H very small. Here, when H is very close to the critical value that is analogous to H equals 0 in R3, then the compact rotational surfaces are not very flat. And this is a problem, because the compact rotational surfaces that are pictured here asymptotically goes, when H is going to 1/2, that is the critical value, towards the red surface. Okay, that is, and if you look at a neighborhood of 0, that's not flat. Okay, so this is a problem for our proof. We need a different kind of procedure. Let me just state the theorem that we have. I know that I have maybe a couple of minutes, or Fida, 2 minutes, or no? No one is answering to me.
Excuse me, I was muted. Yes, no problem.
Okay, so I will take just a couple of minutes. The generalization of Rosa-Rosenberg result in H2 cross R. This is the theorem, and I don't need to read it. I mean, it is completely analogous to Rosa-Rosenberg result, except that we need a further assumption of the boundary curve. As I told you, convexity is not enough, and we take it almost round and small. I will tell you in a moment what does it mean, even if it's very intuitive. But then in this case, there exists a number larger than 1/2, because as I told you, this is a critical value. And in this case, if M is a surface with that boundary and with mean curvature smaller than H of gamma, then M is topologically a disk, and it behaves very well with respect to the cylinder and so on, exactly as Ross-Rosenberg theorem. Let me tell you why 1/2 is the critical value in this space. It is just because in H2 cross R, there are no compact surfaces embedded with constant mean curvature smaller than 1/2. Okay, everything is compact and embedded. Spheres, for example, rotational, must have curvature larger than 1/2. This is just due to the sectional curvature of the space, like in the hyperbolic space. And this assumption H larger than 1/2 is very natural, and the situation for H smaller or equal than 1/2 is much easier. This was proved by myself and others some years ago. In this case, your surface is directly a graph. It's very easy. It's very easy, I don't know, but it's quite different, the situation, okay? So let me just finish by telling you the very intuitive assumption on gamma that is almost round and small. This is just the following assumption. I will show you the picture first immediately. You have to think, you take the maximum and the minimal curvature of gamma that are larger than 1 just because we are in the hyperbolic plane and we want closed curves. Then if you take these R exterior and R interior that are the radius of the circle with this K max and K mean curvature, then it's very easy to see that if you take the circle, the pink one, for example, tangent at the point of gamma, then it will be exterior to gamma. And the other one, the yellow one, is not the yellow one, sorry, gamma is the yellow curve. The blue one with the radius minimum is interior to gamma, okay? So, and then if you take the K mean and K max, not very different one from the other, then gamma is almost round. In some sense, it's contained between these two circles, and if these two circles are not very far away one from the other, gamma is almost round. And then it's small if the exterior radius is not too big. And this is a very natural assumption because of the fact your rotational surface that I showed you before is not very flat. So you need to take your gamma small enough in some sense. Okay, I'm finished. I will not talk really about generalization. I mean, I just go quickly about that. You can generalize to any other curvature function and to other space, or not constant mean curvature. But these are different level of difficulties, of course. And we have plans to do it, but they're still open question. So I finish, and I thank you very much with a picture where I like to come back soon.
Thank you, Barbara, for this fascinating presentation. Are there any questions? Yes, Jihad?
Beautiful lecture, Barbara. Thank you very much. Pedagogic as well as leading to current results. I had a question on some indications, if you have them, on the results pertaining to surfaces with cusps, okay, which are fairly common in physical contexts, perhaps more with drops. And then I was thinking, as you were going through the machinery, wondering whether curvature flows have been used to useful effect in getting results, perhaps complementary to the techniques that you have described?
So you have to think that we start with constant mean curvature surfaces. So curvature flow.
I understand that, yes. So I was imagining that you will actually evolve to these constant mean curvatures from some random looking object with suitably defined dynamics.
Yeah, if you start with any general surface and do curvature flow, and you go usually to a constant mean curvature surface, and then you can have singularities and so on. But this is a quite different subject in some sense. All those, those techniques can be used, for example, for capillarity. So if you have a constant angle, so this is a kind of drops and what you were telling about. This can be very useful because in that case, as capillary surfaces are constant mean curvature surfaces, then you can do something and apply. In some sense, if you have, for example, one of the things that I was not describing, I told that there were some partial results about this problem of understanding if a surface with boundary a circle is a spherical cap or not. So for capillary surfaces, when the angle is constant, for example, everything is proved. There are results of this kind. But the mean curvature flow is another kind of tools, another kind of subjects. It's very related, of course.
Sure. Thank you.
Other questions? I will ask you a small question. Can we, you speak of generalization of these results. Can we replace H2 by another manifold with sectional curvature negative?
Yes, of course you can try to do that, but the point is that, for example, you can replace with a manifold with negative sectional curvature, provided it has some symmetries.
Okay, and
you need
the same technique, Alexandrov reflection.
Yes, if you add enough symmetries, you can use the same technique. Okay. This is also because for example, if it depends on which kind of question are you looking at. For example, if you take a circle and you want to prove that this has the same symmetries of the circle, then you need the circle.
Okay.
And sometimes the geodesic circle has no property, no similar property to a for example, here, even in H2 cross R, if you look at constant mean curvature rotational surfaces, they're not umbilical. They're not totally umbilical. Okay. No? Because because the space is not a space forms. So they're not umbilical. So a lot of things cannot work. Okay, because you know that one of the way of proving geometers are like that. They want example and then they want to classify them. So one of the way of classifying, for example, constant mean curvature surfaces is to prove that they are compact. Is to prove, okay, there is only the sphere. And how to prove it? You prove that any is totally umbilical. Okay. Okay. So in this case, you cannot do it. So if you have M instead of H2 is words. So you have to put there different tools. As I told, in fact, is a toy case in the sense that you start to have some less properties, but you still need some. No? So you okay.
Do we still have some partial answers?
In a general manifold, no.
Thank you, Barbara. Thank you again.
Thank you to you. See you later. I stopped sharing. Okay, good.
Yes, thank you. Let's move now to our next speaker, Antonia Jabour from Université Paris-Créteil et Université Libanaise. She will be talking about sharp upper bounds on the length of the shortest geodesic on complete punctured spheres of finite area.
Yes, hello. You can see my screen?
Yes.
Okay. Okay. So first of all, thank you for the introduction, and I would like to thank the organizers for giving me this opportunity to talk in this nice conference. So in this talk, I'm going to present a work done under the supervision of my directors. It's about giving some upper bounds on the length of the shortest closed geodesic on punctured spheres. So in this presentation, I'm going just to deal with the Riemannian, complete Riemannian metric on those punctured spheres. So the plan is to give, first of all, a short introduction. Then I'll introduce two tools that I'm going to use in the proof. The first one is the Lohner's systolic inequality. And the second tool is two types of ramified cover of the sphere. Then for the main result, it is divided into two main theorems. The first one deals with spheres with 3 punctures, and the second one deals with spheres with 4 punctures and more. Then to finish, I'll give an outline of the proof and some further results. So in the introduction, let us take sigma, a non-compact surface with a complete Riemannian metric of finite area. It was proved by Thorbergson for surfaces with at least 3 ends and by Bangert for surfaces with 1 or 2 ends that the closed geodesic on sigma does exist. So by the existence, we can now introduce the length of the shortest closed geodesic on sigma, which is the infimum of length of sigma, where of gamma, where gamma is a closed geodesic of sigma. And since then, people start to prove some upper bounds over this quantity. For example, it was shown by Kroc the following inequality, but here the inequality of Kroc wasn't optimal. So Beach and Rothman have replaced this constant by some smaller constant. For example, it is 4 radical of 2 for surfaces with 1 puncture, and it is 2 radical of 2 for surfaces with at least 2 punctures. And in our work, we're going to prove similar inequality, but in the case where sigma is the punctured sphere. So to begin with the tools, we have to define the systole of M, where M is a surface with a complete Riemannian metric. So what is the systole of M? It is the shortest non-contractible loop of M. And when M is closed, the systole is attained by the length of a non-contractible closed geodesic that is called a systolic loop of M. Now, Lohner systolic inequality. So Lohner has proved this following inequality for every Riemannian metric on T2. T2 is the torus. And this inequality is sharp. So we have equality if and only if the torus is an equilateral flat torus. Okay, so if we take the equilateral flat torus, we all know that if we identify the opposite sides of this parallelogram, we obtain a torus. So this is the equilateral torus. On this equilateral torus, we have the area equal to radical of 3 over 2, and the systole is equal to 1. So if we compute here the two values, we can see clearly that there is an equality. Then for the second tool, we're going to introduce the ramified cover of the sphere. The second type, the first type of the ramified cover are the degree 3 ramified cover of the Calibric sphere. So what is the Calibric sphere? It is a sphere obtained by gluing two equilateral triangles along their boundaries. So we glue those triangles and we obtain a piecewise flat sphere with three conical singularities, x1, x2, x3. And here I have drawn two arcs just to give you an impression that there is a triangle in the back and the second one in the front. So after defining the Calibric sphere, by the theory of coverings, we can say that there exists a degree 3 cover pi 0 from T2 onto the sphere, ramified over the three vertices of S2, and there exists a deck transformation map rho 0 from T2 to T2, only fixing the ramification points of pi 0. So if you want to see this in a more geometrical way, we can take the Calibric sphere. So this is our Calibric sphere, and we cut it along the minimizing arcs, joining x1 to x2 and x1 to x3. After the cutting, we obtain a geodesic parallelogram, which is x1, x2, x1, x3, this one. Then we copy 3 copies of this parallelogram to obtain a degree 3 ramified cover. So we have 3 copies of this parallelogram. And then we can see that if we identify the opposite sides of this hexagon, we can obtain a torus. And the rotation that is centered at x3 and permuting the parallelograms, this rotation passes to Cauchy and induce the deck transformation rho 0 that gives rise to the degree 3 ramified cover of the Calibric sphere. So now we can say that the Calibric sphere can be described as the quotient of an equilateral flat torus by the deck transformation map rho 0. And this property is necessary for the extremal case that we're going to prove. So now the second type of the ramified cover is the two ramified cover over the tetrahedral sphere. So we take a tetrahedral sphere given by the tetrahedron. So it is a piecewise flat sphere with 4 singularities, x1, x2, x3, x4. Okay, and then by the theory of coverings, we can also say here that there exists a degree 2 cover pi 1 from T2 to S2, ramified over the 4 vertices of S2, and a deck transformation map rho 1 from T2 to T2, fixing the ramification point of pi 1. Now, in a geometrical way, we can see that if we take the tetrahedral sphere and we cut here along the 3 minimizing arcs, joining x1 to x2, x1 to x3, and x1 to x4, if we cut, we obtain some equilateral triangle here. Then we glue 2 copies of this triangle to obtain the whole parallelogram. Then if we do the identification of the opposite sides of this parallelogram, we obtain a torus. And the symmetry centered at x4 pass to Cauchy and give us the map rho 1 that gives rise to pi 1, which is the degree 2 ramified cover of the tetrahedral sphere. Now, also here, we can say that the tetrahedral sphere can be described as the quotient of an equilateral flat torus by the deck transformation map rho 1. Now, the main result. So the first theorem is for the three-punctured sphere with a complete Riemannian metric of finite area. So we have the impression that our surface is a sphere with three ends that go to infinity because of the complete Riemannian metric. And if we have this hypothesis, we can say that there exists a non-contractible figure 8 geodesic gamma on sigma such that we have this inequality. And this inequality is optimal. So we have a extremal metric which is modeled on the Calibric sphere. So our extremal metric is the Calibric sphere, and around the singularities we add some cusps. Okay, and for the theorem, for the second theorem, it is the one that deals with the k-punctured sphere, with k is bigger than 4. Also here we have a complete Riemannian metric of finite area. Then we can say that there exists a non-contractible closed geodesic gamma on sigma, such that we have this inequality. And this inequality is optimal when k equal to 4. Okay, and in this case, we have an extremal metric on the four-punctured sphere that is modeled here on the tetrahedral sphere by attaching 4 cusps around its singularities, around the four singularities of the tetrahedral sphere. Now, the outline of the proof. Let us begin with the case where we have the three-punctured sphere with a complete Riemannian metric of finite area. Here, it does have the three ends. So now we take 3 cylindrical ends, C1, C2, C3, that are far from the core of the surface. And then we will collapse those 3 ends into points. And after collapsing, we can obtain a sphere, S2, with a Riemannian metric that have those 3 points as singularities. So now we are on S2 with a Riemannian metric with 3 singularities. So we can use the degree 3 ramified cover pi0 that we have introduced earlier from T2 to the sphere. Okay, now we can undo T2 with the pullback Riemannian metric. So we just pull back the Riemannian metric of S2 to obtain a metric on T2. Now, since we are on T2, we can use the Lohner inequality that give us the existence of a non-contractible closed geodesic gamma on T2 with the first inequality here, this one. Then we use the fact that the degree of the ramified cover is 3, so the area of T2 is equal to 3 times the area of S2. And by computing, we can obtain this second inequality. So till now, we have proved that there exists a non-contractible closed geodesic on the torus with the inequality that we want. So to finish, we just have to project this closed geodesic gamma. So since the loop gamma does not pass through any ramification point of pi0, we can project gamma and obtain a figure 8 closed geodesic on the punctured sphere. Okay, and this includes our proof for the 3 punctured sphere. Now for the 4 punctured sphere and more, we can do a similar proof, unless here we take 4 cylindrical ends instead of 3. and we consider the degree ramified cover pi1 from T2 to S2 instead of considering the pi0. And for the shape of gamma, it may have a different shape than a figure 8 closed geodesic. It may be a simple closed geodesic on the punctured sphere. So finally, for the further results, so we have proved also similar results for complete reversible and non-reversible Finsler punctured sphere sigma of finite Holmes-Thomson area. So we have similar inequalities with different, of course, different constant. Those constants are available here in this table. For the reversible Finsler case, we have those two constants for k equal to 3 and k equal to 4. And for the non-reversible Finsler metric, we have those two here in this table. So we can see that the constant is decreasing while the number of punctures is increasing. Okay. And those constants are not optimal in all of those cases. So there is a case where the constants are optimal and else there is not. So that is all. Thank you for your attention.
Thank you, Antonia. A question for Antonia. No questions?
Actually, my question, Fida, had to do
Yes.
with Antonia's last slide. I was thinking as to the behavior of the constants as the number of puncture increases. Do you have any sense of the limiting behavior of these constants, Antonia?
Yes, in fact, we have proved an asymptotical constant that we have proved a theorem that gives us a constant that is asymptotically optimal.
Yes, that was my question. Okay.
So
This is published?
it's a frequent work.
Antonia, you said you use an extremal metric on the sphere, on your sphere.
Yes.
And what's the meaning of this? Is extremal with respect to what? Some minimizing some functional?
Yes. So here, there's extremal for the supremum of the short closed geodesic divided by the area of sigma. So because our main goal is to find a relation that's similar to this one. So it is the shortest closed geodesic divided by the, it is the shortest closed geodesic square divided by the area. So if we take the supremum of this functional, we can see that we have an extremal metric, which is modeled on the Calibric rock or on the Tetrahedral Sphere.
Okay, thank you. No other questions? Thank you again, Antonia.
Thank you.
Our next speaker is Mariam Al-Akhdar. Mariam Al-Akhdar, in fact, helped us in the organizing of this conference. She will be talking about of generalized Cauchy-Riemann equations.
Can you hear me?
Yes.
Okay, I will be sharing my file.
Yes, we can see your file.
Okay, so dear all, I'm Mariam Al-Akhdar, a PhD student under the supervision of Professor Bassam Murad at the Lebanese University and Professor Giuseppe Dalla Sala at the American University of Beirut. To start with a short background on some concepts that we used in our research, first of all, we have the holomorphic function definition of the holomorphic function in several complex variables Cn, where the coordinates will be z1 up to zn. So here we considered u to be a subset of Cn and a function f going from u to c. So we can say that f is holomorphic if del f over del zj bar is equal to 0, where j is going from 1 to n. Here it's the same as saying that f satisfies the Cauchy-Riemann equation. Moreover, we can talk about an important analogy in both one complex variable and several complex variables, which called the Cauchy Theorem. So here, if we consider D to be a subset of Cn and K a compact subset of D, such that K is equal to K1, K2, cross K2 up to cross Kn, and F is holomorphic on all of D, then the integral over the boundaries of K will be equal to 0. So here we can take K to be equal to the polydisk, for example, where P will be equal to P1 cross P2 up to cross Pn. Also, we talked about the similarities between one complex variable and several complex variables. We talked first about that also in several complex variable, as in one complex variable, the holomorphic functions are analytic. This can be concluded using the Cauchy formula of the holomorphic function. Also, it's common between one complex variable and several complex variables, this identity theorem, which says that if we have two functions, f and g, holomorphic on a connected set D, a subset of Cn, and they are equal on a subset of D, on an open subset of D, then f and g will be equal on all of D. Now, we stated some differences between one complex variable and several complex variables. For example, we have the Hardtops Theorem, which states that if we have D a subset of Cn and K a compact subset of D, such that D minus K is non-empty and connected, is a connected set, then the restriction homeomorphism taking holomorphic function on D to holomorphic functions on D minus K will be an isomorphism. So in the settings of our research, the most important geometry is called the CR geometry, and its important objects are two. First of all, we have the CR manifolds, which are submanifolds of complex spaces, for example, the real hypersurfaces in Cn. The other two are the CR functions. These are complex valued functions defined on CR manifolds. And one example of these CR functions, one important examples are the restriction of holomorphic functions. So our specific subject of study is the Borel map, which gives us the expansion or the Taylor expansion of the CR functions. So to expand more or talk more about the CR functions, we introduced the vector fields of the following form. The 0,1 vector fields L, which is equal to beta 1 z del over del z1 bar plus up to beta n z del over del zn bar. So introducing these 0,1 vector field, we can define holomorphic functions and CR functions in another way. For holomorphic function, we can say a function f going from several complex variables Cn to C is holomorphic if and only if Lf is equal to 0, where L belongs to psi 01 Cn, where psi 01 Cn is the submodule of 0,1 vector fields. A similar definition for CR functions. So if we have a CR function f going from M to C, we can say this function is CR function if and only if LF equal to 0, but here L will have an additional condition. L belongs to psi 0, 1, and L should be tangent to the manifold M where F is defined. Okay, so if we consider the manifold M, any manifold M belongs to Cn, where the coordinates will be Z1 up to Zn minus 1, and the last coordinate considered to be W, then we can find n minus 1 vector fields which spans the vector fields that are tangent to M. So they will be called x1 up to xn minus 1, and they will have the general form. For example, xj will be equal to del over del zj bar minus 2il zj bar times del over del w bar, the last coordinate. So using these vector fields that will span the vector fields that are tangent to M, we can define the CR function in another way, also using these PDEs. So we can say f from M to C is a CR function if and only if x1f is equal to 0 up to xn minus 1f equal to 0 on M. To make this more clear, we can take the Levy hypersurface as an example, the manifold M belonging to C2, where the coordinates are Z and W. So M will be equal to the imaginary part of W equal to the modulus of Z squared, or V equal to the modulus of squared, where V is the imaginary part of W. So here M belongs to C2, then M will have one vector fields that's tangent to it, will have the following form, del over del Z bar minus 2iz del over del W bar. So from this vector field, we can find the CR equation, which having the form of del over del Z bar minus 2iz del over del W bar equal to 0. So this equation is called the CR equation, which is a perturbation of the classical Cauchy-Riemann equation. And it's clear that it have C infinity solutions that are not all analytic. So that's why we can say that not all CR functions are the restriction of holomorphic functions. So from here, from this CR equation and its solutions, it makes sense to study the Taylor expansions of the CR functions, or the Borel map in another word. So this kind of problems were first studied in the papers that are mentioned at the end of the references, especially in 1 and 4, where the authors, one of the main results of the authors was proving the surjectivity of the Borel map, for example, in the Levy hypersurface. So our conjecture, or our open question is, what are the images of the Borel map? So in the stated papers and the references, they reached two cases, or they proved two cases. One of them where the Borel map is surjective, so directly the image will be all the formal power series. The other case is where the CR functions extend holomorphically to a full neighborhood of a point. Here the Borel map will not be surjective, but it will be injective, and the image will be all the convergent power series. So the question is there some intermediate cases? So that's why we go and talk about our specific model M, which is a manifold in C3. So here we took the coordinates to be Z1, Z2, and W, and our manifold will be of the following form. The imaginary part of W equal to the modulus of Z1 to the P minus Z2 Q, all of it squared. So in particular, if we take P equal to 2 and Q equal to 3, this is an example stated or mentioned in the last paper in the references, paper number 4. So for this model, for this particular case, we conjecture that the image will be of the following form. The image of the Borel map will be of the following form. Will be the series, or the sum of EK Z1 Z2 times WK, where EK is a formal power series having the following form: R0K Z1 Z2 plus theta R1K Z1 Z2 plus up to theta j, r, jk, z1, z2, plus, etc. Where theta is equal to z1 squared to with rjk z1 z2 is equal to bjk z2 plus z1 c jk z2, where these b's and c's are convergent with the common radius of convergence. So in order to prove our conjecture, we should prove two things. First of all, something related to the construction. So we should prove that this kind of series can be realized. The second thing to prove is that the Taylor series of any CR function defined on this kind of manifold M equal to the imaginary part of W equal to Z1 to the P minus Z2 to the Q squared will have this form. So for more general cases, as stated in paper 4, theorem 8.3, we can talk more, for example, for P and Q, where they are relatively prime and have
Thank you, Matt. Are there any questions to Mariam? So, Mariam, the solutions of your equations are CR manifolds?
What equations you mean? The CR equation?
Yes.
Yes, this CR equation, I said that it have solutions that not all of them are holomorphic. That's why we can talk about something related to the CR functions, but are not the restriction of holomorphic function.
Okay. Thank you.
Welcome.
Thank you, Mariam.
Welcome. Thank you. Bye.
Bye. Our last speaker in this session is Mirna Sharif from Université Côte d'Opale et Université Libanaise. She will speak about estimation of the discrete spectrum of unbounded infinite matrices. Mirna, the floor is yours.
Bonjour.
We can see, yes.
Je voudrais d'abord vous remercier de m'avoir invité à prendre la parole à cette conférence. Je m'appelle Mirna Sharif, doctorante dans l'Université libanaise et l'Université du Côte d'Opale. Le sujet de ma thèse est sur l'estimation de spectres discrets de matrices infinies non bornées. Ma thèse est dirigée par le Dr Ahmed Fino et Dr Lesh Zenleski. Je me permettra de commencer cet exposé en remontant brièvement l'origine de notre projet. Comme vous savez, tout système quantique est caractérisé par son Hamiltonien qui est l'opérateur associé à l'énergie totale du système et ses valeurs propres correspondent au niveau d'énergie. Le modèle qui nous intéresse dans ce travail, c'est le modèle de Rabi qui décrit l'interaction le plus simple et en même temps le plus important entre un atome à deux niveaux d'énergie et un champ de mode de radiation monomode. Alors, notre but dans cette thèse est d'obtenir des estimations précises de comportement de valeurs propres de cet opérateur de l'Hamiltonien. Ce problème se réduit à un problème analogue pour des matrices infinies non bornées. Dans tous les cas, il s'agit de matrices infinies non bornées qui ont un spectre discret. La matrice qui nous intéresse dans ce travail, c'est la matrice J de G qui prend la forme, cette forme, c'est écrit comme somme de D, c'est l'opérateur diagonal, D1, D2, D3, etc. Cet opérateur, nous connaissons bien ses valeurs propres, ce sont les éléments sur les diagonales. On doit étudier les perturbations de valeurs propres de cette matrice lorsqu'on ajoute un terme G, B, P, c'est l'opérateur diagonal dont les diagonales sont nues, en fonction de G qui appartiennent à elle. Comme plan de travail, on doit montrer que cette matrice c'est diagonalisé avec les valeurs propres qui sont des fonctions analytiques. On doit montrer qu'ils sont des fonctions analytiques. Et on doit donner une estimation des rayons de convergence de la série, une estimation de l'erreur de l'approximation, un algorithme de calcul de coefficients et l'expression de quelques coefficients. D'abord, pour commencer, on doit faire ces deux hypothèses. Grâce à ces deux hypothèses, on peut montrer que l'opérateur J de G et auto-adjoint borné inférieurement sont spectres discrètes. Les spectres discrètes, c'est-à-dire les valeurs propres sont à multiplicité finie et sont isolés, de points isolés. C'est pour cela qu'on suppose ces deux hypothèses. Après, dans le premier cas qu'on a étudié, on a supposé pour K fixe que DK, il est distingué de tous les éléments les autres éléments diagonaux, c'est-à-dire que DK est une valeur propre simple de l'opérateur D. On fait l'analyse de la valeur propre lambda K de la matrice J de G qui est proche de DK. Alors, on introduit BK qui est écrit cette quantité pour définir le théorème suivant. On a montré le premier théorème dans le cas pour K fixe et DK il est à distance positive de tous les éléments diagonaux et lorsqu'on a H1, H2 sont vérifiés, on a montré que le spectre de l'opérateur J de G dans l'intervalle DK qui est proche de 2K, contient lambda K, c'est la valeur propre qu'on doit chercher. On a montré encore que lambda K, il est simple, il est analytique. On a donné l'estimation de la coefficient et l'estimation de l'erreur. Comme idée de preuve de ce théorème, d'abord, on doit montrer que lambda K qu'on doit chercher, il est de multiplicité 1, car en général, la valeur propre, lorsqu'ils sont courroies, on n'a pas une régularité, c'est 1. Pour montrer que lambda K, il est de multiplicité 1, on utilise le théorème de George-Corin. Ce théorème, il assure que le spectre de l'opérateur, il est inclus dans l'union de disques. Ce disque, le disque qui est de centre de K et de rayon valeur absolue, somme de valeur absolue de l'autre élément. Par exemple, dk-1 et de rayon valeur absolue de ce terme avec ce terme. Et comme on sait, les valeurs propres qu'on doit chercher, c'est lambda K qui est proche de dk. Alors, on sait qu'il est dans le disque de centre dk et de rayon gbk-1 plus valeur absolue de gbk. Alors, si on suppose que ce disque, il est disjoint de tous les autres disques, on peut montrer que lambda K, il est de multiplicité 1. Après, on trouve un contour lambda K, un contour CK dans l'espace de résolvant de l'opérateur J qui entoure cette valeur propre et est séparé de tous les autres valeurs propres. Lorsqu'on trouve ces contours, on utilisait pour définir la formule de projecteur spectral sur l'espace propre de lambda K. Grâce à ces formules PK, on peut montrer qu'elle est une famille de fonctions holomorphes. Puisqu'on peut exprimer lambda K en fonction de cet opérateur, alors on peut montrer qu'il est une fonction holomorphe, déduire une estimation des coefficients et l'estimation de l'erreur de l'approximation en utilisant la formule de Cauchy. Après, on doit essayer de trouver un algorithme qui est à chaque pas, il donne l'erreur O de GM plus 1. Puisque le développement de Taylor il est unique, si on obtient de trouver cet algorithme, on obtient une méthode de calcul des coefficients de la série de lambda K. Alors, pour calculer les coefficients, on construit la suite G de L de G, des opérateurs unitairement équivalents. Lorsqu'on utilise les opérateurs unitairement équivalents à l'opérateur J de G, alors ils ont la même valeur propre de l'opérateur J de G. En utilisant la récurrence, on pose que J de 0 de G, c'est la matrice initiale. En prenant pi, c'est la projection sur l'espace engendré par EK. P tilde, c'est l'identité mon pi. La forme de GL de J s'écrit comme D plus GBL. GBL de G est donné par un somme direct de deux opérateurs plus RL qui est comme un reste. DL, c'est Pi, BL, Pi. AL, c'est P tilde, BL, P tilde. C'est-à-dire, si on a la matrice de la formule-là, BL, ici c'est la colonne, ici la quatrième colonne, ici la quatrième ligne. Il est clair, on peut écrire la matrice de cette forme-là comme somme directe de cette matrice. Les valeurs propres de cet opérateur qui est écrit comme somme directe, c'est DL de K union le spectre de cet opérateur. Alors, pourquoi on fait cette décomposition? Parce qu'on a la valeur propre qu'on doit chercher, c'est la valeur propre qui est proche de DK. Les valeurs propres de cet opérateur sont tout loin de la valeur propre qu'on doit chercher, parce qu'on a supposé que DK il est distingué de tous les autres éléments diagonaux. Et ici, les valeurs propres sont proches de DI qui est différent de DK. Alors, la valeur propre qu'on doit chercher, on obtient par ces termes. On obtient l'estimation de l'erreur par ce terme. Alors, si on peut faire contrôle sur cette matrice, qu'il donne, par exemple, l'algorithme numéro M, il donne OGM plus 1, on obtient le résultat. Pour faire cela, on cherche l'opérateur P de L de G qui vérifie cette égalité, que le commutateur de cet opérateur avec D donne moins RL de G. Alors, si on prend G de L plus 1, c'est l'opérateur unitairement équivalent à l'opérateur GL de G de cette forme-là, on obtient, en utilisant la formule de Taylor, on obtient ces deux formules, puisqu'on a DIGL égale RL, alors on peut débarrasser de ces deux termes, on obtient GL plus 1, une estimation. Et comme on a dit, puisque le développement de Taylor est unique, l'algorithme donne une méthode de calcul des coefficients de la série, de la valeur propre en question. Comme la deuxième cas qu'on a étudié, lorsqu'on a deux éléments diagonaux sont égaux, DK égale DK plus 1. C'est une valeur propre doublée de l'opérateur D. On doit étudier les perturbations de ces valeurs propres pour la matrice G de G. Les valeurs propres, lambda K plus 1, qui sont proches de 2K. On introduit les quantités suivantes pour définir le théorème suivant. On a montré ce théorème lorsque DK il est à distance positive de tous les autres éléments diagonaux de I pour I différent de K et K plus 1. Bien sûr, on a supposé H1, H2 pour que la matrice soit aspect discrète. Et on a montré, si on a ces conditions, la valeur propre, le spectre de l'opérateur dans cet intervalle contient seulement lambda K plus 1. Lambda K est une somme de fonctions holomorphes. On donne une estimation encore de coefficient, une estimation de l'erreur. Comme idée de preuve, puisque ici on a une valeur propre doublée, on ne peut pas utiliser comme la première cas directement les théorèmes de George-Dorin, car ces théorèmes ils donnent que le disque de centre de K et des rayons R contient les deux valeurs propres. Par cette méthode, on ne peut pas montrer que ces deux valeurs propres sont distinguées. Pour montrer cela, on utilise l'algorithme, le même algorithme qu'on a utilisé, mais maintenant, pi est la projection sur l'espace engendré par EK plus 1, au lieu de EK. Alors, en utilisant la première matrice unitairement équivalente à notre matrice G de G, on obtient que lambda K plus 1 donné par ces deux formules, alors ils sont distingués et on peut montrer que chacun de ces valeurs propres il est de multiplicité 1. Après, on suit les mêmes étapes de la première cas en remplaçant notre matrice G de G par G1 de G. Comme une application, on fait une application à le modèle de Rabi à un photon. C'est le modèle donné par l'hamiltonium H de Rabi agit dans l'espace de Hilbert complexe. L'hamiltonium donné par le somme de trois termes, un terme qui se réfère à l'atome, un deuxième terme qui se réfère à champ et un terme qui réfère à l'interaction. H atome donné par cette formule-là, sigma 3 c'est la matrice de Pauli, l'hamiltonium de champ c'est l'opérateur auto-adjoint donné par cette formule. l'interaction dans cette formule qui utilise l'opérateur de création d'annulation. On peut montrer que le spectre de l'opérateur de l'Hamiltonium s'écrit comme union de spectre de deux opérateurs, G1, G2. G1, G2 prend la forme de la matrice qu'on a définie au début, la matrice tridiagonale 1, avec des cas s'écrit K-1 plus moins 1 absence K sur 2, BK c'est racine de K. C'est-à-dire les éléments diagonales sont doublés sauf la première. La première valeur propre est distinguée de tous les autres. Alors on peut utiliser pour chercher la première valeur propre, on peut utiliser notre premier résultat, le premier théorème. Et pour les autres valeurs propres qui sont doublées, on utilise notre deuxième résultat. Et la matrice J2, il est donné par encore la matrice diagonale 1 avec des cas prend cette forme-là, alors les éléments diagonales sont doublés. On peut utiliser notre deuxième résultat, le deuxième théorème, pour trouver cette formule. Merci pour votre attention.
Thank you, Mirna. Do we have questions for Mirna from the audience? Des questions pour Mirna? Je vais poser une petite question, Mirna. L'opérateur que vous avez, dont vous parlez, exprimé par une matrice, c'est bien sur un espace de Hilbert, n'est-ce pas?
Oui, l'espace L2 de M.
C'est L2 de M, d'accord. Et donc, vous calculez les valeurs propres. Il y a certaines valeurs propres qu'on arrive à calculer explicitement, c'est ça?
Non, on ne calcule pas explicitement. On doit donner un comportement asymptotique à cette valeur propre.
D'accord. Et des estimations, des inégalités?
Des estimations, oui.
Estimations, oui. C'est simplement asymptotique?
Oui.
Ou on a, par exemple, une borne inférieure, une borne supérieure pour certaines valeurs propres?
En utilisant cette notation O de J3, c'est-à-dire qu'on peut encadrer en utilisant constante J3 et moins cette constante G3.
Oui, donc l'estimation.
Faire un encadrement.
D'accord. Par exemple, ici, c'est pour la première valeur propre, mais l'estimation, c'est en G, c'est pas en K.
Oui, c'est parce que dans ce problème, on utilise les perturbations de valeurs propres en fonction de G.
D'accord.
On cherche les séries, on cherche la série de la valeur propre en fonction de G, de petits paramètres G.
D'accord, d'accord. Et pour certains G particuliers, on a des valeurs exactes.
Valeur exacte, la valeur exacte, non, peut-être lorsqu'on prend G égale 0, les éléments diagonales sont des valeurs propres.
D'accord.
Dans la plupart des cas, on ne peut pas calculer la valeur exacte de la valeur propre.
D'accord. Other questions? Okay, thank you, Mirna. Merci. Et we will resume. We are finishing now our first session. We will resume at 12:20, not 12, at 12:20. During the break, we have breakout sessions, breakout rooms. You can join anyone to discuss, to exchange with other participants.
We have two talks. We will have two talks by Mariam Souaibi and Marwan Haris, and then we'll conclude by a keynote lecture by Barbara Nelli, Women in Mathematics, which will be moderated by my colleague Fida. So now I am pleased to introduce Mariam Souaibi from INSA Toulouse. She will be talking about computation of Lyapunov functions under state constraints using semi-definite programming hierarchies. So please, the floor is yours, Mariam.
Hello, I'm Mariam Souaibi. I'm in my third year of PhD at last in Toulouse. First of all, I would like to thank all the organizers for preparing this virtual conference, and it is a pleasure for me to participate in this event. The subject of my talk will be about the computation of Lyapunov functions under state constraints using semi-defined programming hierarchy. The supervisors of my thesis are Anil Tanwani and Didier Henrion, and both of them are Atlas. Let's begin by defining the system class related to our work, the class of constrained dynamic system for which we develop our main results are the constraint system with nonlinear vector fields defined by this differential equation, where eta allows us to capture constraints, and it is defined by this normal cone inclusion. We have that f is locally Lipschitz continuous, f of 0 is equal to 0, and s is the normal cone to s at x, and s is a closed and convex defined by the set of x such that gi is positive, where gi is continuously differentiable functions. We have also that the gradient of gi is different from 0 in some neighborhood of the set of x such that gi equals 0. The solutions evolve within the set S, and the right-hand side is discontinuous and unbounded. For just an example of constraint system, it is the complementarity system. Given F and a cone K, a complementarity system is described by this differential equation and the complementarity constraints. These complementarity constraints is the shorthand of the three statements: X belongs to K, eta belongs to the dual of K, and the transpose of X eta is equal to 0. And those three statements are also equivalent to this differential inclusion. This figure represents that during the evolution of a trajectory, if X is in the interior of K, then the normal cone is equal to 0. And the trajectory continues according to the differential equation x dot equal to f of x. And if x is at the boundary, we add a vector from the set minus nk, and the motion of the trajectory continues in tangential direction on the boundary of the constraint set. Some basic stability notions, we assume that 0 is an equilibrium point. We say that the origin is locally asymptotically stable if it is stable in the sense of Lyapunov and it is attractive. We say that the origin is globally asymptotically stable if this latter implication holds for arbitrarily large beta. And as we know, the Lyapunov functions provide a useful tool to check the stability analysis of any dynamic system. For our systems, what goes wrong if we work with simple Lyapunov functions? If we take the linear system where f is equal to ax, the simple option is to choose v, which is the Lyapunov function, of the form transpose of x px and impose conditions such that it works. This necessarily requires A to be Hurwitz, but this is a restriction because A does not need to be Hurwitz for a constraint system. What we can observe that for 0 asymptotically stable, there may not exist a positive defined Lyapunov function on the entire state space. So we have to enlarge our search for Lyapunov functions which are positive defined only on the admissible domain. This figure represents that the positive defined functions form a subclass of functions which are positive defined only on the set S. For a motivation, we give an example to show the need to enlarge our search for Lyapunov functions on the admissible domain. Let F be equal to AX, with A and S are defined like this. Here in this example, we have that the matrix A is not Hurwitz stable because it has an eigenvalue in the right half of the complex plane. So the unconstrained system is not stable. But the constraint system is globally asymptotically stable. And for the proof, we have found a Lyapunov function that you will see in our later example. So the search for Lyapunov functions for constraint system must be investigated differently from the search of Lyapunov functions for the unconstrained system. Based on this motivation, we will give it is then of interest to give the definition of constraint Lyapunov function. For our system, it has a continuously differentiable Lyapunov function V with respect to S if V satisfies these two conditions. The first one is that V is positive on S, and the second one is that V decreases along the system vector fields when X is on the interior of S and when X is on the boundary of S. In the literature, we have some contribution concerning this topic. Sufficient condition to find copositive Lyapunov function, some open question involving copositive Lyapunov functions, numerical tools based on SOS to compute the Lyapunov function, and algorithmic copositivity detection by simplicial partition. My talk will be about our paper. It builds on our research work, which is this one, where we have studied the stability analysis and computed the copositive Lyapunov function, where F is nonlinear and S is the positive orthont in Rn. Here in this paper, we have extended the ideas of our recent paper to more general constraint sets S, where we take S as the conic set and the semi-algebraic set. When addressing the question of computing the Lyapunov function, the first question is to determine the class of functions where the search should be performed. For that, we give the two assumptions. The first one is that F is homogeneous, and the second one is that S is a closed convex cone denoted by K, where C is a matrix, defined by this set where C is a matrix. In our previous work, we have showed this converse Lyapunov theorem. It says, if the origin is globally exponentially stable, then there exists an homogeneous polynomial H such that for some non-negative integer R, the function defined by this rational form is a Lyapunov function. Now we will give the inequalities that need to be satisfied for computing the Lyapunov function. We take the form of V as said in the previous theorem, where H is a homogeneous polynomial and X belongs to K. Then we compute the gradient along vector fields when X is in the interior of K and when X is on the boundary of K. Fi denote the boundary of K. And we denote by S0 of X the numerator of the gradient of V on the interior, and we denote by Si the numerator of the gradient when X is on the boundary of K. So finding the Lyapunov function V boils down to find H such that H satisfies these inequalities. And since the copositivity, which is solving these inequalities, is numerically hard, we have studied a method based on discretization. Because of the conic structure of K, we let Oj be the orthont of Rn. We define Kj by the intersection of Oj and K, Fij the intersection of Oj and Fa and Fi. Then we show that we have an equivalence between the positivity of between the copositivity of an homogeneous polynomial with respect to K and another expression. So this expression is that H is positive for all X in K with the norm of X is equal to 1. Then we introduce the simplices sigma j and sigma ij. Sigma j is a set of X in Kj with a norm of X equal 1, and sigma ij is a set of X in Fij with a norm of X is equal to 1. The task is reduced to check the inequalities on a finite number of points in each of sigma j and sigma ij. And because of this equivalence, the positivity of H is then expressed as the positivity on this simplex. So our goal is to partition the simplex and check the inequalities at the discrete points of the partition and solve for the desired solve the coefficient for the desired function H. To begin, I will give a definition of a simplicial partition. Let delta be a simplex. We say that a family of simplices sigma 1, sigma 2, del sigma n is a simplicial partition of delta if it satisfies these two properties. This figure represents an example of discretizing a simplex in the positive orthant in R2. So the inequalities that we have to solve would be checked on this orange point. And when the partition gets thinner and thinner, an inner approximation of co-positive polynomial with respect to K will be constructed. Let us now give the algorithm. As the first step, we take H, a homogeneous polynomial of degree D, and we fix R. As a second and third step, for each orthant Oj, we define Kj and Fij, and we identify the simplices sigma j and sigma ij. As a fourth step, for each simplex sigma belonging to this set, we compute a simplicial partition of sigma, denoted by delta 1, delta L bar, and we let QL be the corresponding set of vertices of delta L, which is a simplex from this set. Then, for each set of D vertices belonging to QL, which means that for each combination of D vertices belonging to QL, we solve the LP problem of the following inequalities, where we denote by big H and big Sk by the tensors form of the polynomial H and Sk. And if the LP problem is not feasible, we refine partition and we check again. And we can iterate by increasing the degree D and R. And as an end product, we obtain the homogeneous co-positive Lyapunov function. Now we deal with another set S, where GI is not necessarily linear. What is the difficulty here is that the Lyapunov inequality has to be checked for eta for all x in S, which is not feasible in general. Precedently, we checked the inequalities at finitely many points, and eta could be obtained as a solution to an optimization problem. But this works only under the conic sets. So here, to avoid the computation of eta, we will impose condition independently of eta in the following proposition. We suppose that there exists phi continuously differentiable such that it satisfies these three conditions. The first one is that V is positive. The first one is that the gradient of V, scalar, the vector field, is negative. And the third one is that if X is such that GI equals 0, then the gradient of GI, scalar, the gradient of V, is negative. So if we have a V that satisfies these three conditions, then V is a Lyapunov function and 0 is globally asymptotically stable. I will give a definition of sum of squares. A polynomial P is said to be a sum of squares if it can be written as sum of squares of other polynomials. And here in this method, why we think about SOS? Because dealing with positivity is very hard while computing. But with SOS, it's more easier because it boils down to semi-definite programming or linear matrix inequality. So the basic idea here is to find the Lyapunov function where the three positivity constraints in the following proposition can be written as sum of squares of polynomial. We focus on convex semi-algebraic sets, that is, S is compact, and the polynomial GI are and the function GI are polynomials. First, before giving the steps of our algorithm, we introduce the set of active constraints, which is defined by the set of index I such that GI equals 0. For the step of our algorithm, we let V be a polynomial of degree D. Then, for each X in S, we let the second inequality be equal to this form, where the function sigma 0 and sigma I are SOS polynomial. Then for each X in S, if the set of active constraints is empty, we let the second expression in the proposition be equal to this form, where psi 0 and psi I are also SOS polynomials. And then for each X in S, the set of active constraints is non-empty, we write the third expression as this form, where we take here two cases. The first one is when I, the index I, is not in J, which is the set of active constraints, and when I is in J. If I is in J, these functions are not necessarily SOS, and if I is not in J, these functions are SOS. And we can iterate our algorithm by increasing D, which is the degree of V. This algorithm, the feasibility of this algorithm is guaranteed by the theorem of Putinar positive Stalinsatz. It says that a polynomial which is positive on compact semi-algebraic set, we can write this polynomial as SOS polynomial. So it says that if we have S a compact semi-algebraic set and MS a quadratic model, which is Archimedean, so if we have a V positive for all S, X, and S, then V belongs to this quadratic model. As a final step, we implement our two algorithm, and we use the toolbox YALMIP in MATLAB for that. For the application of our first discretization algorithm, we consider a linear system where A and K are given by this, and we obtain this polynomial Lyapunov function, which is quadratic. For the application of our second SOS algorithm, we consider this system where F and the constraint are this, and we obtain this quadratic Lyapunov function. So as a conclusion, we have seen in this talk Lyapunov function for constraint systems, discontinuous system with nonlinear vector fields, homogeneous and rational polynomial Lyapunov function. We have seen two numerical methods. For the conic sets, we have seen the discretization technique based on linear programming, and for the semi-algebraic sets, we have seen the SOS technique based on semi-defined programming. And this talk was based on our recent work, which is published in this journal. Thank you everyone for listening to my presentation.
Thank you very much, Mariam. So we have room for one or two questions. Please raise hand if you want to ask questions, please. So I have a question, Mariam. May I ask you about the proposition where you write the equivalence between h of x non-negative, h of x larger or equal 0, and as equivalence statement. So it was at the beginning of the lecture, I guess.
This?
Yes, exactly this one. So is there anything particular about the norm you are using here? This is my question. And the second one, do you use the property of homogeneity at this place?
Yes, here we use the property of homogeneity because for the proof, we take, for example, x prime equal to x over the norm of x, and x prime, it satisfies that the norm of x of prime is equal to 1. So we replace x by x prime norm of x. So by homogeneity, the norm of x will be a norm of x square d multiplied by hx prime, and hx prime satisfies, which is positive. So and the norm of x is equal to 1, so we give this. So the homogeneity will give this equivalence, and the proof is very simple for this equivalence.
Thank you very much, Mariam. Again, so may you stop sharing screen at this moment? So now with Marwan, please may you start by sharing screen.
Yes, of course. So do you see my screen?
Yes, perfect.
Okay.
So I am pleased to introduce Marwan Haris from Rennes, University of Rennes 1. He will be talking about explicit analysis of large transformation of a T-motion co-beam. Please, the floor is yours, Marwan.
Okay, so I would like to thank you for giving me this opportunity to present part of my work in my PhD thesis entitled Explicit Analysis of Large Transformation of a T-motion co-beam. This is a joint work with Loïc Lemarec and Jean Lerbe. I will first start by giving the problem statement, then I'll solve the problem, then I'll give some physical discussion, and I'll end up my presentation with a conclusion. So what is a beam? A beam is a structural element that resists loads. Many scientists aim to study the beam, one of them Leonardo da Vinci in 1493 and Galilei in 1638. However, the first complete theory to study the beam was given by Leonhard Euler and Daniel Bernoulli in 1750, and it is about bending. It led to several applications, one of them the construction of Eiffel Tower, but it is a bounded theory because it does not include the shear deformation. So later on, Timoshenko introduced the shear deformation in a beam, and it is my main work in my PhD thesis. So what is a Timoshenko beam? We model a Timoshenko beam by a Coursera model. It means that we have a material curve C, a moving director frame D1, D2, D3, where D3 is always normal to the section and D1, D2 lies to the section. As for kinematics, we introduce a curvilinear abscissa S that belongs to 0L. We introduce the placement of C, and we have a relation between the director and the Cartesian basis defined by DI equal REI, where R is the rotation tensor. All along this presentation, I consider plane transformation. It means that we have a placement that lies in D1, D3, and a rotation around D2. We adapt the nonlinear strains. It means that we have a large transformation, so strains are given in the following form. Of course, internal forces and moments are given by N1 and N3 for shear and torsion, tension, and M2 for bending moment. We adapt linear constitutive laws. It means that the relation between stress and strain are given in a linear form, where G is the shear modulus, E is the Young modulus, A is the cross-section area, and I is the second moment of inertia. By applying the principle of linear and angular momentum, we obtain the equilibrium equations. Now, in order to compare physical quantities, we introduce the dimensionless parameters defined by the gyration radius and the bulk ratio, that is the ratio between E and G. Therefore, we can write S in dimensionless form, and also we can write the kinematical variables in a dimensionless form. We can also write the dynamical variables with respect to curvature, with respect to epsilon 1, epsilon 3, and kappa 2, and we have the dimensionless equilibrium equation. Keeping in mind that we have a moving director frame, therefore, by projecting along directors, we obtain a strain formulation. We should mention that this is a first order nonlinear differential equation with respect to strains, so we should expect 3 boundary conditions. Our aim is to solve this equation. So by looking at this equation, we can remark that since n prime is equal to 0, so n is uniform all along the beam. It is a first invariant. So we can introduce the following. Since the n is constant all along the beam, so we can introduce 3 angles. Phi hat is the special orientation of the force. Phi of S is the orientation, the material orientation of the force, and theta of S is the special orientation of dr. So since n1 and n3 are given with respect to n by the following relation, so we can rewrite n1, n3, and m2 with respect to phi. By injecting them into the equilibrium equation, we can remark that the first 2 equations are satisfied automatically, And the third equation gives a nonlinear second-order differential equation with respect to phi. So we aim to solve this equation. But first, we can look for homogeneous solutions. It means that when phi double prime is equal to 0. When phi double prime is equal to 0, we have two direct solutions. Since this condition is not satisfied, so we have, if an L is equal to 0, an elastica where placement and rotation are given in the following form, and if sine phi is equal to 0, we have pure tension or compression. So in order now to solve the non-homogeneous solution, we can multiply by phi prime and integrate this equation in order to obtain the following equation. This is a first order differential equation. We have these conditions with respect to an LML and phi L. So as a geometrical interpretation, we have a first invariant given by n, and we have a second invariant given by m2 and n3, keeping in mind that we have a relation between phi prime, phi, and m and n. So by drawing these two surfaces in the n1, n3, and n2 plane, we can remark that we have an intersection, and the intersection is a curve that corresponds to the solution of this equation. We should also remark that this is a nonlinear first order differential equation, so it has a unique solution that depends on NL, ML, and phi L. Hence, it is a Cauchy initial value problem. However, NL, phi L, and ML define the initial condition of the 3D system and define the coefficients of the ODE. Therefore, a smooth change of these variables may affect the regularity of the solution. Now, in order to solve this equation, we can make a change of variable defined by T of S is equal tangent phi over 2. So we can rewrite the equation of phi with respect to an equation of T in the following form. Here, two cases arise. If A is equal to 0, it means that we have the following equation. However, in this case, B and C are strictly negative. Therefore, non-homogeneous solution does not exist. If A is different from 0, we can decompose this polynomial with respect to A, alpha minus, and alpha plus, where A, alpha plus, and alpha minus are functions of nu and NL. Solution of this equation are well known by a Jacobian elliptic function, CS. So with zeta and m are given in the terms of alpha plus, alpha minus, and A. We can find also a 0 by giving phi L. Now, since we have T, so we can find force, moments, and rotation in the following form. But in order to find the placement, we should first give a relation given in the following form. So this relation implicates us that we can introduce an angle En and a basis En and Et. So we can represent phi in phi T and phi N, and by integration, we obtain the placement. As an example, I took a moderate beam where L is equal to 50. It's steel, so G is equal to 5 over 2, 2.5. And we consider the following Cauchy conditions, phi L and then LL and ML, and the kinematical condition, phi of 0 equals 0, theta of 0 equal to 0. This is a glued beam, this is equal to 0. And since we have the explicit solutions, so we can draw N1, N3, and M2 with respect to S. We can also draw the beam with the cross section and NL. We should mention that this result was given in a real time without hypothesis, and it may be generalized for any beam length and any material. Now, in order to see the example, we should return to the following figure. We can remark that at S is equal to L, we have two cases. So by making a quasi-static evolution, we can remark that phi L is equal to constant. It means that we have a follower load or material invariance, or we can impose phi hat is equal to constant. It means that we have a dead load and geometrical invariance. However, for these two invariances, we may obtain a boundary value problem or a Cauchy problem. We may also inspect the regularity of the solutions. So in order to reply to these questions, I first consider a pure shear load where we took a beam as the same condition before, it's glued at S is equal to 0. But here we consider ML is equal to 0, phi L is equal to pi over 2, and then L is different from 0. It means that we have a pure shear load. So by making an asymptotic analysis and by adapting the leading terms with respect to NL, we can find the placement always given in terms of Jacobian elliptic function Cn and the Jacobian epsilon function. Now, by making a casustatic increase of NL, we can obtain the following shapes. So here, this figure represents an increase of NL where the different shapes are obtained. We can also inspect for a certain shape several properties. One of them is the material period. It is the period along S, the spatial period B, and the amplitude A. We can also find a relation between B and A given in the following form. This relation is independent of material, geometry, and load intensity. Now, we aim to solve another problem. It is a pure dead load. So we have a beam. we consider NL is a pure load defined by NL with respect to EZ, and we consider ML is equal to 0, and we're letting a command theta 0 that varies. It's clear since we have condition at S is equal to L and at S equals 0, it is a boundary value problem, and we wish to compare this boundary value problem to the Cauchy initial value problem obtained before. So in order to compare it, we might ask the following question. What is the value of theta 0 with respect to phi L for prescribed dead load? Once again, since we have the explicit solutions, so we can find explicitly the relation between theta 0 and phi L. Here phi L is represented in alpha plus, alpha minus, and A. We can also draw theta 0 with respect to phi L. So here we have drawn theta 0 with respect to phi L for different values of NL. We can remark for NL small, we have a monotonic curve. It means that we have a bijection for theta 0 and phi L. However, when we increase NL, we can remark that we lose the bijection and we have an unicity of the solution. We can interpret this result in the following form. So we can let a command theta 0 that varies from 0 to 2 pi, and we can remark by reading this figure that for a small theta 0, we can remark that we have a small variation of phi L. However, at a certain value, for example here, for theta 0 is approximately 3 pi over 2, we should have a large jump in the curve in order to maintain the equilibrium path. This large jump corresponds to a brutal change of the configuration of the beam given in the following form, and this brutal change known as a catastrophe. So, as a conclusion, I studied an analytical study of a large transformation of a Timoshenko beam subjected to end force and moments with linear constitutive law and large transformation. In order to compare variables, I applied a pure dimensionless approach. We have a Cauchy problem that depends on one extremity. Solutions are given in terms of Jacobian elliptic functions, and when we adapted the physical discussion, we obtained explicit solutions for pure dead load and catastrophe for dead load. This work was published and accepted in Acta Mechanica article. Thank you.
Thank you very much, Marwan. So now it's time for questions. Please, if you would like to ask questions, raise hand and you will be unmuted. You can unmute yourself. Okay, so probably I will ask a question, Marwan. So just when you wrote the system of 3 equations, may you go back to this?
Of course.
This slide. So then,
here or I don't know. It's also here.
Probably here, yes. So okay. These are the initial equations you started with. You have 3 unknowns. So is it possible to solve this system Directly without doing the transformation you did, or?
We tried to solve the system directly, but we obtained a system that is hard to solve. So by manipulating, by deriving this and injecting it, we tried to solve the system, but we obtained a very hard system to solve. After that, we found that if we made a certain change of variable, we may also obtain a physical important discussion in terms of the variation of beam.
So is it due to the nonlinear terms, the products of epsilon 1 and epsilon 3?
Yes.
That the difficulty is there, or?
Yes, that's it. But after that, if we don't, the difficulty lies here, because we have g epsilon 3 minus 1. But if we omit this term and we also omit this term, we can obtain a direct solution of this system written by a Jacobian elliptic functions also. That's why I'm trying to extend my work into the 3D approach. So I'm concerning about the following system a little bit change, of course, and I also obtained a Jacobian elliptic functions. But here, a direct solution as a form of Jacobian elliptic functions is hard to observe. At least I didn't observe that by doing many manipulations.
Okay, so there is a question by Jihad Toma. Please, Jihad.
Sure. Thank you, Ayman. Thank you, Marwan.
Thank you.
I missed the beginning of your talk, but I had the impression following the rest of it that you had considered the possibility of including torsion, even though ultimately you simply focused on bending. Can you elaborate on that?
I didn't include torsion because I'm working in a plane condition.
Yeah, I understand, but the formalism allows for that, right?
No, because we have only bending. Torsion, it's in the direction of D3. So for a 3D problem, we might include torsion. But here we don't have a 3D torsion.
Yeah, okay. So you didn't mean to include it from the start.
No.
I had the impression that you allowed for a triad in the description. So I imagined, okay, fine. So then you solve the bending problem and you speak of a catastrophic transition towards the end. Did you actually do some work in characterizing the geometry of the catastrophe? Or is it just an observation you made?
The geometry of the catastrophe lies here. It means that for our approach, for the beam approach, we can remark that by increasing an L, beam behaves in a dramatic way. So this is the catastrophe.
I understand. So this is, you used it to describe sudden change, or do you have a more precise use of catastrophe? A more precise use would require that you study the behavior of the equilibria and the parameter space controlling the dynamics.
No, frankly, my aim was to solve the catastrophe by the difference of shape. So here we observe a catastrophe in terms of the difference of shape.
I think you can do a bit more in clarifying the evolution.
Yes, of course. We can find this by looking at this equation.
Yeah.
We have a relation, a direct relation. So we can easily implicate a certain values of an L in order to find the relation. And since we have also all the solutions in terms of Jacobian elliptic functions, so we can find directly the relation of a catastrophe. Thank you for your remark.
Okay, one last question.
Yes,
I mean, this is a beautiful subject with a long history. A very interesting behavior occurs when you allow for, sideways contacts on your beam, i.e. if you load the beam and then the beam will experience normal stresses whenever it's is in contact with the wall, a sort of singular situation.
Yes, I studied this problem, specific problem, by taking a beam subjected to a wall, to certain constraints. Yes, it is a Winkler foundation, we call it, and I studied the small deformation. But here it is a large transformation. So for large transformation, I guess it is a little bit tricky and hard to solve. The difficulty lies in the differential equation mainly.
One, and the singular nature of the boundary conditions. For sure.
Yes, exactly. So what is specifically interesting about our work is that we obtained a Cauchy initial value problem without obtaining a boundary value problem.
Yeah, I noted that. Okay.
The conditions are given only at one extremity. This is very different for all the physical problems stated before.
Yeah. Okay. Thank you very much.
Thank you.
So thank you very much, Marwan, again. So now we move to the keynote lecture by Barbara Anelli. It will be moderated by Fida. So please, Fida, you'll take my place.
Thank you, Ayman. Okay, you are back, but this time with a special session on a topic of particular interest to us, that of women in mathematics. This subject is important, especially as we have a good number of women among our young participants. When Jihad suggested this session to me, I thought of Barbara for such a mission, with several contributions on equality issues, whether through conferences or her place as a mathematician and as a member of the project Women in Math, member of the Equal Opportunity Committee of the Italian Mathematical Union, Vice President of the Italian Mathematical Union since 2018. Barbara Anelli will lead the session. Barbara, you have the floor.
Thank you very much, Fida and Jihad, for inviting me for this section. I'm here again, as Fida told before. I will share, I'm happy to talk about this subject. I will share some slides that I prepare, but I really hope that we will discuss about this subject during my talk and also later. So let me just enter the full screen mode, okay? Because I believe that it's important to have, my goal in this talk is to give you some data, and then one can discuss about that. Okay, so let me start. As usual, I have a problem with, okay. So I will start by a set of data, if you want. There is a book that is, the title is very important, is Gender Gap in Science, a Global Approach to Gender Gap in Mathematical Computing and Natural Science, how to measure it, this is very important, and then how to reduce it. But the idea is that if you want to reduce it, you have to measure in the right way. And this was an edition by Colette Guillopé and Marie-Françoise Roy that have a very important role in the European, in the group of European women in mathematics. This is a very developed group, and they really do many things. Okay. I'm sorry? No, I thought there was some question for me. Okay, so this work was done with a 3 years of research. It was funded by International Science Council and has 11 research partners. So it's really a big stuff. And the way of doing it, let me just describe a little bit. It was first a global survey among scientists. So there were 32,000 of interviews about issues related to all the important stuff about gender gap. So missing role models, feeling of critical exclusion, and so on. Then there was a study of publication patterns that is very important. That is the proportion of women as research authors and the presence of women in important journal, publishing in important journal. And then a collection of database of good practices. I will go back to that during the talk. Some of the data that I'm showing to you are taken from this book and the consequence of this book. Okay, so let me start to give you data. So I'm giving you data, first of all, about gender professorship gap in Lebanon. These are non-official data. Okay, they are just communicated me by friends in Lebanon. So you can look at the female total of professor of different level, but stable professor, and the percentage in the last column. those data are really very similar to the ones that yesterday Fatima Mroued gave in our talk. She was a little bit different. She analyzed a different kind of maybe not all the universities, but more deeply the different kind of work or job that one can have. But more or less the data are very similar. Anyway, if you look at everything, you see that even if in some places the situation is really very bad, like in the American University of Beirut, where it's 2 on 20, more or less, the overall average is 25.5 percentage of women as professors in Lebanon. If you have, of course, as I told you, they are not official data. So if someone has something to correct, you can tell it at the end, even now. But I mean, the idea is to give average data. Anyway, 25.5%. That is really a small amount. But if you look at gender publication gap, if you look at publication, the average is much less. So this is these data are taken by this project that I tell you before. It's very interesting. You have a web page and you can look at data of this kind everywhere in the world. So I looked at the last from 2006 to 2018 in Lebanon, and these were the percentage of publication authored by women in all mathematical journals, and the average of Lebanon is 8%. So you see, even if there is an average of women professor of 25%, the average of women publishing is 8%. So it's much less. I want just to compare with the other situation that I know very well. In Italy, for example, we have the situation of professorship is not very different because it's between 25 and 30, but the average of publication is corresponding to the average of professorship. So in Lebanon, I want to say that in Lebanon, the situation is hard, is difficult, really, and one should do something about that. Even if in Italy the situation is not good, and I know that it's a little bit better than in other European countries from this point of view, but it is still 30% is not a very good result. Okay, but now, so yes, this was just a resuming page. Okay, so what I was telling about the situation. The difference between professor and publication is quite hard in Lebanon. Now, let me go to a more general situation all over the world. So, in the sense that the problem is everywhere. If you look at publications authored by women in top journals, you will see that. Okay, I choose some top journal, very general top journal, not related to some subject and so on. One can choose many others, but I choose those one. And the average of women publishing is 12%. What is interesting is that also if you look at the publication of women in archive, is around 10%. So it's not very different. So this means, in some sense, that you see, as the average is the same, this means that women are able to publish in good journals. You see what I mean? Now, if they publish, they can publish in good journal because there is no a larger percentage of women publishing in archive where everyone can put a paper, but it's the same percentage more or less. So this is a very interesting fact. Is a first hint of what we will see later on. Okay, this is another very interesting information that explains what is happening in Lebanon with the women publishing or not, even if they have a position at university. This is the stop publication rate in mathematics. If you look at men, more or less the 60% of them continues publishing after 5 years after the first publication, 5 years after the first publication. On the contrary, this percentage go to 20% for women. This means that women stops publishing much more than men. So, and everyone knows why. Huh? It's not, I mean, we can discuss about that later. Now, okay, so these are general information about how to say general position and not looking necessarily to excellence. No, it's just the mean. Now let me go a little bit to look at what one calls usually excellence. That is to be a super mathematician. No? So if you look at principal investigator, for example, in Italy of national research projects, this is very big projects, Italian, the very big group. So women are only, the principal investigator women are only between 3 and 5%. This is an average in different years. So this is why we have these, or different subjects of mathematics. So it's very bad. And now let me show you something more general, that is the most important grants that you can get in Europe. I'm sorry, I'm talking about Europe and not more general stuff, because if you go to the USA or other system, this becomes a mess. So I show you something very big, because ERC projects are very important, but is restricted to people, researcher of any nationality, but that want to carry out their research in one of the 28 EU member states, okay, or associated countries. But it's very significant. Maybe all you know that there are 3 kinds of ERC funding schemes: the starting grants, consolidator grants, and advanced grants. Starting grants are for researchers very young, less than 7 years from their PhD, and they are very promising. Then there is the consolidator grants that are for researchers with over 7 and up to 20 years of experience since the PhD. And of course, they are showing again great promise. And the third one is the advanced grants that are really for exceptionally established researcher, and again of any nationality and age, and that propose a really high-risk project, and that open new perspective research and so on. They're really exceptional researcher, and that have shown not only independence but also capacity of leadership in their subject. This is also, I try to be very, to explain in a complete way this kind of grants, because this can be interesting for youngs that want to apply and doesn't know about that. Okay, so but now let us go to data. So in this table, you can see how many female submit a grant, how many female, the percentage, are funded in the 3 different schemes. And then an interesting information, the success rate of female and the success rate of, here is male, but it should be male anyway. You will accept it anyway. Okay, so very few female ask for being evaluated. But then if you look at the success rate, for example, here is 9%, 12%. So it's not very different, except then in the consolidator and advanced it is worse, and it's clear why, because women stops to publish, stops to work more often than men. This is always the same. But at the beginning, you see, the success rate of female is very good. So this means that it's very similar to the one of the man. So this means that female usually apply less, simply. Really apply less, but when they apply, they have success. So this is typical. This is typical of this kind of things. Women need more courage to apply, no? Because of many things. It's not because of them. It's because of the ambient. It's because of the role models. It's because of many things. We can discuss about that later if you want again. But this is a very interesting situation, in my opinion. Okay, then let us go to very, 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 very small numbers. If you look at the women in editorial board in top journal, you see that they are less than 7%. And that, if you look at the most important prize for mathematics, that is the Fields Medal, you have only one woman that got it. Everyone knows Mariam Mirzakhani, and she got the Fields Medal in 2014. And then, unfortunately, she left the community. But then she deserved a day only for her to celebrate her birthday. In fact, on May 12, since some years, there are many, many events all over the world, and it's really very interesting. I think that we should always remember of Mariam and her kind of work and the way she worked in mathematics. She was very interesting from this point of view as a role model, because she had a family, she came from Iran. She was really something to keep in mind, Okay, so just a couple of words, because my time is almost over. I have 2 minutes more, I think. Let me talk a little bit about COVID time for women. There are studies, scientific studies, that computed how COVID time influenced the publication of women and men. And it's clear that there was a decreasing of submission of scientific articles authored by women. On the contrary, there is an increasing of articles for men. And of course, there was an increasing of family and also academic care duties for women. Family, it's clear why, because children were at home and so on. And academics, because usually women are more generous with their time. So as the academic duties increased during this COVID time, women are than men. And these are really computed studies. So COVID was not the same for women and men, affected in different way women and men. And there is an open letter from the AWM about that also suggests good practices to fight against this situation. Then I want to show you as last page a good practice scheme. I took the one by London Mathematical Society. There is also the one from these gender gap books. They are not very different one from the other. The ideas are always the same. I will not read the details of the good practice schemes. You can imagine they are more in the idea behind this is to create equal opportunities. It's not to give some more to women, but really to be and to give equal opportunities, because this is not the case. Even if it looks that women and men has equal opportunity, is not like that for many reasons. Because if it was like that, there would be more women in mathematics, because there is, of course, there is no other problem that the opportunities and the society behind that. Okay, because we are all convinced that there is no difference of brain or think similar things. So what I want to conclude by telling that more women in mathematics is good, not especially for women or not in particular for women, but is good for mathematics because women can give a contribution, a better contribution if they are more. And for the moment, they are less, so or they have less opportunities. So all the contribution that they can give is reduced. Those are a lot of women doing very good mathematics. I'm just concluding with this wonderful slide, in my opinion. Thank you all for listening to me.
Thank you very much, Barbara. Are there any questions or comments? Maybe someone wants to speak on the subject. Can be a woman or a man, young people are also, you are concerned. Any contribution is welcome.
Also, if you wanna, I'm listening myself twice. Okay. Also, if someone to ask question about my data or to answer to some of the questions that you all received and give your personal experience, I would like very much to listen to that. I'm very interested in what you can say. It's very useful.
Yes, Fatima.
Thank you very much for this interesting contribution. Well, I would like to ask, based on the data that you propose, you showed in this presentation, and since there is a European action towards it, are there any grants supposed to help young women researchers in mathematics? Based on the data that you gave, to give more opportunity or more chance for women to contribute to the mathematical society?
Look, there is not much, but the European women, if you go to the website of European Women in Mathematics, there are, for example, there are two kinds of things. One is to put together women so that they can talk among themselves. For example, there are many congresses or satellite congresses that to big stuff. There was one also in the ICM in Rio de Janeiro. There was a first day that was only for women. And this is not, I mean, this can be something like it's a zoo for women. They will go on this day and that's it. But this is not the idea. The idea is to put them together to learn what is around and to be free of telling about their experience and to try to help themselves, to help each other. And so there are some special grants for participating to this kind of events. And there is also a tutoring idea. For example, if you go to the website of Women in Mathematics, if you are young, you can choose. There are many women that among many women, you can choose to have a tutor to ask for information and for ideas. And there are also something like research impaired grants for women. Okay, so this is
that's interesting. Yes.
That's interesting. And also, for example, it happens to me to be invited in a congress in what's the name of that? The Banff that is not in Canada, because there is one that is in Mexico. And so they organized something for women, and there were groups of women working together. And then what is also interesting is that there are prizes only for women. And this is important because it seems as usual. Those kind of things may be seen as, but it's a discrimination, okay? But it's only for women. But it isn't, because most of prizes, in fact, are men that are taking, just because of bias reasons and so on. So if there is some prize for women, this will be very good for the woman that will get it. This will go in our CV, and this will increase our possibility of getting jobs and so on. So there are similar things. There are countries in Europe that gave a position special to women, but these are very few. Most of them are in the north of Europe, some like Sweden and so on. But these are really very few, and there's also something that many persons do not like. So it's very hard in this sense.
Thank you, Fatima. Other comments?
Thank you.
No one has to want to talk a little bit about his own history in I don't know how some young that went abroad, for example, and find some different situation from Lebanon, or I don't know, some personal experience would be welcome.
Yes, Samara.
Yes, hi. Thank you for such a nice presentation. Yeah, I just want to mention that when I went to the US, I expected things to be better, but actually we are 100 graduate students, and I think we are less than 20 women in the department, maybe also less than 10. I can count them like on my hand, which I really find it really weird. I was like expecting things to be so much better here, but it's actually not at all. So yeah, I think my question is, do you think as a small society in Lebanon, is there something we can do, like us, not the institutions, but us like the students, to make the situation better now that we know also it's not actually better worldwide?
That's a very interesting point. I mean, what institution can do for making things to be better? And this is, I mean, this is in the scheme of good practices. For example, there is an important thing that we do in Europe, and we do in Italy, we do in Europe, and is also one of the main points of the ERC grant. That is, I mean, I say this and then I want to answer to because I'm not sure that if I understand correctly your question, but I have to answer. So from this point of view, a very important thing is that when you look at the CV of a woman, sometimes you see that there are interruptions due to family care, children, and so on. So in Europe, we have a system that take out of the career of a woman 1 year or 1 year and a half for each child, for example. So you are not considered discontinuous in this case. You are taking out, for example, these grants, these ERC grants, you have to be between 2 and 7 years from the PhD. For a woman that has a child, that this will be 8 years instead, 8.5 in fact. So this is important in my opinion, very important. Then there is the second answer about students. You are talking about students, and the situation is all over the world equal. So in this problem is very hard to solve, because this really depends on the society, families, and so on. One should already mathematics is already something that is a little bit far away from person. The most of person tells you, mathematics is very hard. And being hard, women are less pushed towards mathematics. So this is really a big problem. And for example, we in my university, and this happened a lot in Italy, we have a summer campus at university. We have summer campus for students of school, I don't know how to call it from college. Okay, so girls between 15 and 16 years old, they can be selected and comes to the campus and have 2 weeks in which they do mathematics, engineer projects, and so on. And this is very important. This is something that shows that they have possibilities, shows that it works. For mathematics, is a little bit different because, in fact, in Italy, for example, there are a lot of students, female students in mathematics at university. The problem comes later.
After, yeah.
Later.
Exactly.
So I mean, there are different situations following the kind of science, of course, that and something is depend on the society, and something depend on institution, and what we can do as role models also. This is very important.
Yeah, thank you so much.
You're welcome. You're welcome.
Thank you, Samara. Other comments, contributions?
What about men? Are you interested in this problem? Because that's also a point.
It was the idea of jihad. I'm sure he has something to tell.
Yeah, I know. This was a provocation.
Well, we chose to have you give a keynote lecture, and actually people may wonder why a keynote lecture in a meeting that is so broad. I felt that the purpose of the meeting is precisely to feature and celebrate the work of this young and upcoming generation, the future generation of mathematicians. And this is essentially the theme of that meeting, if you ask me. And in that context, I believe that your lecture is fundamental, because that future generation is primarily built out of women, fairly gifted, talented, and as you mentioned, generous women. And I've had really the fortune to work with such high caliber female colleagues in mathematics, whether in terms of administration or research or organizational work. My experience with FIDA speaks loudly to that invaluable resource we have in our context, and my experience with younger generations as well. So to have you give that lecture to me is precisely speaking to the essence of that meeting, which is thinking about that future generation, thinking about the hope represented in their research, their excitement that we're all feeling and actually feeding on in many respects. And at the same time, trying to think collectively about how to make sure that the percentages that you described, the alarming percentages, some more singular than others, but I took note primarily of the 8%, of the 25% to 8%. I would like to think of this as the main issue for us, at least right now, in terms of sustainability continuity. Okay, what happens when we go from 25% of representation and 8% in productivity, and how we as a society, and specifically as a center, in my position as director, I am here as a listener, trying to hear what you have to say, what our colleagues have to say at different stages in their career. You put me on the spot. I wanted to hear more from the various generations. We want to hear about diagnosis of the issue, and we want to hear about processes we can engage. It's not going to be It's not going to be very fast. The transformation is going to be slow. But having seen what happens to talent in many cases now, as a professor of physics, guiding extremely gifted women in theory and experiment at graduate levels, PhDs, I can see the pressures working on them and limiting their careers. And I am certainly willing to listen, help organize, catalyze, stimulate to make sure that we have processes in place that can, few years down the road, get us to a better place. We need success stories and we need sound recommendations on how to go, okay? I think I'll stop here and I'll put the ball back to Fida and tell her, in her position as a fantastic mathematician, geometer, mother, and leader, I think she's the one who has most to say to us on this subject at this stage from a Lebanese point of view. Thank you, Barbara, for a wonderful and very enlightening presentation. Thank you.
Thank you, Jihad. Maybe Fatima has something to say.
I just wanted to ask whether Barbara thinks that when we have, because we don't have any research positions in Lebanon. So my thought was, if we have some kind of research positions, not teaching and research or teaching alone for mathematicians, would that be a trigger for women to go into those positions, to choose those positions and do more research in the field? Because I think according to the statistics and the data that she showed, it seems like even when there are such positions like in Europe, women are not applying or are not going to such options.
Yes, this is a very interesting question. It's a much more general than women theme. Position only for research, even in the country where you have them, are very few, usually, are really very few. For example, I'm thinking about France, where there are CNRS positions, they are really very few. So I don't think that this is the real point. I don't think that women are not doing research because they have to teach. This is not the key point. Of course, they have to teach. Everyone have to teach, but the point is that they have other things to do. From the society asks them to do something else. The society and the fact that there are not much role models and so on makes that they are less competitive. For example, they feel less interested in the competition, and so they do less research. Also because the system is a system that have rules that are made by, let me tell, men, in the sense that they are, as I told, more competitive usually, and also if you are in an ambience where everyone is a man, it's a little bit strange to be there and to do the same as the others. But as for your question, I don't really think that position only for research would solve the problem, because there are few. And this is not really what counts. I mean, you can give a position only for research to some very, very special person. But in general, you need to teach. And also teaching is important for example, a good researcher teaching is a very good model for a student. So it's very important to have a very good research, a woman, very good researcher that teaches, also for this reason.
Thank you. That's a very interesting point. Thank you.
Maybe temporary positions, postdoc positions.
Of course. I'm talking there about the permanent position only for research. Of course, postdoc position, and this is very important because at the beginning you need, or at least a position. It depends also how much you have to teach. I don't know how much you have to teach in Lebanon as usually. I mean,
a lot.
Yeah, that can be a problem, of course. That can be a problem. It should be equilibrated. If you have to teach too much, it's clear that you have a problem. But you know, man as well has to teach too much. So
Yes.
So why? You know, the problem is not really there. The problem is not really there.
Yeah, exactly. So, when men teach, they still have some time for research, while when women teach, they no longer have the time for research because they need time for the family, while men do not have as much responsibilities at home. Exactly.
That's the point. I mean, it's not. It's nothing to do with the really with teaching. It's really a problem of society and family. But for example, if an institution, an university, would have a nursery in the university, this would be a difference for women inside the university with the longer, for example, with longer time, because you told me that in Lebanon there are nursery, but then at 2 o'clock they close.
No, the schools.
And good nurseries are very expensive. Excuse me.
Ah, that's an important information that I didn't have. Because if they are expensive, they close and so on. That's clear that it's not enough. And this is very important. So, for example, as Jihad was asking, what can an institution do? Open a nursery inside the university, for example.
Yes.
Or for example, very often the system of the university does not take into account the fact that women at a certain point have to come back home. So there are things happening at 6 o'clock in the afternoon, and women cannot go because they have a child, they have I don't know what, and so on. This is also taking care, giving really everyone equal opportunity means also that.
Do you see that remote teaching technologies are going to help improve on that situation, or make it worse, perhaps? It's a double-edged sword, I know, because you're home, then the responsibilities are all immediate and there for you to look after. You go to work, you also isolate and somehow manage to block things off. So I would like to hear your experience with that.
I think that it's worse because, of course, you can do more things than before because you are at home and so on, but this will not be research. This will be academic chaos, as I told before. Administration and so on, you can do more. But research, no, because for research, you need more concentration and you need to decide there is no one telling you you have to do that. So you need to decide and sitting down and so on. And if you have your family around, this is worse, of course. So I don't think that from this point of view, it's clear. You saw my data about COVID time. So yes. It's worse. For women, it's worse. It's clear that they were more affected.
Yes, it's in the culture, women, in my opinion, women tend to put the needs of their families before their own. It's in education, but I want to believe that it will improve over time. In fact, women are much more aware of their rights and fight for success. I think the big changes are starting in the way they educate their children.
You're totally right. You're totally right, Fida. It's education is very important. But it's a long way. I mean,
yeah, it's a long process. Yes.
And it is not going by itself. I mean,
sure, I agree. And what is important is above all the solutions, anything that can help now at our in this time. But before continuing, maybe Ayman and Sarah want to contribute. Ayman?
Thanks, Fida. So probably I will talk about personal some things that happened to me. I had talked with Barbara in the breakout room about this matter. I had many brilliant female students. Lastly, I had Wafa Asad. She's very brilliant. She did a wonderful PhD. She has a lot of energy, but the gender disequilibrium really left me disappointed by the fact that women are somehow forced by the society that after they finish their PhD, they have to focus again on their own work, teaching, let's say, in the case of a teacher, or other private work, on the taking care of kids and family matters, restriction on their travel. So it's kind of the society accept, they are tolerant for a woman to work at a bank or to work at a school, but they are not tolerant for a woman to close the door in her room at home and work for several hours on research, for example, because there is a particularity with research that it's not the kind of work that can be done quickly. So one has to focus for 2-3 hours, etc., and doesn't like to be interrupted. And I'm really disappointed by that, in the sense that I am losing some kind of investment. So when I have a brilliant PhD graduate, so I am looking forward to see the future projects of him or her, and to continue the investment with them by working with them and collaborating with them. And the point is that I am losing that investment at some point, which leaves me disappointed from the perspective of a PhD advisor. And I'm wondering all the time how we can somehow change the society's opinion about research. So in Lebanon, from my personal perspective, I think that research is underestimated. So people understand that, even for men, they understand that men will work very hard, for example, for whatever reason, but to work on research which doesn't have financial outcome. So it's somehow the society that doesn't understand. And I think that as senior faculty members, I think part of our role is to change this society's opinion. And I am really encouraging all my graduate and undergraduate students that a PhD is not something that we do to get a job at a high institution, high education institution. It's something that you have to continue afterwards, and it deserves a time to continue and pursue research in that direction. So just I wanted to give this short perspective. Thank you.
Thank you, Ayman. And Sarah?
Yes, thank you for that. Thank you, Barbara, for the talk. I'm here to testify, though tangentially. I'm a professor in physics. I can tell you I'm the only female in the department. But it's not that I'm going to talk from like the non-supported faculty member. I've been having a very good supportive environment in the physics department. So just to bracket this. But listening to the talks, and your talk, Barbara, and Fatima's talk yesterday, and looking at the numbers, I think what you've highlighted so far is that the problem is actually multi-layered. So there's the societal aspect, there's the institutional aspect, but there's also the, let's say, constitutive aspect, the woman's role in the family. We tend to somehow undermine that motherhood is a full-time job. Like it's really something that cannot be singled and looked at as something that is like peripheral in any sense. So in discussion with Jihad and and having listened to these to both these talks, I thought that, and also I've told Jihad about this idea of having kindergarten or some sort of nursery on campus. But then I thought, okay, women are actually pursuing their PhDs, they're in the graduate school, but this gap or this post-PhD thing, the hiring that Fatima had showed, has to do with a lot with motherhood. And I think you mentioned this year of like this 1 year or 1 year and a half taken out of the woman's career. I think if CAMS as a center wants to contribute to women in mathematics, I think women returning to math after motherhood is a good contribution to the community. Like, okay, you've raised your kids, they're somehow relatively fine on their own, and like one push could be reinforcing that representation in the math community through consideration of number of kids and like all these engagement. I mean, cannot take it as a CV with a woman with gaps. It's like completely absurd to do that. So I think one contribution camps can do is to somehow empower women coming back to mathematics after this long somehow engagement with family. And I think it's partly societal, but it's also constitutive. Like we tend to be caregivers, so it's like it's also at the individual level that the problem lies. So that's like my perspective on the matter.
Thank you, Sarah. Do you want to add something, Barbara?
Yes, I want to answer. I thought there was another intervention. You both give interesting hints because, for example, Ayman told a very interesting thing, that is research is underestimated in Lebanon, for example, and even in Italy is underestimated. This is a good occasion for women. As it is underestimated, the society is not giving a lot of importance to that. So there is a place for women entering there. Okay, as it is underestimated, there is more place. For example, in Italy, it's not only research you're underestimated. For example, to be a professor at university is not like being an engineer or a doctor and things like that, okay? So in fact, there are a lot of women that are professors at university. In mathematics also, but in general, in mathematics, there are, not bad. Then the point is to do research, of course, but already the fact that the job is not very important makes that there are more women. And this is an occasion for women. Because, for example, in France, there are less women than in Italy at university. But France is a very developed country, more developed with respect to Italy from this point of view. But there are less women. Why? Because research, culture, and so on are very important in France. So to be a professor in France is something important. So there are more men. So there is space for women for this reason. And then I wanted to answer, but it's not an answer, to comment about Sarah's observation. You're right that, it's something personal to do research and so on, but it's very, very important that women can have a family and do research in the same time. In the same time, not really, because there can be a moment where you stopped, and so this you must keep it into account. But one should show that it is possible to do both, because it's clear that if you have a choice between having a family or doing research, why? So you can say no. And also the point is that making children and so on, it's something that you have to do when you are young. You cannot do when you are 50. So it's something that you have to do here and now. And so there is a biological stuff. So you should be encouraged to do both in the same time. And you can see that there are many examples of women doing that. There are, I don't know, I think it's Claire Voisin that have something like 5 or 6 children, something like that. I mean, so it is possible. It's just a problem of society. And the fact that you mentioned that women are more generous with their time. I mean, they want to take care. No, this is something. I mean, it's. I believe that is a lot depending on the society, because, for example, all of us received dolls when we were children to play with. So dolls, you have to take care of it, while men received something completely else. I don't know, some bang stuff and so on. So really, since we are very young, we learn to take care. And so, of course, it is natural, because, I mean, we are not...
My comment, Barbara, is like there's a physical dependence of the kid on the mother that is not with the father, in a sense, like, you know, there's this attachment for some time that the kid or the, you know, there is a physical attachment that one cannot somehow turn an eye to.
I agree with this, of course, but this physical attachment can be in a certain time. If you have also, you should, I mean, for example, of course, at the beginning is like that, and one should keep into account and give women more possibility of having interruption of careers. Okay, that's of course, and that's, for example, 1 year or 1 year and a half is a good amount of time, but it's not so big, because in fact it's much more what you need. We know about that, because if you stop to do research during 1 year, really stop, then you need more time to be again inside research. So it's difficult, of course. So 1 year is something, but it's, I mean, you cannot exaggerate, of course. So 1 year is okay. 1 year and a half, it's okay. But then there are countries, for example, in Sweden, they oblige father to take parental, what's the name of that? Leave, parental leave. Okay. Then you get accustomed, and then after 1 year of parental leave of the mother, then there is the parental leave of the father, and it's very good that the father take care of the children. It's also very good we are men and women, so we can use our cultural opportunities. So we don't have to relate everything to biological stuff. There is a biological influence, of course, because the child is of the mother, of course, at the beginning. But then we change with cultural influence many things. This can be something that can be interesting to change a little bit. After 1 year that the mother take care of the child, there is the father taking care of the child. And then this will create a relation, very strict relation between the child and the father. And this is very important, in my opinion. Why not? I mean, of course, we have to, I mean, we cannot do both all the time. It's impossible. The time is, it's limited. So I'm not telling something very popular now, but it's clear then that the society must help a lot women. So it's not only on our shoulder, because we are not responsible for all the problems that women have in science, not at all. But we have to contribute a little bit to leave to men a part of our work, of family work, I mean, in my opinion. This is my opinion, only my opinion. It's not the opinion of some society and so on.
Thank you, Barbara. Other ideas? I want to add something about the solutions. For me, the schools, it's important. If we have the possibility to have schools that remain open until 4 p.m., for example, with good conditions for kids being able to eat lunch, to having breaks, this will be very important for mothers. And probably this is too much demand now under current conditions in Lebanon. But hopefully soon, this type of question can be asked. for me, it's the first point in Lebanon. At the level, at the national level, maybe if we create committees to study equality issues, that will be important.
I completely agree with you, Fida. You mentioned two very important things, really important things.
Something to conclude? Any other ideas?
Well, I listened and I took a lot of notes, and one way to dismiss something in conclusion is to say we will have a committee that will look into this. I will not say that. I will say that we will be reaching out to many of the participants in this meeting and try to solicit suggestions on moving forward, specific suggestions, keeping in mind the questions that Barbara shared and the conversations we've had the first day, today, and I'm sure we will continue having. I will certainly also be considering earmarked and dedicated resources with women in mind, and we will try to explore what are sound options with the experience of colleagues such as yourselves to try to articulate something that would be effective, meaningful, and sustainable. Okay. Finally, I also want to leave the young audience with a sense of hope and possibilities. We are meeting and we are discussing, and I think their contributions to this discussion, as well as their contribution to the sustainability of mathematics in Lebanon, will be essential to push the whole atmosphere around the subject in directions which would actually, I believe, make for opportunities for them as well. So their role is going to be essential, and we look forward to hearing from them and having them stay in this conversation. Mentoring this critical stage in their career is, of course, essential, and they have some very interesting people represented in the meeting who can engage with them on this matter. But we're all learning, and we will all be engaged in trying to better diagnose and better identify solutions.
Thank you, Jihad. Thank you, Barbara, for this day.
Thank you to you for inviting me and for organizing such a session. This is very important, I agree.
You are welcome. Thank you. It's time to take our lunch break. We will resume at 3 p.m.
Bye-bye. Thank you. Bye.
Excellent. Thank you, everyone. Thank you.
Everybody, and welcome again to the third session of the day. I'm very glad to announce the first speaker of the session, who's from our own mathematics department at AUB, Nabil Nassif. Thank you very much for agreeing to give a talk. And he's going to talk about the Poisson brackets in the Hasegawa-Mima plasma equation.
Thank you, Giuseppe. So thank you for the organizers, all of them. I think I'm glad that this conference is a result of a collaboration between CAMS and the Lebanese Society for the Mathematical Sciences. This is a very nice happening. Also, I want to thank each of the organizers that really have put a lot of effort to get the program well tight and well followed up. So I'm going to speak about some work that we have been doing recently on the Hasegawa-Mima plasma equation, and this is a joint work with Hagop Kalagazian, who is a PhD candidate, and Sophie Mfawad, who is a colleague in the math department. This is a junior colleague in the math department. So I will start by talking about the mathematical model. The mathematical model is essentially something that that is based on the usual what people who are used to Navier-Stokes. Then we have a continuity equation, momentum balance equation, then simplifications, and then rescaling the variables. And then you fall on a model which is of this form, which is essentially, we have it's a third order differential equation because you have the minus Laplacian of ut. And then we have this Poisson bracket here, which is a Poisson bracket between u and the Laplacian of u. Laplacian of u, so now, of course, the Poisson bracket is given by this formula here. It is uv, which is ux vy minus ui vx. Plus pu here, and pu also this is a Poisson bracket, but this p is a given function, which depends essentially on the initial magnetic field of the in the plasma that is governing the plasma. So this is really a simplified system, a simplified model, which has been devised by Hasegawa and Mima in 1978. So if you want to look into this model, then we have to seek a function u, which is defined on a domain, on the closed domain omega bar cross 0 t to r. So it's a time-dependent problem which satisfies this system here. And of course, we usually have an initial condition at t equal to 0. And of course, we have also a boundary condition that are satisfied on the boundary of omega. So this is, we're going to restrict ourselves to 2D turbulent system that describe time evolution of drift waves during plasma confinement. So as far as the thread of this research, maybe I should mention here that this started in 2009 with it was a collaboration with Professor Ghassan Antar in the physics department, who proposed the problem as part of a master thesis in the computational science program at the time. This was the second master thesis in the computational science program. Then it was a second master thesis in math by Hagob Karakazian in 2016. Then another one in 2017 by Dana Malouf. It's in applied mathematics. And since 2018, we have been working, the three of us, Hagob, Sophie, and myself, on several aspects of the problem, which are computational and theoretical. So there is a lot of things inside the problem, and they are all centered around the how to handle the Poisson bracket. This is why the title of my talk has been handling the Poisson bracket. So I'll explain that. So if you take now if I take this Cauchy problem, that is to say, if we work on an infinite domain in R2. Then you seek a function u, whereby here you don't have boundary conditions. You have, of course, you have to restrict the solution u to belong to some space. And then you have this system here. So here I took the function p to be only a function of x without loss in generality, and this has been considered actually in 2004. By two authors, one Pomot in France in his PhD thesis, and another one by Japanese researchers. And what we obtain essentially, we obtain the following: that we have if you take an initial condition which is in HM of R2. M greater or equal than 4, so you have to be very restrictive about the initial condition here, that you need to have so much regularity. Then you can get your solution u to remain in HM, and then L infinity of 0 t HM, and then continues in from 0 t to H1 of R2. And the derivative also has certain property. It is C of 0 t L2 of R2. So, but we have to really to be very restrictive about the initial condition. So the other thing is that we have existence, the existence space, and then we have uniqueness. So we, in one case, for example, for m greater or equal than 4, then we have uniqueness. But again, if I have m if m is equal to 2, then if u0 is in H2, then the question about uniqueness is open. Okay, it's still an open question. But we have a solution which is L infinity of 0 TH2, and UT is in L infinity of in R2. So now what we are interested in is a model where the plasma is confined in a rectangular domain, which we take to be 0L or 0L or whatever square, with periodic boundary condition. That is to say, what you assume is that you have the Hasegawa-Mima equation, so which is the usual one, and then we have periodic boundary conditions on u and ux and ui on the boundary. That is to say, since you have a square, then you will have periodicity of the function u. So if you on these two faces, and then these two faces periodicity, and of course also periodicity of ux and uy on the boundary. So and of course we have an initial condition here, which is u0 of xy. Now, this problem is, I think this is how the first work was done. It was done basically on that problem, and there were difficulty here to handle the Poisson bracket either theoretically or computationally. That is to say, it's one of the features that to prove existence. For example, you have to take I minus delta, invert it, and then use semi-group theory, and then try to work out on finding estimates, which is not an obvious procedure. Now, it's worse even for the computational part. Okay, so to discretize this term is one of the most important difficulties. So this is why we looked into tried to find another way, another approach, and that approach is really to consider if we can make to change the system into a coupled system. So if, of course, if we introduce the variable w, which is minus Laplacian of u plus u, then we can, by doing simple algebra here, then we get the following. We get that the Hasegawa-Mima equation becomes a transport equation. We have Wt plus v of u dot Laplacian of gradient nabla of w equal to v of p nabla u. So again, here this is the nonlinear term, and this is the linear one, and where v of u is defined by minus ui. It has a component minus ui and ux, and of course v of u will become a vector field which is divergence free. So div of v of u is equal to 0. This is a property that is used a lot in the proofs that we have. So then this is the coupled system. So of course now when you write the problem as a coupled system, so it's a Hasegawa-Mima coupled. So then you have a transport equation here, and then you have which is a hyperbolic system, and then you have given a w, then you have an elliptic equation. So you can see that this elliptic equation is a very nice. It has a nice sign here. So it takes w, for example, if the regularity of w is in hm, then this way u will be in hm plus 2. But this one here, the hyperbolic one, then this will keep the regularity of the initial condition, which is whatever it is. So then you will have a problem, which is a coupled system. So you have to seek down here a pair uw from 0t cross w bar to R2. Then you have the system of equations, periodic boundary conditions on u, ux, uy, and w, and then u of 0 equal to u0, and w of 0, we take it to be minus Laplacian of u0 plus u0. So this is then the, so of course now we have to adapt, so we have to define appropriate Sobolev spaces, and these are, we call them periodic Sobolev spaces. So the periodic Sobolev spaces are what? They are spaces, so if you take, for example, h1p of omega, So H1P of omega, then the traces of the functions are well defined. The trace of the function which are in H1, they are well defined. So H1P here, then this will be the functions which are in H1, and then they are periodic on delta omega. So this is possible to define. So of course, then you can generalize to H2P to whichever. But I think what we mostly use here in this in our work is the H1P periodic Sobolev space. So now then, the problem that we set. So if we do a variational formulation of the coupled system, then you come into something like this to seek U in this intersection of spaces, C1 with respect to time, and then C1 with respect to time, and then C with respect C1 with respect to time, and then with the images in H2 of omega. Intersect H1P of omega, and then this is intersect. It is continuous at 0t H2 of omega intersect H1P of omega, and then the W here is in C10 t L2 of omega, and then intersect C of 0t H1P. So you see in this formulation here, then we require W to be in H1. That is to say, you see in this formulation, I put it in red here. The W has to be in H1. So of course, it would be nice if, for example, we don't restrict W to be not to be in H1. And this is possible because of this property of the divergence free of V of U. So what we can do is to prove that V of U nabla W of T V is equal to minus V of U nabla V W of T. So you can see that then you kick out the gradient here, and then you get the function W of T, and then you'll have a variational formulation. And this variational formulation is essentially given by the following, that it is, so we have here the test functions will be in H1P, but then the UW, the pair U and W will be, will have to be in, so I'll put it's here. So now this one here. So we have to seek here U that will be it will be in the same spaces as before here, but I don't need for W to have this H1P here. It will be only W in C1 of 0TL2. Okay, that's all I would need. I would not need this part here. And of course, when I would write this here, then automatically I would ask, I would like also, this is what I would like also to get rid of the derivative with respect to time, because for computational purpose. So if you take an integral formulation by integrating from 0 to t, then you get that system here, which is an integral formulation, which is a formulation that we use for basically to prove existence, and also to discretize, to find numerical solutions. Okay, so then this is what we're having. Then we have to find a pair UW that satisfy this problem. Okay, with again here, this is the part which is the hyperbolic part, which is now written as an integral equation. And the elliptic part remains as is. So of course, now this formulation, if you want to take it only, you want to integrate over locally, then you go from t to t plus tau, and this will be very good if you want to do discretization with respect to time. So that's another the other formulation which is adapted to numerical discretization. So now what we're going to do is the following. We're going to consider this problem here, this problem as is, and now we're going to have a discretization of both equations by finite element. That is to say, we call it semi-discretization. That is, we keep the time continuous and we discretize with respect to the H1P. That is to say, we consider then we take a mesh over this unit, not this square here, and of course we take a conformal triangulation over this domain, and then we can define here. So we can define functions, we can define the space xn, which is a function which are continuous, and then which are on every triangle they are p1. And then this is a Lagrangian basis, so that that is to say the value at the nodes constitute the element of the vector. And this has very nice approximation property, which are very important, that we have for all v. For example, in W1P, we have this convergence property, and this is the semi-norm here. So the semi-discrete system, when you discretize, then just you have this semi-discrete system, which is on the coupled system here. So in other words, everything like before, but except now that the V are belonging to X and P, and the Wn, and they are functions that are defined on the function that are in X and P. And then this, of course, is going to be translated into a system which is first order differential equation in W, where here we have matrices and R matrices R and A, and then A with being K inverse M. And then you can see that you have a system here, and then of course you can apply the theory of ordinary differential equation on a finite dimensional spaces. So of course you can prove here existence and uniqueness without much difficulty. Now, the interesting thing here is to go to the limit. In other words, what you want is really to see whether you can go to the limit. That is to say, you have then so this is a discrete system. Now I want to know whether, if when n goes to infinity, whether I can get a solution to the continuous problem. So this is something that we do. This is the theorem here, which is. So if I assume that U0 is in H2 intersect H1, and then W0 is in L2, then we have these a priori estimates here, and these a priori estimates, which depends on capital T here, and on the initial conditions. Then for all T positive, the unique solution of the discrete system then admits a subsequence that weakly converge to a solution to the to this problem, which is, that is to say, the Hasegawa-Mima integral formulation of the problem. So you can see here we get a solution which is quite, the regularity is quite weak, and in other words, we don't really have to impose anything on the initial condition that is more than needed. So U0 is only has to be in U0 is in H2 U0 is in H2 intersect H1P. That is, you assume that U0 has the periodicity conditions. Okay, so now if we want to go to the full discretization, then we have so we take this formulation here, which is, and then we discretize. So we discretize this. So when we discretize this, then we take this integral from T to T plus tau, and we replace it by some using an implicit right rectangular rule, so which is equivalent to the Euler implicit implicit formula. And then we get this, when we go into, so we have to seek, given un of t, wn of t, which is in x and p, cross x and p, then you have to move the solution, you have to move the wave to t plus tau, and this has to satisfy this nonlinear system. So this nonlinear system, and so you get, so in matrix notation, so this becomes like this. So in other words, the matrix, we have the matrix M, which is the mass matrix, and then we have a stiffness matrix, which is the finite element, and then we have the nasty term here, which is S of U here. This is the term that comes from the Poisson bracket, and that is related to the term which is this one here, that one. Okay, so what we show is that the discrete system has a unique solution. We can prove this, but we prove it for tau has to be less than, has to be restricted by this condition. So in that case, that system here has a unique solution, And this matrix B here is invertible. And of course, then to prove this, we used the Leray-Schauder fixed point theorem. Now, what we have, the uniqueness is also obtained by using the property that that if we have two solutions in this ball, then we get this very nice Lipschitz condition, and this will allow us to obtain uniqueness of the fully discrete system. We don't have yet proofs about the convergence to the solution of the continuous problem. So now if I come to the algorithm and the computer simulation, so given then U of t, W of t, then you have to go into U of t plus tau, W of t plus tau. You have to satisfy this. So you see here, you have this nonlinear equation because you have here on the left-hand side U of t plus tau. And then you have K U of S, the MW of S equal to the MW of S for S equal to T plus tau. So this is when you put it in, if you take the semilinear approach, that is to say you replace S of U of t plus tau by S of U of t, this is the simplest thing to do, but of course there are other ways to do it. And then we get these systems, and all the matrices here are sparse, and they have essentially the same block sparsity. So okay. So the matrices, these are the matrices. So this is the mass matrix. K is a summation of the mass matrix and the stiffness matrix. S is this term here, which includes V of U. So this is the term that has to be always updated. And R is the linear term, which depends on P. Okay, so this is the algorithm. So this is the algorithm, which is essentially the algorithm for the space finite element time Euler implicit, which is this one there. And then we have implemented it in free FM++. So this is let me show you some simulation. So this is a simulation here where you take the initial U0 is to be of this form. And then P, the function P has a gradient P with respect to X and the gradient P with respect to Y. And the solution is a traveling circular wave centered at the center of the square and drifting in the direction perpendicular to nabla P. So these things are things that we observe them, and the physicists were happy about them, that this is exactly what they wanted to see. So this is this is then the one of the condition U0. So I think, okay. So now this is another example. This is another example where you have here the initial condition is a U0 is a sine wave in the Y direction. So it turned out that this U0 is a traveling wave. So that is, this U0 gives a traveling wave which is in the Y direction. Why? Because here we have nabla P is 12, 0. So then it has to go in the traveling wave has to go in the direction which is perpendicular to nabla P, and then it will be in the Y direction. So you can see here that this is moving in the Y direction. So if I take now this last case here, so this is here a case where you take the initial condition, which is a sine wave in the X direction, but now what you're going to see is that this sine wave in the X direction is going now to, at one point, is going to switch. Now here it will switch and it becomes a sine wave in the Y direction. Okay, so this is the so that's. Okay, so I think then this is what I have to say. Then now as conclusion, so then I think at this point we dispose of mathematical and computational tools to handle Poisson's bracket that appear in plasma physics modeling. So there are issues which you have to find, which is studying the traveling waves like the modern, proving the convergence of the semilinear implicit when tau goes to 0, using a Newton scheme to solve the nonlinear implicit. This is now a master thesis on which is going. And of course, we can move to an upgraded plasma model by taking the Hasegawa-Wakatani model, which is a more complex model, which I wrote here. So I think this is all I had to communicate to you in the little time that was given to me. So I stop here. Thank you.
Thank you very much, Nabil, for the talk. Thank you so much. The floor is open for questions, so you can unmute yourself and ask a question, or you can raise your hands through Zoom. Yes, please. I think Tony was first.
Hello.
Hello, Tony.
Thank you. Hello, Nabil. Just one question, please. I think you show the existence of the solution and the uniqueness of the solution.
No, I didn't. We did not show
a global solution in time.
No, we showed only the uniqueness of the discrete solution. But we did not show the uniqueness of the solution, and that is this theorem. Let me show you. Excuse me. So, yeah, we showed the theorem.
At the beginning, when you discretize only in space. No. At the beginning,
in space there is
when
no
you
problem.
discretize only in space.
In space, you have unique solution
Yes.
of the discrete system. No problem.
Yes.
Because
and later you show the later you show the existence of the solution when tau is smaller than some condition.
Yeah, this condition.
Yes.
We have to be able to invert this matrix B here.
Yes.
So invert this matrix B
here
you need to have the coercivity of this bilinear form.
Okay.
So you need to have this condition. So you cannot, or maybe you can by other ways, but this is what was
a condition on the time step.
Yeah.
A condition on the time step. No.
This is a condition on the time step.
A condition on the time step.
Yeah.
Yes. Yeah. Yes. To have the existence of the numerical solution.
The numerical solution. This.
Yes, but you don't have if you have tau smaller than this kind of this quantity, you have the existence and uniqueness of the numerical solution.
So the uniqueness, we get it if we have.
Oh yes, tau smaller than another condition. Okay, you take the minimum of them.
Just like the CFL here.
You have H here. Excuse me.
Yeah,
okay.
H.
Okay. You have a condition with H with the
mesh step. If you're using an implicit scheme and then you want to match the.
Oh yes, clear. Okay. Thank you, Nabil. Very interesting.
Okay, I think there is another question.
Yes.
Yes, it's a little bit intuitive. I want to know the connection between the matrix M and the frequency space. Are they related?
The matrix M is a simple mass matrix. The matrix M, excuse me, the matrix M. No, it's not linked to the matrix M. This is the matrix M. Just the L2 inner product, and you restrict it on the phi I phi j are the basis of the finite element space. It's a very normal block matrix, which comes from the discretization of the L2 inner product.
Okay.
It has nothing to do.
Then how do you relate your frequency to the traveling modes?
The frequency will have to be here, in the P, in the P here.
Okay.
So I'll tell you something. We focused mostly on the math. We were lucky to have Professor Antar, who comes. We consulted with him on all the results. He gave us a bank of tests that we have tried. And I think, I think we can do more tests. But there is definitely, if we tied up the physics and the math, I think we can understand the problem much better.
Okay.
All right. Let me also point out that, of course, you can continue asking questions and continue the conversation also later when we are in the breaking rooms, and also if you desire to write any questions in chat. Okay, so I would like to thank
Giuseppe, excuse me.
Yes, please.
I would like to ask you, how do they get to these meeting rooms? Are they links?
At the end of the session. At the end of the session, I think everybody is invited to join one of the breaking room. That's my understanding of how it works.
Okay.
All right. So thank you very much once again, Nabil. I would like, if you can unshare your screen, I think that I would like to invite Hanin Al-Jabawi to share the screen, please.
Okay.
Once again.
Okay, is this okay for you?
Yes, it seems to work. I don't know if you can try to make it full screen.
Yes, I will try for sure. Okay, now it's okay.
All right, it seems to work. So the next talk will be given by Hanin Al-Jabawi, who I'm assuming is in co-tutel between the University of Compiègne and the Lebanese University here. And she's going to talk about thermoacoustic and photoacoustic imaging of small absorbers.
Okay, thank you. First of all, I am Hanin Al-Jabawi, a postdoctoral researcher at the University of Technology of Compiègne. Today I'm going to present for you my work on thermoacoustic and photoacoustic imaging of small absorbers. This actually was a part of my work during my PhD thesis that was done under joint supervision between the Lebanese University and the University of Technology of Compiègne. Actually, the main part of this of my thesis was on inverse problems for wave equations and their application to medical imaging, more precisely to thermoacoustic and photoacoustic imaging. So a good thing to start with is the definition of inverse problems. So what is an inverse problem? In fact, an inverse problem is a mapping between certain unknown physical parameters and the acquired information about these parameters. So from its name, unlike the direct problem that usually try to calculate the observable effects of a certain physical model, the main goal of an inverse problem is to reconstruct some unknown physical parameters in the physical model from the measurements or the observations that usually provide us by limited information about this unknown. Even though the mathematical study of inverse problems has recently developed, however, inverse problems are as old as science, and the applications of inverse problems can be viewed in our everyday life. Inverse problems actually started, we can say, by the experiment given by the Greek philosopher Plato. In his experiment, Plato's allegory of the cave. In his experiment, Plato had a group of people chained all their lives facing the wall of a cave. And all what they were allowed to see were the shadows, or the two-dimensional shadows of some objects that passed in front of a fire behind them. So these people had to reconstruct the outside reality, or the 3D shapes from the 2D shadows that they viewed on the wall. This is a very old example on inverse problems, and it shows how difficult it is to deal with such a problem, because it's difficult to reconstruct a 3D object from its 2D shadow. For example, two different objects can have the same shadow, so the reconstruction is not unique, and we cannot obtain a unique solution for such inverse problem. Inverse problems nowadays can be applied in different domains, starting from astronomy, geology, oceanography, medical imaging. And one of the main applications that we work on in our thesis is the application to medical imaging, in particular to photoacoustic and thermoacoustic imaging techniques. So medical imaging actually is a continuously developing domain whose aim is to image some body organs for some diagnostic purpose. These techniques can be divided into structural imaging techniques that try to observe only the organ, such as the X-ray based techniques, or functional techniques that try to observe the organ and its functioning, such as the magnetic resonance imaging. Also, scientists are always trying to improve these techniques in order to get cheaper, faster, harmless, and highly resolved results. For this purpose, they developed what's known by the multi-wave imaging techniques. And one of the most important techniques in this domain is the photoacoustic tomography or the thermoacoustic tomography. It is a multi-wave imaging techniques that combines between optical waves and sound waves or acoustic waves. In photoacoustic tomography, the object is illuminated by an optical pulse. Then some of the energy is absorbed by the underlying medium, and the object eliminates or produces some acoustic waves. These waves propagate and they are measured by some transducers located at the boundary of the object, and the image is produced. So first of all, we send an optical wave into the medium to be imaged. Then some of the delivered energy is absorbed by the underlying medium, which causes heating up of the absorbers, and then thermal expansion of the tissue. This leads to the generation of acoustic waves, and this is known as the photoacoustic effect. It is the generation of sound from light, or the generation of acoustic waves from previously absorbed optical energy. These waves then propagate until they reach the boundary of the imaged object, where they are measured and the image is produced. Now, the main difference between photoacoustic tomography and thermoacoustic tomography is in the type of the optical pulse used. In photoacoustic tomography, a high-frequency radiation is delivered into the biological tissue to be imaged, while in thermoacoustic tomography, low-frequency radiations are used, such as radio waves or microwaves, for example. Now, the high-frequency radiations used in photoacoustic tomography are characterized by a wavelength that corresponds to the absorption spectrum of hemoglobin, which is an interesting absorbing molecule. In fact, in our body, there are certain molecules that are responsible for energy absorption, such as hemoglobin and melanin. And from a medical point of view, tumors are highly vascularized. They are highly rich in hemoglobin, which enhance the energy absorption in such tissues and makes a very large difference in energy absorption between healthy tissues and cancerous ones, which makes photoacoustic tomography an effective method in detecting tumors. However, these high-frequency radiations are also characterized by their diffusive property, which allows low penetration of light and decreases the image depth. On the other side, high-frequency radiations used are characterized by their very high speed compared to the speed of propagation of acoustic waves. And they are known to satisfy the stress confinement condition. That is, one may assume that the absorption is done, one may neglect the duration of the absorption of the electromagnetic wave, and we may assume that the production of the acoustic waves is done initially. And under this condition, actually, we were able to solve our problem in a more general case. More precisely, we were able to give our results in a case of partial boundary observations. That is, there is no need to measure the acoustic pressure on the whole boundary of the imaged object. It's enough to get the measurements on part of the boundary. Also, we were able to solve the problem in case of variable acoustic speed. Now, for the thermoacoustic tomography problem, even though the low-frequency radiations used do not have the wavelength that corresponds to the absorption spectrum of hemoglobin, however, from a medical point of view, tumors have very different electrical properties than healthy tissues, which results in a large difference in conductivity between healthy tissues and cancerous ones. And different experiments on liver cells, for example, or on breast cancer, have shown that at low frequency radiations, which is the case of thermoacoustic tomography, a very large difference in conductivity is detected between healthy tissues and cancerous ones, which also makes thermoacoustic tomography an effective method in detecting tumors. Moreover, the low frequency radiations used in this case do not undergo much diffusion, such as the high frequency radiations, and this allows a deeper penetration of light and it increases the image depth. However, on the other side, the low frequency radiations do not satisfy the stress confinement condition, which obliges us to give our results or to apply our algorithm in case of total boundary observations and in case of constant acoustic speed. In fact, we have worked on both problems, but due to lack of time, I will just mention my work on thermoacoustic tomography problem. This work actually was published in a journal, in the Journal of Inverse Problems. It was done in collaboration with my thesis supervisor, Abdulatif Libati. So, as I've previously said, in thermoacoustic tomography, a low frequency radiation is delivered into the tissue to be imaged. This radiation is described by the light fluence U that satisfies the following wave equation, where C is the light speed, sigma is the conductivity that we are interested in reconstructing, alpha is the permeability, and W is the value of the optical pulse applied at the boundary of the imaged object. As we have said, the sum of this energy is absorbed by the underlying medium, and it's given by H equal to sigma U squared. Now, due to the photoacoustic effect, this energy absorption causes the generation of some acoustic waves that are described by the acoustic pressure P, which is known to satisfy the following wave equation, where Cs is the acoustic speed assumed to be constant and known. Beta is the Green-Sinn coefficient. It is a unitless coefficient that measures the efficiency of conversion from optical waves into acoustic waves. H is the absorbed energy, and then this acoustic wave propagates inside the imaged object until it reaches the boundary, and the measurement is given at the boundary by P is equal to F. Now, the inverse problem we are interested in is to reconstruct the conductivity coefficient from the measurement of the acoustic pressure at the boundary. In fact, this problem was highly considered in literature, and different approaches were used for solving it. One of the main approaches used is the quantitative thermoacoustic tomography approach. The main goal of this approach is to divide the problem into two inversion problems, the acoustic inversion and the optical inversion. So first of all, in the acoustic inversion, we need to invert the wave equation, this one, in order to reconstruct the absorbed energy H, or the source term, from the measurement of the acoustic pressure at the boundary. Then the next step is the optical inversion, whose goal is to reconstruct the conductivity coefficient from the previously calculated H using the relation H is equal to sigma U squared and the wave equation satisfied by U. In fact, this approach actually involves many difficulties, starting first by the non-absorbing background medium. So most work done on quantitative thermoacoustic tomography assumes that the healthy tissues or the background medium is non-absorbing. So they neglect the absorption by healthy tissues, which is not accurately true. The second one is the limited boundary observations. So most work done requires the total boundary measurements, which is not always available. So we may not always be able to measure the acoustic pressure on the whole boundary of the imaged object. Also, the spatially varying Green-Sinn coefficient. So most work done assumes that beta is constant, and it's equal, usually it's taken to be equal to 1. However, beta is a physical property and it varies between different types of tissues. So this assumption is not accurately true. And finally, the main difficulty is the nonlinear dependence of U, the light fluence, on the conductivity coefficient. So even here, if we know H, the reconstruction of sigma from H equals sigma U squared is not easy because U itself, it satisfies a wave equation that depends on sigma. So U also depends on sigma. Now, in our approach, we do not follow the quantitative thermoacoustic tomography approach. However, we first assume that the conductivity sigma is defined piecewisely. That is, sigma is equal to sigma 0 in the background medium, and it's equal to sigma j in each absorber omega j, where omega j represents the tumors. So we have omega j are of centers Sj and diameter epsilon. Now, due to the large difference in conductivity between healthy tissues and cancerous ones, we may assume that sigma 0, which is the conductivity in the healthy tissues or in the background medium, it's equal to O epsilon kappa for some kappa that we choose to be greater than 4. Now we follow or we provide a direct reconstruction algorithm based on the algebraic algorithm that was first developed by Al-Badia and Dong in 2000. This actually considers in developing some algebraic relation based on the idea of the reciprocity gap functional and Green's formula. So the main idea of this algorithm is to project the problem into well-chosen test functions, and then to reconstruct the unknowns from the boundary data. So first we reconstruct some Hankel matrix H from the boundary observations. Then the number of the observers can be reconstructed as the rank of this matrix, while the locations of the sources or the centers are the eigenvalues of some companion matrix that can also be built using the boundary measurements. So as we have said, we take V to be a solution of the following wave equation, a test function. Then multiplying the wave equation satisfied by the pressure by V and integrating by parts, we get the following formula, where R is given by the following relation. So our goal now is to reconstruct M, the number of sources, to get some information about Wj and sigma j from this relation. We note here that R can be reconstructed from the boundary observation. So F is known, it's measured at the boundary. V is also known, we chose our own function V. However, as you can see here, we need the knowledge of the final pressure P at time t or Pt at time t. Or otherwise, we may assume the condition that V at time t is equal to Vt at time t equal to 0. So this part is cancelled. And thus, R can be directly be obtained from the boundary observations. So for example, we take V to be rho at zt x plus iy power n, where rho satisfies the following one-dimensional wave equation, with rho at time t is equal to rho t at time t is equal to 0. Now substituting this function V in our algebraic relation, we get the following formula. Ujka are some coefficients related to sigma j. Pja are the projections on the xy plane of the center. So the goal now is to reconstruct M, Pja, and the coefficients in Ujka from the boundary observations or from the values of R that can be obtained from the boundary measure. So we follow the algebraic algorithm. This algorithm actually allows us to reconstruct the number of the observers M as the rank of the Hankel matrix H, the projections on the XY, YZ, and XZ planes of the centers. Also, we were able to reconstruct the coefficients in UJKR that provides us by some information about the conductivity. And we note that the combination of different projections on XY, YZ, and XZ planes may not uniquely determine the centers. For this purpose, we proceed in one more step to reconstruct the final locations of the centers using the previously calculated coefficients. Also, we gave a generalization of this algorithm to higher dimensions Rn, provided that n satisfies the following condition for some k positive. And it's good to note here that this generalization is not only for the thermoacoustic problem, it works for the algebraic algorithm in general that can be applied in different inverse problems. And finally, we were able to give some Holder stability estimates. This actually was the work done for thermoacoustic tomography problem. Similar work was also done for photoacoustic tomography problem, which is also submitted for publication. And thank you.
Thank you very much. Thanks a lot, Hanin. So I think there is maybe the time for one question still. Is there any question on the floor? Please unmute yourself or raise your hand. All right, it doesn't seem to be the case. Then let me thank once again Hanin. Thank you very much for the talk. And I would invite Now Luna, Suki, to share the screen.
Yes, hello everyone.
Thank you very much. Let us try to see if the screen sharing is working correctly.
Okay, can you see my
Yes,
slide?
everything seems very smooth today. That's very good. All right. So I think that we can directly start. So the next talk is going to be given by Luna Suki, who's from the University of Lyon and University of San Joseph in Lebanon. And she's going to talk about a generalized method for sparse partial least square theory and applications.
Thank you. So hello everyone. My name is Luna Al-Suki. My PhD is I'm doing my PhD in the Claude Bernard University of Lyon and in the St. Joseph University of Beirut, but also in collaboration with IFPN and in the framework of the LabEx Million. I'm glad to be here today, so thank you for allowing me to present some of the main work and results that have been completed until now. Okay, so this will be the scope of work. I will start by presenting the main context of the thesis by pointing out the goals and one of the IFPN data set that have been provided to us. And then I will talk briefly about PLS related methods. So I will share some of the main components for you to be able to understand the presentation a little bit better. And in the third part, I will detail a new generalized method that we put in place and called the dual sparse partial least squares. And I will end with comparative results and conclusion and some perspectives. So in the field of chemometrics and analytical chemistry, one main task is to analyze the composition of complex mixtures via different types of measurements, mostly high dimensional ones, like the NMR data here. And we would like to predict some properties of these oil samples, like the density, for example. So we have a data set of oil sample measurements, and we would like to use these values in order to predict at best the properties of petroleum samples that we have in our hands. Therefore, in this thesis, we would like to find a robust regression strategy that is compatible to different kinds of data. Our goal is to increase the accuracy of prediction, reduce the dimensionality, and find a way to visualize where is the information, where is the most important information hidden in these data. So we are interested in regression problems. 3 data sets have been provided to us, but I will only share with you the results for the NMR spectra. So the nuclear magnetic resonance, it's an analysis technique that helps in unmasking the composition of complex mixtures. Here we have the representation of 182 NMR spectra of refined oil after pre-treatment that have been done. And they are represented with 21,000 variables, which is quite a lot, and will allow us to talk about high dimensional data when characterizing these spectra. Moreover, if we look at the figure here, we can notice the existence of several peaks with different length. And we can also consider the NMR spectra to be functions. So our aim here is to predict the property of density of these oil samples. Now, one main common problem in this data set is that the number of variables is much bigger than the number of observations. A lot of regression methods address this challenge, but the regression strategy that gave the best results until now and led us to dig deeper in it is the PLS. In fact, the PLS is a common tool used in chemometrics. And so in this part of the presentation, I will briefly detail the PLS and some related methods that intervenes also in solving the problem of high dimensionality, but try to enhance the PLS strategy, which will lead to the main work accomplished until now. So for the PLS, it is an iterative regression tool that handles highly correlated data. Its goal is to search for k number of orthogonal directions in the x space in which we will project the y vector in order to reduce the dimension of the data. So here initially we have x, our matrix of data, with p numbers of variables that we represent here. We search for k weight vectors, and which will lead to a score matrix T, a new score matrix T of reduced variables composed with k components. We call them the PLS components. And we choose these components with this optimization problem here in equation 1, where we maximize the correlation between the new component xw and the response vector y, subject to an L2 norm of w equals to 1. So we are reducing the dimension from p variables to k PLS components. Now, this algorithm here summarizes the PLS method. We compute the weight vectors in this step. We will compute the components of the score matrix in this step. And this is the deflation step, which will allow us to get orthogonal directions for the score matrix. Now, as good as it sounds, and like most methods, PLS has a lot of advantages, but also have some important downsides. It is applied in an easy algorithm with no matrix inversion. Moreover, it's accurate in its results. However, the coefficients are hard to interpret in order to extract useful information concerning the variables. In this example here, we chose we applied the PLS regression to NIR spectra, which is another type of measurements for oil samples. The NIR spectra differs from the NMR because it's more smooth. Now, when we applied the PLS coefficient for PLS regression for 8 components, here are the regression coefficients that we have. We can see the similarities between the two curves, but we can also notice that no important information, we can't extract important information that will tell us which are the most relevant variables to keep and which are the irrelevant variables to neglect. And this led our curiosity to look into the sparse partial least squares methodologies. The sparse partial least squares methodologies combine the PLS dimension reduction strategy to a variable selection strategy, like, for example, the lasso procedure. In this table, I summarized the optimization problem for 3 types of SPLS methods. They all adopt the soft thresholding function as a solution, which will lead to sparse results. Now, sparse results are one good lead in finding which are the most relevant variables. Now, inspired by these methodologies, we conceived a more generalized procedure that we call the dual sparse partial least squares. I will start by the definition of the dual. So if we have the dual norm omega is Z in RP is the maximum value between ZT and W constrained to omega W equals to 1. Now, why is this relevant? Well, if we go back a few slides and we look at the PLS optimization problem, comparing the dual norm definition, one notices that optimizing the PLS function amounts to finding the vector W that goes with the dual norm of the norm L2 when Z is equal to XTY. And so finding this similarity gave us the idea to evaluate different types of norm other than the L2 norm, and maybe adding some penalization to the norm. As a first suggestion, we chose a combination of an L1 and L2 norm of this type here in equation 7. It's similar to the lasso penalization. For the resolution procedure, we start by applying the Lagrange multipliers. So instead of maximizing ZTW, we are minimizing the function LW here. Second, ZTW reaches its maximum value if W and Z are in the same orthant. In other words, if each coordinates of W has respectively the same sign of each coordinate of Z. Then on one hand, if we differentiate equation 7, we get this result here where delta is the vector of signs of Z. And on the other hand, if we differentiate equation 8, we get that the gradient of omega W is equal to Z over mu. Now, we find after a few manipulation, we find this solution for W. It is similar to the closed form solution of the soft thresholding. We can notice that we have denoted nu as the product of the two initial parameter lambda and mu. This is relevant because this way we can compare Z to nu, solving the problem of choosing the right parameters. Indeed, the first parameter, mu, guarantees the constraint imposed, but the challenge is finding the lambda. So we would, it's better to find the mu. And so finding the mu is more difficult. And we suggested a new strategy. Now, this strategy is to choose the nu iteratively according to the number of variables that we would like to keep in the active set at each iteration, which means we impose the number of zeros in the W vector at each iteration. And so for each iteration, if we look at the graph here, we represent the cumulative distribution of Z, which is xty. We impose the percentage of variables that we would like to shrink to 0. For example, if you want to have 80% of the variables to be equal to 0. So the question is, which 20% of the variables are the most important? We can easily find the mu that can be used in the algorithm. Now, this being said, we implemented this first case, and before applying it to our data set, we used a calibration and validation method that I don't have the time to detail here, but I will show you the comparative results. And the comparative results are for the validation set. So our set is divided into two, the calibration where we do the regression, and the validation set that we use to validate the model. And so the evaluation will be focused on the validation set. The evaluation of the accuracy of prediction is done by evaluating the root mean square error, the RMSE. We took 80% of the calibration data. Now, if we look at the figure where we are comparing, the figure on the left where we are comparing the errors, we can see that we have compared, we have the dotted line in black to be the regression of the PLS, the values of RMSE for the PLS. In red, our new method, the dual SPLS, and the other colors are for the sparse partial least squares, 3 methods that I presented in the table. We can see how the two curves that are the most close to each other are the red one and the black one. And we know that the PLS is accurate in its results, so we can conclude that the dual SPLS is also accurate in its results for this case. Then we have the SPLS from Shan and Lucao, and we have the SPLS from the Durif regression that is a little bit further away because it's more of a variable selection than a regression for prediction. So according to this graph here, we can say that we have accuracy in our results for the dual SPLS compared to the PLS and the rest of the SPLS methods. Now, if we look at the spectra here at the right, first we have the raw spectra, the NMR spectra. We can see where the peaks are located. Then here we have the regression coefficients for the PLS. We can see similarities also here between the raw spectra and the PLS coefficients. The peaks remains in the same place. but we can see that there is still a lot of noise. As for the dual SPLS, when applying this regression method, we can see that we have sparse results. For about 21,000 variables, we have selected using the algorithm only 400 null values. So it's like saying that there are 400 relevant variables in the NMR spectra. We can see that we have selected the right peaks, and it's very similar to the raw spectra with almost no noise. Now for the other SPLS methods, we can see that the results are, and the lasso, the results are misleading, even if we got good accuracy in prediction and sparse results. It's unfortunately misleading to the NMR data. So in conclusion, the dual sparse partial least squares maintain the advantages of the PLS. We still have accuracy and prediction. We still have an easy algorithm. It will allow us to choose better adapted norms for each type of data that we have, and it provides sparse results. So it's good for coefficient interpretation because we can know which are the most relevant variables to consider. Now, as perspective, these are the norms that we would like to evaluate. So if you have any suggestions, please. And we would like to use some basis functions to adapt the method to the functional data literature. We would like also to study the statistical properties of the PLS and the dual SPLS. And soon, I hope all the dual SPLS norm methods will be available as R packages in R. Thank you.
Thank you very much, Luna. Then, as usual, the floor is open for questions. So if you want to ask something, you can unmute yourself and or raise the hand through Zoom. Okay, I think again it doesn't seem to be the case. Then let me thank once again Luna for the talk. Thank you very much. I will invite then Diala to share the screen. Hello, good afternoon. Thank you for joining.
So can you see my screen?
Yes, it seems to work very well. All right, so the next talk of the final talk of the session will be given by Diala Hawat from the University of Lille. And she's going to give an introduction to the concept of gravitational allocations. All right, so I think that you can just start.
First of all, thank you for inviting me to this conference. So I will give a quick introduction to the gravitational allocation, since this is the basic of my works. So first of all, I will talk about point process, since I will talk about gravitational allocation from the Lebesgue measure to a point process. So I will give a brief introduction about point process. Then I will talk about gravitational allocation. First of all, what is a point process? So in probability, a point process is an infinite set of points distributed in the space randomly, such that it follows certain properties. So the most famous point process is the Poisson point process. And it's famous since it has a property of independence. The homogeneous Poisson point process of intensity lambda, for example, is known by two properties. The first one is that the number of points falling in a window has a Poisson distribution of parameter, the intensity of the Poisson point process times the volume of the window. And when I say the intensity of a point process, it is the number of points in unit ball. And the second property, which is the most important, is that if we take disjoint sets, the number of points falling in each set are independent. So this point process is used to modelize phenomena where independent is observed. But not all phenomenon has independence. So there's two other classes of point process. The first one, where there is repulsion between points. We know from this class the determinantal point process. And determinantal point processes are point processes which are specified by a certain kernel. And we can see that the points are better spread in the space than the Poisson point process. The third class is a class of point process where attraction between points is observed, and we call them permanental point process. And we can see here in the picture Cox point process, which exhibit attraction between the points. So we can see cluster of points. Okay, now what is an allocation? First of all, what is a transportation? Given two measure nu and mu, a transportation between nu and mu is a measure such that its first marginal is mu and the second marginal is mu. This means that I'm defining a measure which take the first measure to the second measure. Now, when nu and mu are counting measure, the transportation will be denoted by matching. This means that if we take two sets of points and try to do a transportation between them, we'll denote it by matching. Now, an allocation is a transportation between the Lebesgue measure and a counting measure. So, for example, we can imagine that the Lebesgue measure is a piece of land, for example, and the counting measure are farmers, and we wanna divide the piece of land between these farmers. So we wanna divide it into part. Each part will be associated to one farmer. In our work, we work on gravitational allocation from the Lebesgue measure to a point process. So the counting measure will be a point process. Here in the picture, we see the Variational solution. It's not a gravitational allocation, but it has the idea. So the idea is that we have a point process, the green dots. We will denote them by stars. And we want to divide the Lebesgue measure of the space into cells that will denote them by basin of attraction of the star. And all the other points of the space will be denoted by seeds. So the aim is to divide the space into zone. We will call them basin allocated to the seeds, to the stars. Okay, and the fair allocation is an allocation where all the basin have equal area. So in 2006, the first work on this field was introduced by Nazarov, Sodin, and Volberg, who talk about the transportation by gradient flow from the Lebesgue measure to the zero of the Gaussian analytic function, which is one of the point process exhibiting repulsion between points. And they proved that the transportation is well defined, and that this transportation divides the space into basin of equal area. The area is pi. Then in 2018, Perez, Palindromic, and Chargi talk about the gravitational allocation from the Lebesgue measure to the Poisson point process. Now I will talk about the gravitational allocation from the Lebesgue to the point process, and I will give the idea behind construction of any allocation to any point process. So we take a standard Poisson point process. We will denote it by Z, and I repeat, we will denote their point by centers, and we want to divide the space into basin allocated to this center. So to this purpose, we suppose that each center, each point of the Poisson, has a force of attraction acting on all the teeth, on all the point of the space. And we define the force acting on a seat X by the sum of the force of attraction exerted by the stars from the point of Z. So we can see here in the formula, this is the summation on the star of the force of attraction. In dimension 3, this is the force of gravity of Newton. That's why we denote it by gravitational allocation. This is the force of gravity in the dimension. So there is a term under the sum, which means that we reorder the summation by increasing distance from the target point X, and this ensures that this summation is convergent in dimension bigger than 3, since this is an infinite sum. In dimension 2, it's not convergent, and in dimension bigger than 3, we have to reorder the terms to make sure that what we talk about is well defined. Now, so we have the force acting on each seat. Now we have to define the trajectory of each seat into its allocation. So taking a seat X, we define the integral curve yx of t to be the unique solution of the differential equation dyx of t over dt equal f of yx of t and yx of 0 equal x over some maximal domain. This curve will be denoted by gravitational flow curves. What does it mean? This means that the yx of t represents the trajectory of x. So it will begin by x, and it will follow the vector field f to move. What happened in reality is that if you take any seat, any point of the space, this point will follow the trajectory to fall into a star, and all the set of points that will fall into the star, and this means that their trajectory end in this star, will be allocated to the star and will form the basin of attraction of this star. Okay, in this allocation, all the basin have a volume equal to 1. And now I will explain why this happened, why why each point should, if it follows this trajectory, will end by a star. So first of all, I will give an alternative definition of the force function. So this is the force function that I defined at the beginning. The problem with this definition is that x appear in the order of the summation. So if we want to differentiate f with respect to x, there is a problem. So Perez, Cauchy, and Romick prove an alternative formula by considering the difference between the sum, but starting from arbitrary points. And so they find the residual terms, which is kd. Kd is the volume of the unit ball in d dimension times u minus v. So we get the alternative definition of the function f, which is the same, but this time we reorder the point by increasing distance from the origin, and we add the correcting term, which is kd times x. Now, the force function, as is defined, if we take the divergence of this force function, we can see that it's the sum of Dirac over the stars plus a term, and this term is a constant positive. So this divergence is always positive outside the point of z. So we can think that f of x is the negative of the gradient of a potential function that I will denote it by u. And so the Laplacian of u is the negative of the divergence of f. And then the potential function u will be a superharmonic function on Rd without z. This means that the Laplacian is negative, and this means that it has a certain property which make all what I defined work. Since the superharmonic function verifies the minimum principle, which say that they didn't have minimum on their domain, the minimum are attained on the boundary. And so in our case, the boundary is the point of z, the stars. So we can think that if we take any seat, almost surely, this seat, if it will follow the force F, the force F, it will be directed into decreasing the potential U, and so it will fall into a star. That's why it will end into a point of the point process. So, in other words, we are going, this differential equation is a gradient descent into the minimum of the potential function. And this is how this scheme works. And we can define any allocation by considering that I need a potential function such that this potential function, their critical point or their minimum are the point of the point process. He should be superharmonic, and we will direct each point of the space following the vector field f, which will be the negative of the gradient of the potential function u. What I did is that I construct a gravitational allocation to the Ginebra point process, but it's not published yet. And I'm working on the good property of the gravitational allocation to define new point processes, and this will be used to get more result in numerical integration. So thank you for your attention.
Thank you very much, Diala, for the nice talk. Once again, the floor is open for any question. So if you want, you can unmute yourself or you can raise your hand. I understand, by the way, that there will be now in the break between session 3 and session 4 break room available, so you can join one of them and continue the conversation if you wish so. Then in the meantime, then I will thank Diala once again. Thank you very much for the talk.
So I'm chairing the session, and our first speaker is Professor Pierre Youssef from New York University in Abu Dhabi, who will speak about spectrum of random graphs. Please go ahead.
Thank you, Nabil. So yeah, I'm really happy to speak here. It's really a great initiative. It's so cool to see. I didn't realize there are so many Lebanese mathematicians. So it really feels good. So yeah, so today I wanted to speak about spectrum of random graphs, but before that I wanted to advertise a couple of postdoctoral positions we have in NYU Abu Dhabi. So one is in high dimensional probability, so it's random matrices, graphs, Markov chains, but also concentration and functional inequalities, convex geometry, geometric functional analysis, and high dimensional geometry. So yeah, people who are interested in this, please drop me an email. Another position is we're trying to explore mathematical foundation of machine learning, so feature selection and modeling bias and fairness in AI, and application of random matrices to machine learning. So yeah, if you also are interested in this, or if you know someone interested in this, just drop me an email and I will tell you more about that. Okay, so so I want to talk about, I know it's a general audience, so just stop me. It's at some point it may get technical, but I hope it will be accessible to everyone. So graphs, I mean, are there in everyday life. So and more so. So on the left, it's an image of the graph of internet. So as you can see, it's a huge graph. And this is a feature which will be with us in the talk, that the number of vertices in the graph is going to be huge. The graphs are really huge because this is the reality nowadays. And yeah, I don't know if I should be admitting people or someone else is admitting them. Okay, you're muted. But...
No, it's okay, Pierre.
Okay. Yeah, so one feature, even though it doesn't look on the picture, so you see a lot of edges inside the graph, but this is actually not at all the case in reality. In reality, graphs are very sparse, which means they have a huge number of vertices, but very few connections. Like in your life, you know, I don't know, you may know on Facebook, say you may have, if you are a star person, you may have, I don't know, 500 friends, but this is extremely little compared to the size of the Facebook graph, right? So keep in mind that graphs are usually, nowadays, are usually a huge number of vertices, but very, very sparse. They have very few connections compared to the size of the graph. So as I said, we have social graphs, which are very important, but you can also think of road graphs. So here actually I was able to find a map of supposedly metro in Beirut, which we'll see the light at some point. I don't know when. So yeah, so all in all, graphs are important to study in themselves. And one important feature of the graph is just how well connected they are. So the road maps, how well connected they are. If you send a message on Facebook, how well it spreads out. So you really need to know the expansion properties of the graph and how well connected it is. So more formally, a graph is just a collection of vertices and with a set of edges. And I'm gonna talk, in this talk, I'm gonna just look at undirected graphs, which means that I don't, I mean, if I am friends with you, you are also friends with me. I'm not allowed, like, it's not like I talk to you and you do not reply to me. So it's really goes both ways. So I'm gonna enumerate the vertices from 1 to n, and keep in mind that n is really huge. So the number of vertices is very large. So I'm allowing crazy people. You're allowed to talk to yourself if you want, but so I'm not allowing multiple edges. So just a simple collection between vertices. And one way to measure how well of an expander you are, so how well connected you are, is to look at how many edges. So you take any set S of vertices, and you look at how many edges takes you from S to the complement of S. So imagine you have a city, S is a city, and you would like to have many roads which lead you outside of the city. Okay, this is the number of edges from S to S complement. So if whenever you arrive to a city, you have many roads which lead you outside of the city, then you are very well connected as a graph, right? Of course, you cannot ask to have many roads going out of the city if you are, I don't know, in some small town, in some small village town. So it has to be compared to the size of your city. That's why I divide by the size of that. Okay. And I take the worst case, and the worst case has to be large for your graph to be well connected. So this h of g that I denoted here really measures how well connected your graph is. So it measures the quality of your net. So basic example, so if you want a road map, let's say, which is a road which is very well connected, like just draw roads everywhere, like, or connect everyone to each other, right? So this is the complete graph. Of course, if you are at the city S, if you want to go outside of the city, we're saying that we have roads everywhere. So the size of the edge, number of edges from S to S complement is just, for each vertex, you have S complement edges. So you have in total S times the size of S complement edges, so which tells you that h of g is just huge, right? Which is normal. This graph is very well connected. However, this is not very nice because it costs a lot to build roads everywhere or to build connections everywhere. You don't want to do that. So on the other extreme, you can imagine the cycle graph where like you just put people on circle and just each one passes the message to the next one. Now this graph is not at all well connected because the points which are diametrically opposed, in order to get the message from this point to the point down, you have to go all over all of these guys which are between them. So you only have two roads basically for each vertex to get to the other extreme. So which makes the edge expansion constant very, very small. So in total, I mean, what I want to say here is that the goal of people is basically to build graphs which are well connected, which means that they have this edge expansion constant large, so separated from 0 as the number of vertices grows. Of course, you want to do this not in the trivial way. So you want to do this not by building a lot of edges, by minimizing the number of edges. So you want to do little construction, but still be able to be efficiently connected in this respect. Now, from a theoretical point of view, so there are people who study just the edge expansion constants from a graph theoretical point of view. So what I do is more spectral theory. So we're gonna link this to spectral properties of graphs. So how we're gonna do this? Actually, every graph you can represent it as a matrix, so as an adjacency matrix. So you list the vertices. We already named them from 1 to n. You list them as rows and columns from 1 to n, and then you decide that if vertex I is friends with vertex j, then you put 1 in the ij entry. Otherwise, you just put 0. So you can see that this is a one-to-one correspondence between simple graphs and adjacency matrices. So for every graph, we have an adjacency matrix, and for every adjacency matrix, this completely characterizes the graph. And since we are undirected, if I is friends with j, then j is also friends with I, which means that this matrix is actually symmetric. So we can talk about its eigenvalues, and we can ask, actually, is there a relation between the spectrum and what I just talked, the connectivity of the graph? And it turns out that yes. So I'm going to denote lambda to be the second largest eigenvalue in absolute value. So I take lambda 1 is the largest one, lambda 2 is the second largest, and lambda n is the smallest one. And I take the second largest in absolute value, which is the maximum of lambda 2 and lambda n in absolute value. And it turns out something really interesting, which was observed by Allen and Millman, that for graphs, the bigger the gap is between the first eigenvalue and the second eigenvalue, the bigger this gap is, the better the expansion properties of the graph are. So whenever lambda 1 and lambda 2 are glued together, the graph is really not connected, actually. And the bigger, when you create a gap, the graph starts to be connected, and until you reach the maximal gap, and this is the best possible expander. And for the record, graphs which have the maximal possible spectral gap are what we call Ramanujan graphs. These are the best expanders, best spectral expanders. Okay, so instead of looking at constructing deterministic graphs, one way to check for expander graphs is to look at random graphs. So there are many ways to create randomness here. One way, you could just pick a class of graphs and pick one uniformly at random. That's not what we're going to do. What we're going to do here in this talk is I'm going to talk about Erdős-Rényi graphs. These are basically a very, very basic model, not very realistic, but it's a basic model of graph where you decide, you look at each two people. If you look at your room, you pick two people, and then you decide to make them friends with probability P, and you decide not to make them friends with probability 1 minus P. And you do this independently, which is not very, very realistic because our connections really depend on each other. in reality. So, okay, so this is the Erdos-Shreni graph. So entries inside the adjacency matrix are now just Bernoulli variables, which have parameter Pn, and they are independent up to the center. Okay, so just maybe notice here that the degree of each vertex, so the number of friends for each person in this graph is just the number of Bernoullis which are equal to 1, which is a binomial distribution, which is on average equal to D, which I denoted D as NPN. This is the average number of friends inside your graph. So before checking the spectral gap, the gap between the first and the second eigenvalue, let's maybe ask ourselves, how does the whole spectrum look like of this matrix? Now, this is a topic which is this is actually the basic topic in the field of random matrices, that you are given a random matrix and you would like to understand how does the random spectrum look like. So it's a random process which lives on the real line, and you'd like to see if it has some shape, some limiting shape as the dimension of the matrix grows. So one way to capture this is by what we call the empirical spectral measure. So you basically just want to locate the eigenvalues. So you put the Diracs as the eigenvalues of the matrix, and then you just take the average, 1 over n, the sum of these Diracs. So you get a measure, which is a measure on R in this case, because the matrix is symmetric. And what is this measure doing is that for every interval, it just tells you how the average number of eigenvalues landing inside this interval. So it's a way to locate the eigenvalues on average. Okay. So it turns out that as the average degree NPN goes to infinity, Tran, Wu, and Wang showed that basically the limiting distribution of this Erdos-Shreni graph, it really looks, the shape of the eigenvalue really looks like a semicircular. Okay, so the limiting spectral distribution is what we call the semicircular law, which is the law which has this distribution, this density function. So this already gives us an indication how does the spectrum look like. Now this result is actually a special case of a much general result, which is called Wigner's semicircular theorem, because it applies for general random matrices. There is a universality phenomena, which we're not going to talk about here. So, okay, so this result just tells us what? It tells us that most of the eigenvalue, because remember the conversions that we had there, was telling us, it was measuring the proportion of eigenvalue landing inside this interval. It doesn't mean that it may have 1 or 2 or 100 eigenvalue which are doing something else, but most of the spectrum lives in the scale of the semicircular law, which I didn't tell you here, but these guys here, this side of this guy is -2 and 2, which are given by the support here. So the most of the spectrum, if I remove the normalization here by square root of NPN, most of the spectrum of this matrix, of this Erdos-Shreni matrix, lives between -2 square root of NP and 2 square root of NP. And you now ask, what about the leading eigenvalue? What happens to the leading eigenvalue? So from this limiting distribution, what we know is that they cannot be inside this interval. Otherwise, the limiting law will have a support which is smaller. So they have to be bigger than 2 square root of NP. But where are they? Okay. So the largest eigenvalue was a bit easier to estimate, and this was done by Krivulevich and Sudakov, which basically showed that the largest eigenvalue of this Erdos-Shreni matrix is of order the maximum between NPN, which is the average degree, and square root of the maximal degree. So this I should probably denote it as average degree. So whenever NPN, the average degree, is very large, so it's much bigger than log n, it turns out just by some concentration phenomena, all degrees are basically very well concentrated. So each person inside this graph has almost the same number of friends. So what does it mean? That it means that this maximal degree here is just equal to the average, because everyone has the same number of vertices, number of friends. So this guy is like around square root of NPN. So which means that lambda1 is of order NPN. So it's very, very far from the rest of the spectrum, which is at 2 square root of NPN. So what about the second eigenvalue? Because the second eigenvalue will tell us if whenever there is a gap between the first and the second, that's when we will have that the Erdos-Shreni graph is a very well expander or not. So it turns out that whenever NPN is much larger than the log n, then we do have a spectral gap. So lambda 2 is basically glued up to the limiting, to the support of the limiting measure. So the second eigenvalue is at the scale 2 square root of np, while the first eigenvalue is at the scale np. So there is a huge gap between them, and this is the best possible gap, and which means that the Erdős-Rényi graph is actually Ramanujan, almost Ramanujan. It's the best possible experiment. So, and this was observed by several authors, Reddy Komlosh, Wu, Benaish, Bordunov, and Knowles, and Latawa, Van Handel, and myself, up to the optimal scale, which is log n. And now you ask yourself, okay, so putting it another way, whenever npn over log n goes to infinity, we have that the second eigenvalue over square root of npn converges to 2 as n goes to infinity. And as I said, this means that this is the best possible expander in this regime. Now you ask yourself, what's happening if I go below that? So whenever npn over log n is very small, goes to 0, what happens? So if we look up the calculation of Krivya-Levich and Sudakov, now it's no longer the average degree which works, it's the maximal degree which works, just because the degrees are no longer concentrated. So it's the maximal degree, and this is the maximal of binomial distribution. You can just explicitly calculate this, and it turns out it's this expression here, but it doesn't matter. And it was also done by Benaish, Bordunov, and Knowles that in this regime, npn over log n goes to 0. Actually, the second eigenvalue is also equivalent to the square root of the maximal degree. What does it mean? It means that the second largest eigenvalue and the largest eigenvalue are glued together. They are glued together, and they are both equal to the maximal degree, square root of the maximal degree, which means that you do not have a spectral gap. You do not have a gap between the largest and the second largest, which means that the Erdős-Rényi graph is actually not at all very well expanded. It's actually even worse than this. Whenever you go below this log n, this is actually log n is the threshold of connectivity. Erdős-Rényi is not even connected. You will have a vertex which is isolated. So you will never be able to reach it. It's not just that it's not a very well expanded, it's not connected. Okay, so now we have like two regimes, whenever npn is extremely large and whenever npn is extremely small compared to log n. In one of them, you have that the Erdős-Rényi graph is a very well expander. It's almost Ramanujan, and in the other one, it's not at all an expander. It's not even connected. And the natural question is, what's happening in between? So, is there some phase transition? Is there a place where I can say, okay, at this place, I'm passing from being very well expanded to not being very well expanded? So, and this is actually what we did with Konstantin Tikhomirov. What we did is that whenever npn is going to infinity, we completely characterize the second eigenvalue. So the second eigenvalue is equivalent to this quantity rho n, which is this expression square root of the maximum between maximum degree over npn minus 1 and 1. More importantly, what is important here is that now we can just check whenever this quantity here is glued to the limiting support. So when is this guy, we're gonna discuss if this guy is bigger than 2 square root npn or smaller than 2 square root npn. And this depends if theta n is bigger or smaller to 1. So this is probably bigger than 1 and this is smaller than 1. And this depends really at whenever the maximal degree is bigger or smaller than 2 times the average. So all in all, we can calculate it. And we can put this into numbers, into exact numbers. And what we found out is that whenever npn over log n is bigger than a specific constant, 1 over log 4 over e. Now, it's not a magic constant. It's the constant where you have twice the average degree. Whenever you have a vertex, a person which has friends more than twice the average of other people. This is when you start having an optimal, this is when you stop having an optimal spectral gap. So let me summarize it again. Whenever npn over log n bigger than this specific constant, 1 over log 4 over e, then your Erdős-Rényi graph is an optimal expander. And whenever it's smaller than 1 over log 4 over e, then it has no spectral gap. Okay. So whenever you start having a person in your graph which has more than twice the average number of friends, this is when your graph stops being an expander. And this is kind of natural in this sense because the information will get stuck at him. Like he becomes a hub and information circulates around him and no longer goes out to other people. Okay. So if you think at the original question, which was, we would like to build a graph, which is very well connected by putting the least amount of connection, and at least in this random setting, the number of connections, we know what it is. NPN was the average degree. We have to go up to log n over log 4 over each connection on average, in order for us to be able to build a very well expander. And this is the minimal number of connections we can afford. Okay, and I should say that this result was also obtained independently by Aldo Petesnols, who also actually refined some things that we also obtained. Okay, so I have still 4 minutes. So let me tell you that this story here, I just told you, is part of a bigger, more general story. It was actually what we were trying to do is something else. We were trying, I mean, it's of course related, but we were trying to understand what is the effect of sparsity on random matrices. So you have a random matrix which have entries which are centered and of variance 1. And what you start doing is that you start putting zeros inside the matrix. You start eliminating entries. Okay, this is, if you think of data science nowadays, this is very important because you would like to reduce number of reduce the data. One way to reduce the data is to do some dimensionality reduction techniques, but one way also to do it is just to decide, okay, I'm gonna just eliminate part of the data by zeroing out these entries. Now, the way we do it is a bit stupid maybe, but we just flip a coin and decide if we just remove it or not for the entry. And we'd like to understand what is the effect of this on the spectrum of the matrix. And it turns out that, so whenever I showed you this picture of the spectrum was looking like a semicircle, or it means most of the spectrum was living inside the semicircle, but it meant that maybe there are eigenvalues which are far apart. So in general, whenever the entries are bounded, then this is not the case. All eigenvalues are already sticking to the bulk, so they are all in this regime. But this transformation that we just did by zeroing out entries, actually it turns out that we know when it will start having eigenvalue pumping out of the bulk of the spectrum. And this is actually very, very similar to something very famous, which is the Bike-Benarouspe shift phase transition. It was famous because it has application in signal processing, where you have a signal and you have a noise. The noise is basically the random matrix, and you would like to know what is the magnitude of the noise which you should put for the noise to be seen, for it not to be lost inside the rest of the eigenvalue of your random matrix. And for this, you would like to have an eigenvalue which comes up out of the system. And this is a sort of sparse analog of this result. So, and maybe just let me finish with one more thing here, is that just on a more theoretical level, a consequence of the theorems that we did, the characterizations that we did, is that the operator norm of the matrix, if you do this calculation here of understanding what is this quantity here, but for the case of general random matrices, it turns out that you will obtain that the operator norm of the matrix is between the maximal Euclidean norm of the row and 2 plus epsilon times the maximal Euclidean norm. Now, okay, you may not find this amazing, but let me just put this here. This guy is the supremum. So the norm of a matrix is the supremum of the action of a matrix on the sphere, on the unit sphere. While this guy here is just the supremum, it's actually the maximum of the action of your matrix, but on the canonical basis. And if you look at it, it's just crazy. Like in general, this is absolutely wrong. You cannot say that the norm of the matrix, that the largest eigenvalue of the matrix, is characterized by just looking at the canonical basis. While here for random matrices, at least for these random matrices, this is true. So a random matrix which has IID entries, its norm, instead of looking at the supremum over the whole sphere, you just check n vectors, the canonical basis, and you obtain the norm, up to a constant, of course, but you get the norm with high probability. So, and this actually, you start asking yourself, is this something particular to random matrices, or like, because it's completely wrong for deterministic matrices. And it actually, it turns out that Segener observed already this for IID matrices, so entries with matrices which have entries which are the same low and they are independent. This is always the case. The norm is just equal to checking it on the canonical basis, which is crazy. And you would ask yourself after, is this because the entries were the same law? And it turns out that yes. So Segner already observed that this is no longer true if you drop the IID entries, if the entries have different law. And what we observed is actually still that with Latawov and Handel, we actually observed that this phenomena is actually true just for Gaussian matrices. So either for IID matrices, matrices which have the same law, or for matrices which have maybe different laws inside, but they are Gaussian. So they have different variances. This phenomena will still be true, that the norm is captured by looking at the canonical. I'm gonna stop here. I'm gonna thank you.
Thank you, Pierre. We can take a few questions. Question? Anybody would like to ask a question?
Oh, I see someone raising his hand.
Okay.
Me, may I ask a question, Nabil?
Sorry?
May I ask a question?
Yes.
Yes. I am. So go ahead, please.
Okay, thank you. Thanks, Pierre, for the nice talk. My question is about the case where there is asymptotically no spectral gap. So may you show us, please, the slide on that? Yes, exactly. Right? So asymptotically no spectral, it means that the difference between lambda and the largest eigenvalue, lambda 1, is very small. So is there some toy example saying whether we have equality between lambda and this first eigenvalue, or whether we have they are different and the gap is very, very small, and whether there is some kind a rate of convergence estimates of the error, whether it is exponentially small?
Yeah, so actually everything is actually no. So the result that I stated here is asymptotic in the sense that the largest eigenvalue over the second largest eigenvalue converges to 1 as n goes to infinity. These guys here, I actually obtained a rate of conversion. I don't remember what are exactly the rate of conversion, but you need to know also that deterministically before that, so for Erdos-Srini graph, there is a threshold of connectivity, which is exactly log n. So not this guy here, but really exactly log n. So below the threshold of connectivity, the graph is no longer connected. So lambda 1 is equal to lambda to the second log, because you no longer have connectivity. So there is a very tiny interval here where like the graph is just not connected. I mean, before that, the graph is completely not connected even. You have isolated vertices. And above log n, there is a tiny interval between log n and this guy times this constant here, where the graph is connected, but it's not a very well expanded. And this is really this small regime, which is interesting here, this small interval here. I don't know if I answered the question.
Thank you. You've answered it. Thank you very much.
Okay, thanks. Thanks, Ayman. Any other question, please? No? So in that case, we thank Pierre.
Oh, wait. No, wait.
Somebody
Nabil, there is someone.
Yeah, okay. Sarah.
Yeah, thank you, Nabil. Thank you, Pierre, for the talk. I've just, I come from a physics background, and the circle you've shown is, I think, what we call the Wigner semicircle, right?
Yes.
So, and we know that the limit for the largest eigenvalue, or the distribution of the largest eigenvalue, is what we know as the Tracy-Widom distribution.
Yes, that's all.
Yeah.
So in the specific regime, not in the sparse regime, right? When I'm yeah.
So I mean, do you know of any results? I mean, of the physical implications of this spectral gap, because the largest eigenvalue in that context, in the context, it was like the energy bands in the physical context. That was the somehow the physical underpinning of the largest eigenvalue. But now with the spectral gap, can you or do you know of any physical?
Yeah, so physical is gonna be hard for me, guys. I have absolutely no background in physics. But so what I can tell you is that the spectral gap, it just means that you also have what we call Poincaré inequality. So okay, if you launch a random walk on this graph, It's gonna reach all vertices very quickly. So that's what we call it. It's gonna be exponentially ergodic, and which means that you have a Poincare inequality. Now, Poincare inequality. Why am I saying about Poincare? Because this may speak to you because it's an inequality between the variance and the Dirichlet form. So it should be interpreted as some form of drop of energy or something. But I don't know. I don't know more.
And just like a follow-up on this question. So if you have, I mean, the larger or the smaller the spectral gap, you're somehow characterizing the topology of the network, right?
It's somehow, sorry?
Characterizing the topology of the network. Yani it's like you can say, and it's in the sense that you talked about this random walk, you somehow have a measure of diffusion over the network, right?
Yes, of course.
So that's like some sort of a physical interpretation of that gap.
Oh, yeah,
it's
okay.
like,
This is exactly this exponential ergodicity or this Poincare inequality. It's really the drop of or the amount of diffusion, if you want, in your cross.
Sure. Okay. I'm thinking as I'm.
But this is something very general, right? Not just this talk. Yeah, in general, spectral gap, it just means what you just said, basically. Cool.
Okay.
Thanks.
Thank you, Sarah. Thank you, Pierre. So we move to the next speaker, Maher Saeed, Dr. Maher Saeed from Northwestern University, who will speak about natural experiment to assess the impact of street-level urban design interventions on walkability and business activity. Looks like.
Thank you.
So please go ahead, Maher.
Thank you. Hello, everyone. My name is Maher Saeed, and I'm a PhD candidate at Northwestern University. Today, I'm going to be talking about an urban design intervention that took place on Jeanne d'Arc Street and how it affected walkability and business activity. To give a quick introduction about myself, I did a bachelor at UB in civil engineering, followed by a master's in civil engineering as well in 2015. And there I did some work in pedestrian mobility, structure equation modeling, and discrete choice modeling. After that, I worked for 2 years in the industry as a transportation engineer. And now I'm pursuing my PhD at Northwestern, where I work on autonomous vehicles, automated modes of freight shipping and parcel delivery, and currently working with the US Department of Transportation on assessing the impact of COVID-19 on mobility and spending. So today we're going to be talking about walkability, and this presentation is going to be a bit more applied, and I intentionally selected this work because I feel like it's something very relatable to most of us here in the audience. We all experience the horrible, I would say, walking conditions in a lot of parts of Lebanon and Hamra in specific. And it's a big problem, especially in a country that is plagued by congestion. We really don't want to be discouraging people from walking and accordingly using public transportation, better modes of transport. And it's not to ignore the benefits of walking, from increased physical activity, better health, less air pollution, better sense of community, etc. So I would assume with a similar mentality, in 2011, the AUB Neighborhood Initiative and the Center for Civic Engagement and Community Service proposed to redesign Jeanne d'Arc Street to be an accessible pedestrian-friendly street prototype for other cities in the city and Lebanon overall. In 2014, the design was completed and presented to the municipality of Beirut, and in July 2017, construction works began. The intervention consisted of many changes to the urban environment, but main changes have been the widening of the sidewalk on one side of the street, providing an obstacle-free pathways for pedestrians across that sidewalk, and also elevating the intersections to be flush with the sidewalk so that we're prioritizing pedestrian traffic over car traffic. It's easier to cross the intersection. We can see some of these changes here on the before and after bird's eye view of the street. And we can see this very narrow sidewalk on the left side of the street and a parking lane next to it. So in the redesign of the street, what we did is we took away that parking lane and provided more sidewalk for pedestrians to travel. After 8 months of construction work in February 2018, this is what Jeanne d'Arc looks like today. And we can see the wider sidewalk here, besides all the upgraded infrastructure. This is a before and after to kind of give you a good sense of how much Jeanne d'Arc Street has changed. And the nice thing about this intervention is it's a perfect opportunity to do a natural experiment study and analysis, given that we can measure pedestrian mobility and experience before the intervention takes place, and we can measure it after it takes place. And using some statistical methods, we can disentangle the impact that this intervention has had on both pedestrian mobility and experience. So using data from this natural experiment, this study aims to explore the impacts of street-level urban design interventions on walking pattern satisfaction, provide insights on the impact of the intervention on commercial activity, and also draw policy recommendations that would benefit planners, research, and analysts alike. A very elegant and simple method to do the analysis with this data that we have is called difference-in-difference regressions. And the idea behind difference-in-difference regression is that it captures the effect of a treatment using before and after analysis. So let's assume we have this plot here, and I'm using pedestrian flow just as an example variable to simplify the discussion. We can capture the pedestrian flow pre-treatment. So our treatment occurred in 2018 when construction finished. We can capture pedestrian flow before it, and then once construction is done, we can capture pedestrian flow post-treatment. Now the pedestrian flow might just continue rising at the same rate, might rise at a faster rate, or might actually decrease. But the problem here is, so if we're thinking that it decreased, for example, how do we know that this decrease has been due to the intervention itself? How do we know that this decrease has not been due to an economic downturn, which Lebanon has experienced, for example, or due to drastically bad weather in a specific year, or due to COVID-19? For now, we can't, but there is a way to do it. So let's take a step back. What we can do is actually select a street in the neighborhood of Jeanne d'Arc that has a very similar profile to Jeanne d'Arc Street in terms of pedestrian mobility, knowing that the intervention will not affect that street at all. So this is a very important assumption, that we're assuming that the intervention will not affect that street, either because it's distant enough or because of other reasons. And that would be our control street. So now we're making an assumption that is called the parallel trends assumption, which is all external variables affecting these two streets are similar, with the exception of the intervention. And if that's the case, then pedestrian flows should vary on the two streets in a similar fashion, except for when the intervention takes place. And this is when we see that deviation from the parallel trends, and our treatment effect, so the effect of the intervention on pedestrian mobility or experience or satisfaction, is that difference between the observed outcome and the unobserved counterfactual. Now, we can calculate that just by taking the distance between the two lines, but the problem is that we don't get that nice suite of statistical methods that would allow us to identify whether this treatment effect is statistically significant or not. So what we can use here is use a regression as a proxy to get all the statistical analysis that we want to do and still get that treatment effect value. So if we take the pedestrian flow as equal to beta 0, which is just an intercept, plus beta 1 times Jeanne d'Arc Street, which is a dummy variable that is equal to 1 if the data comes from Jeanne d'Arc Street and 0 otherwise, in this case being Lyon, plus beta 2 times post-treatment, which is equal to 1 if the data comes from post-treatment and equal to 0 otherwise, plus beta 3 times those two dummies, we end up getting beta 3 being that treatment effect. And we can prove that beta 3 is equal to that treatment effect. But now the nice thing about it is that because we're estimating a regression, we get a t-statistic for beta 3, which means we can do statistical analysis on it and then discuss whether the treatment effect is indeed significant or not. And we're going to see how this comes into play in later slides when I show you the analysis before adding the statistics with it and after. But let's talk a bit about that control street. So the control street we chose is Lyon Street, which I briefly mentioned. It's located on Hamra Street on the south side. It is mixed use similar to Jeanne d'Arc Street, but it's also distant enough to reduce any contamination bias due to the intervention, and also perpendicular to avoid induced switching of pedestrians due to the intervention. So we're trying our best to make sure that the parallel trends assumption holds. We collected three main categories of data. We collected pedestrian counts on both streets for 8 days total in each of 2015 and 2019. We also inquired pedestrians on the street about their attitudes and perceptions towards the walking environment. And we got feedback from business managers about their customers and their opinions on the intervention. The surveys were collected on the stretches that are highlighted by red on Jeanne d'Arc Street and Lyon Street. And the pedestrian counts were collected on points B and C on Jeanne d'Arc Street and points E and D on Lyon Street. And these points will matter in a bit because we're going to start doing the difference in difference regression analysis for them in pairs. The data was collected in April 2015 for the pre-treatment scenario and in April 2019 for the post-treatment scenario. And notice how both data collection efforts occurred in April. This was intentional to reduce seasonality effect, especially weather in specific, because we don't want to collect the data in months with very different weather. So looking at the results, before we go into statistical analysis, we see some evidence of increased pedestrian traffic, and we see stronger evidence of increased utilization of the sidewalk. And that's another variable we collected. We were keeping an eye on whether people were walking actually on the sidewalk or on the street, which Lebanese people tend to do just to get around all the obstacles that they encounter while walking. So we noticed on Jeanne d'Arc Street that percent of people walking on the sidewalk almost jumped to 100% from roughly 90, while compared to Lyon, that increases only around 4%. And remember, we're always thinking in differences here. So it's good that Jeanne d'Arc is increasing more than Lyon because it indicates that the intervention might indeed have benefited the percentage of people walking on the sidewalk. Looking at pedestrian flow, we see some increase on Jeanne d'Arc and some decrease on Lyon, which is also a good sign. However, once we start looking at the difference in difference regressions, we notice that with pedestrian traffic volume, the treatment effect is generally insignificant. And the way we know that is by looking at these p-values and the fact that they're most below, above 0.05, and even above 0.1, while we're looking for significant values to be below 0.05 in terms of p-value, which is the case with the pair BD, but it's only one pair out of 3. So although there is some evidence that the treatment effect has been positive, it's generally, the evidence is that it's generally insignificant. While for percent of pedestrians walking the sidewalk, we can see a consistently positive insignificant treatment effect, which is very good to see because it indicates towards the success of the intervention. Pedestrian walking patterns are better now. When we look at the satisfaction, we see also similar results, which is good. So pedestrians overall, with their overall walking experience, are experiencing roughly 10% increased satisfaction. And we did the analysis in a similar way, where we took the satisfaction indicators and ran them through a difference in difference regression between Jeanne d'Arc and Lyon Street. And we also see increased satisfaction with a lot of elements of the walking environment, especially street lighting at roughly 30%. However, we don't see significant effects regarding greenery and the aesthetics. For businesses, we didn't do much statistical analysis just because the sample size was very small. We had only 11 respondents. So the analysis was mainly qualitative, but even qualitatively, we can see a treatment effect of roughly 21% increase in daily customers. And we also observed that while businesses were excited for the intervention, after the intervention, there was a general dissatisfaction, mainly due to the long construction process and also due to a reduction on street parking. Businesses were not very happy with that. So in conclusion, the intervention has been, in my opinion, a success, and it led to the improvement in walking patterns, satisfaction of pedestrians, and commercial activity on the street. However, the businesses experienced some dissatisfaction, which is important for planners to take note of and examine the full range of solutions in the future to mitigate the concerns of these businesses. And we still have some relevant future works regarding pedestrian mobility in Beirut. Professor Maya Abu Zaid, who's one of the collaborators on this paper, is collaborating with MIT and is currently in the early stages of analyzing pedestrian mobility and experience in areas surrounding the port following the explosion last summer. Also, I've been granted a fellowship recently from the Buffett Institute at Northwestern to also keep studying active mobility in Lebanon and Beirut, especially after the explosion. I would like to thank the funders of this study and a lot of people who helped make this study happen, and also my sponsors who are making my PhD happen. So thank you very much for attending this talk, and if you have any questions, please let me know. Professor Nabil, I think you're muted.
Sorry. Thank you, Maher.
Thank you.
For interesting live talk. Any question, please? Any question? So
hopefully that means that everything was clear.
Yeah, well, no, it's clear. So, well, thank you. If there are no questions, then we can move to the next talk.
Thank you very much.
Thank you. Okay. So our next speaker is Eli Abdo, PhD candidate at Temple University, former student at AUB. So welcome, Eli, and you can go ahead. You can share your screen and start your talk.
Okay, thank you. So today I'll be talking about Navier-Stokes equations in 2 dimensions. And I will talk briefly about an electroconvection model that we have been recently working on, where the velocity of the fluid obeys a forced Navier-Stokes equation. So the Navier-Stokes equation is a PDE describing the flow of incompressible fluids. Incompressibility means that if you take a volume element in the fluid, then its volume is preserved under the flow map for all positive times. So the Navier-Stokes equation is given by the following PDE. Time derivative of u plus u dot gradient of u equals minus gradient of p over rho plus no Laplacian u. U stands for velocity and p stands for pressure. U and p are both functions of 2 variables, position x and time t. And nu and rho are just positive constants. So the Navier-Stokes equation can be studied in different types of domains and boundary conditions. And for example, we can take a bounded smooth, an open bounded smooth domain with homogeneous Dirichlet boundary conditions, and we can consider the periodic case on the d-dimensional torus. In 3 dimensions, it has been shown that global weak solutions exist. And it has been shown that a local smooth solution exists, but it has not been shown yet that global smooth solution exists for arbitrary initial data. And this is one of the millennium problems, and it's called the Navier-Stokes existence and smoothness problem. So in this talk, we are going to consider the 2-dimensional periodic case on the 2-dimensional torus. And we are going to use the following functional spaces. We have H, the Hilbert subspace of L2, consisting of periodic divergence-free mean zero vectors. We have V, which is the Hilbert subspace of H1. Here, H1 is the Sobolev space of order 1, consisting of periodic divergence-free mean zero vector, and V prime will be the dual space of V. We also consider the L2 inner product on H and the H1 inner product on V, namely the V inner product of U and V will be just the L2 inner product of the gradient of U and the gradient of V. We are going also to use the spaces LP 0T LQ consisting of vectors U such that the LP norm of U as a function of X is in LQ as a function of T. Now we consider the forced Navier-Stokes equation where we have body forces in the fluid, and the equation is given by the PDE, time derivative of U plus U dot nabla U plus nabla P minus Laplacian U equals F. And we have the incompressibility condition, which is equivalent to the divergence-free condition, which means that the divergence of U is 0. And the forced Navier-Stokes equation will be posed onto two-dimensional torus. All unknowns are periodic. The body forces are time independent. They are taken to be smooth, divergence-free, and have mean 0. And we take the initial velocity U0 to be square integrable with mean 0 and divergence free. And now the first question is whether the following PDE has solutions, and if it does, how regular are they? So let's define first weak solution of the forced Navier-Stokes equation. So a solution of 8 is said to be a weak solution if first it satisfies a regularity condition. The L2 norm of U is essentially bounded on 0T, and the H1 norm of U is square integrable on 0T. 2, it has to obey the forced Navier-Stokes equation in the distribution sense. And 3, it has to obey the divergence-free condition in the distribution sense. So if the following 3 conditions are satisfied, then we say that U is a weak solution of the forced Navier-Stokes equation on 0T. We are going to use also two operators. We have, so H, the space H consisting of periodic mean 0 divergence-free vector is a closed subspace of L2. And so L2 can be written as H plus its orthogonal complement. We have a projection. The projection of U will be just, so U has a Fourier series. It can be written as the sum of Ujei Ijx. The projection of U can be written as the sum of Pju J Ix, where Pju J is just the orthogonal projection onto the unit vector J over J. And we are going to use also the Stokes operator, which is defined on H2 intersection H. H2 is Sobolev space of order 2. And the Stokes operator A applied to a vector U is just the projection of minus Laplacian of U. So the operator A is nice. By the spectral theorem for Hilbert spaces, we can find an orthonormal basis of H consisting of eigenfunctions of the Stokes operator. The eigenfunctions are infinitely differentiable. They are divergence-free and have mean 0. And now we are going to consider Galerkin approximations. So namely, the projection of U onto the space spanned by the first n eigenfunctions. So we have a Navier-Stokes equation. We want to show whether this equation has global weak solutions or not. So we take equations approximating the original Navier-Stokes equation, which are equations like that, given by equation 19. And we show that each equation has a solution. So we obtain a sequence of solutions, and we show that that sequence of solutions has a subsequence that converges to some function U in some norm. And that function U, which is the limit, will turn out to be the weak solution that we are looking for. So let's note first that equation 19 is equivalent to a system of nonlinear ODEs. So if we write the equations obeyed by the coefficients of the Galerkin approximations, we obtain a system of nonlinear ODEs, and a solution of that system exists if it's bounded in L2. So we show that UN, the sequence UN, is uniformly bounded in L2 0TV, and we show that the time derivative of UN is uniformly bounded in L2 0T V prime. V prime here is the dual of V. And so the open lines lemma tells us that UN has a subsequence that converges strongly in L2 0T L2 to some function U, and that function U turns out to be the weak solution that we are seeking. So this is briefly the technique. We are not going to go through the details. We obtain the following theorem. So fix an arbitrary time t and let U0 be in H then the forced Navier-Stokes equation has a unique solution U. The L2 norm of U is essentially bounded on 0t. The H1 norm of U is square integrable on 0t, and we have an estimate given by equation 20. The L2 norm of ut squared is bounded by the L2 norm of u0 squared e to the minus t plus the L2 norm of f squared. And we also have a similar bound for the gradient of u in the space L2 0t L2, which is given by equation 21. Now, this is true if the initial data u0 is in H. If we upgrade the regularity of the initial data and we assume that u0 has weak derivative, u0 is in V, then we can upgrade the regularity of the solution and we can obtain similar estimates for the L2 norm of the gradient of u and for the Laplacian of u in the space L2 0t L2. Now, from that theorem, we can show existence of absorbing balls. In other words, suppose that u0 is in H and suppose that u is a solution of the forced Navier-Stokes equation. Then you can find a radius r depending only on the body forces. We remember that the body forces are time independent. So we can find an r depending only on the body forces f and a time t0 depending on the L2 norm of the initial velocity u0, such that the L2 norm of the gradient of u is bounded by r for all times t greater than or equal to t0. This basically follows from this theorem. So we are taking u0 in H. So we have that estimate 21 holds. So from that, take capital T to be 1, for example, and then you conclude the existence of some time T1 such that the L2 norm of the gradient of u evaluated at T1 is finite. And then your initial data here will be u evaluated at T1. So u0 is not in V, u0 is just in H by assumption. But now u evaluated at T1 is our initial data. So we can use now this estimate, which will hold for times t greater than or equal to T1, and take advantage of the exponential decay here to bound this term by some constant depending only on the body forces F. So all in all, we obtain an absorbing ball. Now we have a solution map which is well defined. So for each time t and for each initial data u0 in H, you have a solution in H. And the solution is unique, so the map is well defined. We have also shown existence of some ball BR such that for any u0 in H and for any time t0, depending on the L2 norm of u0, the image of u0 under the solution map as of t lies in the ball BR. Now we can see that this ball is compact in H. This follows from Relic's theorem, which tells you that the embedding of H1 in L2 is compact, and it follows also from the Banach-Alaoglu theorem. So this ball BR is compact, and we actually have three properties. We have compactness of the ball BR in H, we have continuity of the solution map, and we have injectivity of the solution map. Of course, this requires a proof, but the following those main three properties allow us to conclude the existence of a global attractor in H. So whenever we have a solution map which is continuous and injective, and whenever we have a compact absorbing ball, then we can automatically conclude the existence of a global attractor, which is actually a compact connected invariant maximal set with the property that the limit of the distance of the image of u0 under the map as of t to x is 0 as t goes to plus infinity. So that's a general technique to show existence of absorbing ball. Now we have considered an electroconvection model describing the evolution of a surface charge density in a two-dimensional fluid. The evolution of the charge density is given by the PDE 33. The time derivative of Q plus the divergence of J is 0. J here is just the current density, which is created by Q times U, where Q is the charge and U is the velocity of the fluid. U is also unknown. And by some electric field created by the charge density Q and some potential phi. So Q is unknown. Q, of course, is a function of two variables x and t, and U is also unknown, and U obeys a forced Navier-Stokes equation, which is given by this equation, we note here that the forces F is time independent, but the force QE depends on Q, and so it depends on time T. And so here we have a coupled system consisting of two different equations. So that problem reduces to the following system. An equation described by the charge density Q. It's given by time derivative of Q plus U dot gradient of Q plus, this is the fractional Laplacian of order 1. Applied to Q equals to Laplacian phi is just a smooth function. It is time independent. We have an equation obeyed by the velocity U, where we have some body forces which are smooth time independent, but some forces depend on Q. And we have the incompressibility condition, which is the same as the divergence-free condition. And we are going, so we have shown that the system 35 has regular solutions. So a solution of this system is said to be a strong solution if it obeys the following regularity conditions. So the H1 norm of U is essentially bounded on 0t, and the H2 norm of U is square integrable on 0t, and the L4 norm of Q is essentially bounded on 0t, and the H half norm of Q is square integrable on 0t. We have shown that this system has weak solutions. Weak solutions are not unique. If we upgrade the regularity of the initial data, we were able to show existence of a unique global strong solution. Now you can notice that if you integrate in the space variable, you can show that Q preserves. So we are assuming that the initial data Q0 has mean 0. It can be shown that Q preserves that property. So the space average of Q will be 0 for all times t. But also we are assuming that Q0 has mean 0, but this property will not be preserved because of some term here which might blow up. So the space average of the velocity might grow up in time due to that integral. So we perform a change of variable and we obtain an equivalent system where U and Q preserve the property, the mean 0 property, and that new frame will be called the mean 0 frame. In that frame, we show the existence of a global attractor. So this has been published in the transactions of AMS, and the Navier-Stokes equations, the information about the Navier-Stokes equation is somehow taken from Constantin and Foya's book. Thank you.
Thank you, Eli. Thank you, Eli. Any question, please? Ahmad, Professor Sabra.
Hi. Thank you, Nabil. Hi, Eli. How are you?
Hi, Professor. I'm good.
Thank you for the talk. Mark, you said that the weak solution for the system that you showed in the last slide, in this slide, are not unique?
Yes, the weak solutions are not unique. So if you take U0 and Q0 in L2, you can show, or probably U0 in L2 and Q in L4, I don't remember exactly, you can show the existence of weak solutions. But you need to upgrade the regularity of the initial data to show that those solutions are strong, and strong solutions turn out to be unique.
I see. And this is in Rn, yes? You are talking.
No, here we are. No. The model here is posed on the two-dimensional torus, so the square.
I see.
Yeah, and higher dimensions, the Navier-Stokes equations, we don't know whether the Navier-Stokes equation has global solutions. That's one of the millennium problems.
Okay. Thank you.
Thank you.
Other questions? No more questions. So, I have a small question for you, Eddie. You don't talk about the boundary condition. I mean, when you have to when you take your Galerkin approximation. So you take a space.
So here we are just working. The whole presentation today was just posed on the two-dimensional torus. So we are just assuming that on the boundaries, the values are the same. So we are just considering the periodic case. The functions, all the functions are periodic here.
So then this is why you can take this expression.
Yeah, in the case of general domains, the situation is a little different. And so, for example, here P and minus delta commutes in the periodic case. And the general case, those two operators do not commute. And so here just the projection of minus delta of Phi k is just the minus Laplacian of Phi k. But in the general case, that's not the same. So, and you can consider homogeneous Dirichlet boundary conditions. There are different situations you can deal with.
Okay, thanks. So, no more questions? No. Okay, thank you, Eli.
Okay, I'll stop sharing.
So you can stop sharing, and then
thank you.
So now we are in advance. So we go to Noor Khudari. Hi, Noor.
Hi.
Hi, Noor. So Noor also is a former AUB student, math department, and she's now at Temple University also. She will be talking about macroscopic interpretation of microscopic car following models with traffic waves. Please go ahead.
Thank you. So when talking about traffic flow, the first thing that comes to mind is why we study traffic models instead of just observing traffic flow on the street. And the answer for that is very simple. It's because models are much simpler than reality, where you can isolate certain parameters and study their effect on traffic flow and make some predictions. And that does not only apply for traffic flow, it applies to any modeling in general. So since human driving behavior is so much complicated and it depends on so many changing variables, modeling might help us understand it better. Now, in the world of traffic modeling, we have two communities: the microscopic community, which focuses on minute aspects of traffic stream, like vehicle-to-vehicle interaction and individual vehicle interactions, and they help us analyze very small changes in traffic flow over time and space. And on the other hand, we have the macroscopic modeling community, which focuses on traffic flow as a whole without considering features of individual cars, but it rather focuses on aggregated quantities like density, flow, and velocity. What we are trying to do is we're trying to bridge the gap between those two communities by trying to understand the macroscopic interpretations of some non-equilibrium phenomena and microscopic models. So I will start first by introducing some basic quantities, followed by some examples of the models. And I'm sure everyone knows that, but just for the sake of notations, we denote by rho the density, which is the number of vehicles per unit length. Q is the flow rate, which is the number of vehicles passing a fixed position per time. And U, which is Q divided by rho, and it's the velocity, which is the distance traveled per unit time. An example of a macroscopic model is the LWR model, which has the following continuity equation, and it's an equation in two unknowns, rho and u. And the simplest idea was to model u as a linear function of rho, and the person who did that first was Greenshield, and that's a picture of him collecting some data in the early 1930s and trying to fit it into a linear function. To give an example of a microscopic model, we should first introduce the setup. So on a road, we consider n vehicles. We denote by xj the position of the jth vehicle, and then by vj its velocity, aj its acceleration. And for a second order microscopic model, the acceleration is seen as a function of the gap between the car j and the car ahead of it, sj dot, which is the difference in the velocities of those two cars, vj, which is the velocity of the current car. And for microscopic models, we consider two different types of roads, and for simplicity, we just consider one lane dynamics. So we consider either an infinite road with one vehicle leading, or just a ring road where the last vehicle is following the first vehicle. Now, an example of microscopic models are car following models, where drivers react to the changes in the relative positions of vehicles ahead of them. And an example of that is the IDM, or the intelligent driver model, which has the following equation. So in this case, it's a second order model, and the first derivative of the position is the velocity, the second derivative of the position is the acceleration, and it's described by this complicated equation, where v0 is the desired velocity, and s0 is the minimum spacing between two cars, t is the headway time, and a is the maximum vehicle acceleration, b is the comfortable braking deceleration. So an important aspect of traffic modeling is our ability to generate a fundamental diagram. And a fundamental diagram is a relation basically between traffic flow and traffic density, and it generally has the following shape. Now, just like, so if you are on the fundamental diagram, this means that you are at equilibrium, and at equilibrium means that the vehicles are equispaced and they are moving at the same speed. Now, just like the pendulum, being at equilibrium means that you are either stable or unstable. So if you are thinking of a pendulum and it's hanging down, then it is stable. If it's hanging the other way around, and if you leave it, then it falls down and it's not stable. Similarly, for being on the fundamental diagram, if you are on the blue part, for example, in this case, you are stable. And if you are on the red part, you are unstable, which means if you add some perturbation to your system, eventually waves would develop and you are, your traffic flow is not stable. And to determine the regions of stability and instability, basically you need to do like a parameter analysis. And for the case of the IDM, basically A and B are the parameters that determine those regions. Now, to make a connection between microscopic and macroscopic models, we should first derive the macroscopic quantities from the microscopic models. And one way to do that is to use the Gaussian kernels. An example is this, where h is the width of your kernel, which should be small enough to get localized information about rho and q. And then we can use standard reconstruction techniques to get rho and q. So basically in that case, rho is a superposition of the Gaussian kernels, and q is the same thing, just weighted with velocities. And this is a good reconstruction because the reconstructed rho and q actually satisfy the continuity equation. And if you plot the data that you get pointwise from those quantities, you get this line over here, where you have like over here, you have full stoppage, and over here you have cars that are going a little bit faster. And then the average of those data is this blue point over here that we will call the average state or the effective wave state. Also, the slope of this line is actually the speed of the traveling wave that would develop. Now, our main question is, starting at equilibrium, let's say at this point on the fundamental diagram, if you add perturbations to the system, how would the average state or the wave state move? So how would this blue dot move? And the answer is we actually verified that it would move possibly in 3 different waves. And to verify that, we took 3 different scenarios that are simple. And any other complicated scenarios is basically based on those 3 building blocks. I don't have time to go over all of them, so I'll just focus on one scenario, which is considering a ring road. We start at equilibrium. So as you can see in the plots of velocity versus position, all cars are equispaced and they have the same speed, as you can see. Add some noise to your system and you can see small perturbations. And if we wait a long time enough, you can see that the waves are fully developed. Now, how does that translate on the level of the fundamental diagram? We can see that if you start at equilibrium at this red point here, and you have perturbations and waves are developed, you can see that the wave state or the average state moves down on this vertical line, which means that you are having lower velocities and lower flow rates. So if that is what happens when you get waves, the question is, are we able to dampen those developed waves using AV control? And the answer is yes, we can dampen the waves using carefully choosing parameters. And even if we are more careful in choosing the parameters, we can actually not only dampen waves, but shoot for going back to equilibrium on the fundamental diagram. And we will see how we do that in a second. So the way we introduce AVs is, I'll use this example. So say we have a long road and we have a platoon of cars with one leading vehicle at the beginning moving at a constant speed. We have AVs or autonomous vehicles at a 10% penetration rate. In that case, we took every 10th vehicle to be an AV. And the way we model those AVs is the acceleration of those cars is actually the acceleration of the human drivers, which is the IDM acceleration, plus a relaxation term, which is this one, where we are relaxing over 1 over gamma of the time to the ideal speed u, which is in this specific example chosen to be the speed of the lead vehicle. So as you can see in this plot of the length of the platoon, so we are measuring the length of the platoon, we can see that not all choices of gamma are actually working. So if you start at equilibrium with that length of the platoon, you add perturbations, so the length is getting longer and longer. And when you turn on the AVs at this time, you can see that for certain choices of gamma, you were actually able to go back to the original length of the platoon, while for other values of gamma, you still have waves. Now, to understand better how we can choose gamma, we do a parameter analysis. And in this case, we are measuring the difference between the maximum and the minimum velocity of all vehicles averaged over a certain time interval. And we are choosing a certain AV gamma parameter and a certain penetration rate. And if that measured value is near 0, which is the dark blue in this plot, then our AV actually was successful in dampening the waves. And if it's not, then we did not succeed. I will end up here with a simulation of this scenario. So what you're seeing now is the ring road scenario where you are adding perturbations to the system. You started at equilibrium, but then waves have developed. You can see the car-to-car interaction down, and in a few seconds the AVs will be turned on when you see something red down, and the waves are being dampened, and then with a careful choice of view we were able to go back to the fundamental diagram. So just a final thought that you can take with you, that waves don't only imply local oscillations, they also have important macroscopic consequences. And finding the macroscopic interpretations of microscopic models can help us actually use some properties microscopically of waves and backtrack to inform more properties at the microscopic level. And that's it from my side. Any questions?
Thank you, Noor. So,
thank you.
Questions?
Can I ask a question? Sorry, I'm not seeing the raise hand button.
Yeah, I'm not seeing the raise hand, but yes.
This is Maya Abu Zaid. Thanks for the interesting presentation, Noor. So just a question, what is the advantage of doing a joint macro-micro analysis as opposed to doing the whole thing using micro simulation? Can you derive the same measures about congestion and other things using purely micro simulation?
Right, yeah. Of course, you can like use the derived macro quantities to have like, they have the same properties, but on I can give you like on a bigger picture level. So on the macroscopic level, we actually know or we have a completed work on the study of waves and their stability, which does not apply on the microscopic level. So the bigger picture idea is to try to find macroscopic limits of microscopic models and then backtrack to microscopic models, if that was clear. So we're trying to use what we know about waves on the macroscopic level and then go back to microscopic. That's not done yet. It's just the big level picture.
Okay, thank you. Very interesting. And just another question, did you test or are you planning to test multiple levels of AV penetration and seeing how the results would change? You tested 10%, right? In your
Yeah. So if you look at this, you actually can see that for different levels of penetration rate.
you have that. Sorry, I missed it.
Yeah.
Okay. Well, thank you and good luck.
Thank you.
Any more questions? I don't see any hands.
There's a question in the chat.
Oh.
In the chat, well, I haven't seen it. Yes.
Could I? Okay, so all the simulations that we did are on one lane, just for simplicity. I personally have not tested multi-lane scenarios, but I'm part of a bigger group. We're working on smoothing waves on the I-24. On the I-24 highway in Tennessee, and they have actually tested multi-lane scenarios, and it does work. So the same thing carries on for multi-lane scenarios, of course, with more like complexity.
Okay. Any more questions to Noor? Where? The chat. Okay, well, we can thank you, Noor.
Thank you.
Thank you. So then now we can move to the last speaker. So we are in advance actually, but that's okay. So Ghada Abi Younis from Université de Lyon 1, France. She will talk about mathematical modeling of inflammatory processes of atherosclerosis. Okay. Okay, please go ahead, Ghada. Ghada.
Yes, can you hear me?
Yeah, we hear you now. Okay, so let's John. Go ahead.
Okay, so hi everyone. My name is Ghada Abiyounes and I am a PhD student at Université Claude Bernard Lyon at France under the supervision of Vitaly Vorpert at University of Claude Bernard Lyon 1 and Nader El Khatib from the Lebanese American University. Today I will be talking about a mathematical model of atherosclerosis where I will be focusing on the inflammatory processes of this disease. So just a second, it is not working. I think that's better. Now let me start with a brief overview of this presentation. We will start by introducing atherosclerosis. Then we are going to talk a little bit about the biological processes of this disease. Then we move to describe a mathematical model, a complete mathematical model. Then the next step will be to talk about a reduced model. Then we are going to study the perturbed solutions as well as solutions of a traveling wave type. And finally, we are going to investigate the transition from the reduced to the complete model. So you may have heard about atherosclerosis, but have you ever known that the clinical manifestations of atherosclerosis, such as ischemic heart disease and stroke, are the top 2 leading causes of death worldwide? And even though COVID-19 is on track to become one of the top causes of death, heart disease remains the leading cause of death, even in highly affected countries. So what is atherosclerosis? As a terminology, it is the formation of a lipid pool inside the arterial wall. This causes the arteries to narrow and to be less flexible, and this reduces the amount of blood delivered through these arteries and causes a depletion in the amount of oxygen and nutrients delivered to vital organs. Now, in order to talk about this biological process, let us first have a look on the physiology of a normal artery. Here is a cross-section of a normal artery where you can see here the lumen where the blood circulates and the arterial wall that consists of 3 layers, the intima, the media, and the adventitia. As you can notice here, there is a selective barrier. It is called the endothelium that is between the blood and the arterial walls. When the arterial wall is exposed to cardiovascular risk factors such as an elevated level of cholesterol in the blood, it becomes damaged. Here, let me explain to you what happens here. Here is the lumen where the blood circulates, and here is the first layer of the arterial wall. So when this endothelial cells are exposed to risk factors, they become damaged. First of all, this thin layer that covers these endothelial cells becomes compromised, and the junctions between these cells becomes ruptured. So this causes an abnormal leakage of macromolecules from the blood towards the intima. Now, the pathogenesis of atherosclerosis is the following. When the endothelial cells become damaged, they allow the passage of a high level of LDLs towards the intima. So they start to attract white blood cells from the blood, such as monocytes. So monocytes undergo morphological changes and roll over towards the intima, where they become macrophages. Macrophages release free radicals that oxidize the LDL particles. Now, macrophages start to engulf and phagocyte the oxidized LDL, and they produce cytokines in order to promote the recruitment of new monocytes. At this stage, T helper cells regulate the differentiation of monocytes into macrophages. Now, the excess of lipid inside the macrophages gives it a foamy appearance, so we call them foam cells. But at the end of the day, foam cells cannot destroy the oxidized LDL, so they undergo apoptosis and release their content, which forms the atherosclerotic plaque. Indeed, this atherosclerotic plaque changes the geometry of the artery. Now, studies have shown that there are two different processes that occur during atherogenesis. The first one is the pro-inflammatory process mediated by pro-inflammatory monocytes and macrophages, as well as T helper cells of subtype 1. So their role is to support inflammation, whereas anti-inflammatory monocytes and macrophages, as well as T helper cells of subtype 2, suppress ongoing inflammation and facilitate tissue repair. So now let us move to the mathematical part. We propose a 1D model to describe the biological processes that have been mentioned earlier. It is a model of 14 equations of reaction diffusion type, where we can see that we are modeling the evolution in time of many concentrations such as LDL, oxidized LDL, monocytes, macrophages, T helper cells, their corresponding cytokines, and foam cells. Here, you can notice that we have a term P in green. So this term represents the endothelial permeability indicator. Now, since we have a big model and it is hard to handle it, we decided to reduce it by keeping only the inflammatory part of atherosclerosis. So the reduced model is the following. It is a model of only 5 equations. The term P in this reduced model is modeled this way. So first of all, we have this term alpha. It refers to the assessment of endothelial dysfunction. And h of alpha is a step function. We have this term alpha 0 that represents a threshold between normal and abnormal endothelial function. So if there is no endothelial dysfunction, h of alpha is 0, otherwise it is 1. Now for this term, it describes the permeability of the endothelium. P0 describes the selective permeability of a healthy endothelium, and K1 denotes the effect of endothelial impairment regulators. For this reduced model, we had to impose a condition that is the monotonicity of the system. We mean by this, we need that all the off-diagonal elements of the Jacobian should be non-negative. Now, this condition will be used later on in order to prove the existence of traveling wave solutions. So this conditions means that we have to take lambda 2, the parameters lambda 2 and P0 to be 0. Now, the stability analysis of the monotone reduced model leads to the existence of 4 fixed points, but in the positive half space. We are not going to consider the negative ones because we are dealing with physical concentrations. So the fixed points we are going to consider are E1, EU, and E2. We also take into consideration some conditions. So this stability analysis leads to the following. If there is no endothelial dysfunction, we only have one solution, E1, that is stable. And otherwise, we have this classification. You may notice that we may either reach a monostable case, I mean by this when we have only one stable equilibrium, or a bistable case when we have two stable equilibria. Each fixed point has its own biological interpretation. Since E1, for example, is the state where there is no pro-inflammatory cytokines, so it means that there is no inflammation. So it corresponds to the disease-free situation, whereas E2 corresponds to the inflammatory state. The fixed point EU, it is always unstable. It corresponds to a threshold the system has to overcome in order to move from the non-inflammatory state to the inflammatory state. Now, I will list briefly some of the results that we got from this monotone reduced model. If we have a healthy endothelium, then no inflammation is triggered. Otherwise, the inflammation may be triggered or not, depending on the rate of LDL penetration, as well as on the effect of endothelial regulators. We tried to report data from the literature, and we could elaborate this predictive diagram where you can see three different zones of different risk levels. For example, in zone 3, it is a zone of high risk level. In this zone, only E2 is stable, the point that corresponds to the inflammatory state. Zone 3 is the bistable case, and zone 1 is the zone where only E1 is stable. I just want to mention something here, that this predictive diagram is elaborated according to the values of some critical parameters. We note here that lambda 1 is the rate of intimal LDL penetration, and K1, it is the effect of endothelial regulators. Now, as I told you before, we took two parameters to be 0 in order to ensure the monotonicity of the system. But what if we take these parameters to be positive but close to 0? Do we still have the same solutions, having same stability analysis? The answer is yes. We considered the concept of perturbation, that is as follows. If we have an equation having a solution here, and we are going to perturb slightly this equation, then the solution also varies slightly. So using the implicit function theorem, we proved that, in fact, we could ensure the existence of solutions when lambda 2 and P0 are close to 0 but positive, and these solutions are close to the one found for the monotone reduced model, and they have same stability analysis. And as I told you before, we are interested in finding a solution of traveling wave type. Why? Because we want to show that the inflammation within the arterial wall propagates as a wave. And this was done using some of the theorems that I'm going to talk a little bit about them. But first of all, let me tell you what is a traveling wave solution. If you consider this kind of problems where U is the unknown, U is a function of X and T, the traveling wave solution takes this form, U of X and T equals to omega of X minus CT, where C is the speed of the wave. Of course, this traveling wave solution has limits at infinity, omega plus and omega minus. If you want to apply this to our model, we will have the traveling wave solution will have this form. And here, the constant C is the speed of the propagation of inflammation in our case. We proved using the theorem that there exists a unique traveling wave solution in the bistable case. And for the monostable case, we could prove the existence of a traveling wave solution, but in this case, the uniqueness does not hold. And let me show you a simulation for the traveling wave solution. Here, if we start by taking at time t0 this step function, and then we exhibit the simulations, what we are going to get is the propagation of the wave. So here, the wave reaches the fixed point, that is the inflammatory state, and starts to propagate. And now we can show you that, mathematically speaking, we proved that the inflammation propagates as a wave. And finally, I'll be talking very briefly about the transition from the reduced to the complete model. The first thing I'm going to talk about is the consistency of the stability for a specific range of parameters. We could find that there is a high conformity in the stability analysis of the reduced and the complete model. That means we could retrieve the same classification of the fixed points for the complete model. This is an inductive approach. So this approach works here. We are moving from the reduced to the complete under a certain range of parameters. That means we can rely on the reduced model to have some conclusions for the complete one. Moreover, we could draw some bifurcation diagrams for the complete model, and the conclusions drawn from these bifurcation diagrams are in line with the biological knowledge. For example, here, the highest the endothelial permeability is, the more likely we are going to reach the inflammation, and same for the LDL penetration. In this model, as I told you before, we have two processes, the pro-inflammatory process as well as the anti-inflammatory one. So for the reduced model, we only considered the pro-inflammatory process. Now, what we are going to do is to consider this parameter that in fact triggers the inflammatory process in our complete model. We are going to increase this parameter and see what happens to our model. One of the results that we got using some clinical data is that when we increase this parameter, the velocity of the wave propagation decreases. So for example, if lambda PA2 is equal to 20, a medium-sized plaque, atherosclerotic plaque, takes about 12 years to form, which is in agreement with biology. So in our model, the attenuation of the disease severity is attributable to the anti-inflammatory processes. And thank you for your attention.
Thank you, Ada. Any question from you? Any question? Okay, doesn't look like that. Okay, so thank you, everybody. So we close then the this last session, and then we close the day or so. Thanks, everybody.
Thank you.